This Relational DBMS course is your all-in-one resource for mastering database concepts, design, and querying, tailored for both academic success and technical interviews. This course offers structured theory, practical exercises, and comprehensive materials to build deep understanding. You'll explore essential topics like ER modeling, relational algebra, SQL, normalization, and transaction management, progressing from foundational principles to advanced applications.
Welcome everyone. Today we embark on a special journey into the world of databases. Whether you realize it or not, databases power almost everything around you. Healthcare records, social media platforms, e-commerce platforms, banking systems. Data is literally the new oil. And by the end of this course, you will have a strong grasp upon the database concepts like normalization, concurrency mechanisms, transaction handling, deadlock handling, SQL, relational algebra, etc. We will see the syllabus in few minutes, provided that you have followed the guidelines of this course. You cannot just sit back, relax, and watch this course as a Netflix series. I have prepared a workbook for you. It's a group of assignments that you have to solve for more clarity. Do not binge watch this course in 1 or 2 days. Eat chunk wise, understand and digest accordingly. We will see the syllabus now. Jai Shri Ram everyone. Welcome to this in-depth database management system course. I am really excited to take you through the journey of this DBMS course where we will break down the complex DBMS concepts into simple digestible chunks. But before we dive into actual learning, let me take you through the structure of this course so that you can make the most out of it. First, I will begin by explaining the official syllabus. I have opened the syllabus right in front of you so that you know exactly what topic we are going to cover and what you can expect at each stage. After that, I'll show you my handwritten notes of over 200 pages of carefully crafted topic-wise content. And these notes are really the backbone of this course. In the description below, you will find the link of course resources. You can have them. And in the course resources, along with notes, we have the reading material, the workbook for you to practice, because without practice, you will not understand what mistakes you could have made. And you'll also have detailed lecture slides and everything you need to follow along to master and revise the subject. The course will be about 9 to 10 hour course. So buckle up, take note, pause, rewind, rewatch, whatever it takes. So let's discuss the syllabus. DBMS consists of 6 units. The first one is introduction. The second one is relational data model and relational algebra. Third one is SQL. Fourth one is high level database design, normalization, functional dependency, all these concepts. And then transaction processing concept. And sixth one is indexing. In the part 1 of this course, we have discussed the first 3 units, which is introduction, data modeling, ER model, all these concepts, relational data model, relational algebra, and the SQL. We have gone to the enough depth that you will not find anywhere on this platform. We have discussed and followed the standard textbook. Various standard textbook I have followed, and if you are preparing for GATE exam, for some interview, or even university exams, this course will be goldmine for you. After watching this course, you will have enough critical ability, thinking ability to solve problems of university level exam and GATE level exam. I can guarantee you the GATE questions will be a cakewalk for you. Okay, so let's begin by the course structure. We will start by discussing the handwritten notes. These are the handwritten notes. It consists of over 200 pages notes, and I can surely say that I have discussed each and every word of this note. Each and every word. Yes, I have not skipped any word. Line by line, word by word, these 200 pages are discussed. And these notes I have prepared with the help of various AI tools and by going through standard textbooks, which are discussed in various universities. So after these notes, let me walk you through these notes. Yes. So till SQL, these notes are prepared. And after these notes, we will discuss. Let me show you. This is my file directory. These are all the videos which I have prepared. And this is the course resource folder. You can access these course resource with the help of description link below. So you will have the handwritten notes. These are the topic wise notes, and this is the complete notes, which is of 200 pages. This is the part 1 of this course, and then you will receive 2 workbook. In these workbook, you will have reading material and around 300 problems, which include gate PYQ and other different problems, their answer key and their solution. You will have reading material. So you can, these are kind of short notes. You can revise from these reading material, and the lecture slides, which are the slides which I have used in this course. So these are the course resources which you can access from the link below. So that's it. I think we should start. Let's begin. Okay, so this is our lecture 1. We will start by understanding what is data, when it becomes information, what are databases, what is DBMS, the advantages of using DBMS or file system. We will see all those things. So we'll start with understanding the data. So what is data? Data is raw and unorganized facts, just like text in the textbook or some observation or figures. Data doesn't have any significance by itself. So what I've written here, data consists of raw, unorganized facts and details. Data lacks a specific purpose. Data has no significance by itself. It's measured in bits and bytes. But when data is processed, when we derive meaning from the data, it becomes the information. Okay, so data on its own is meaningless. It requires processing to extract value and meaning. Without context, it's simply collection of recorded facts. So we can see different types of data. You can read this. When data becomes information, when it is processed, when we derive meaning from that. So information can be said it's processed, organized, and structured data. Okay, it provides the context of data and enables us to make decisions from them. Okay, so what I've written here, processed data. Information is processed, organized, and structured. It enables decision making. It gives meaningful insights. Okay, so what is data versus information? I hope the difference is clear. It's fact versus context, or it's individual versus big picture. Data is the collection of facts, while information put those facts into context. Okay, data is raw and unorganized, while information is organized. Okay, and when data gives us meaning, it becomes the information. Well, if you understand this line, it's okay. Independence versus dependence. Data does not depend on information. However, information depends on data. Data is the foundation upon which information is built. Okay, so when data or those raw and unorganized fact becomes structured and in a clear and concise manner, we derive information, we derived meaning from that, it becomes information. Okay, so data does not depend on information, but information depends on the data. Forms of presentation. Data typically comes in form of graphs, numbers, figures, while information is presented through words, thoughts, ideas. These are the things which we use to express the meaning. Now comes what is database. So I hope the point is clear between the data versus information. Now we'll move to the what is database. Database is electronic storage where data is stored in a way that it can be easily accessed, managed, and updated. So these are the points I have written. Electronic storage. Database is electronic place where where data is stored in a way that it can be easily accessed, managed, and updated. It gives easy access and efficient management, because we want to see the data doesn't remain same always. Data changes with time. So we need such system which gives us privileges to change data. Okay, we need a system which gives privilege to retrieve data whenever we want. So this is what database is. Database is a place where data is stored. That's it. It gives easy access, updation privilege, and retrieval privileges. Okay, so to make real data use, we need database management systems. So what is DBMS? Managing interrelated data. A database management system is a collection of interrelated data. So what is database? Collection of interrelated data. And management system, it is the set of programs to so that we can readily access these data and enjoy the privileges which we want, such as updation, creation, deletion, CRUD operation, which we say. And the convenience and efficiency should be the goal. The primary goal of DBMS is to provide a way to store, retrieve database information that is both convenient and efficient. Okay, so why we use DBMS instead of the file system? Here you can see the image. This is what a traditional file system looks like. There are different points which we can make. It is not the case that every time DBMS is better than file system. Well, we will discuss that also. So the first point which I want to discuss is data redundancy and inconsistency. Okay, so let me first name all the points and then we will discuss it one by one. So first is data redundancy and inconsistency. The second is, in file system, data is a kind of difficult to access. When the file systems are large and we want to access a specific data, it becomes difficult for us. The third point is data isolation. We face integrity problems also in file system. Then atomicity problem, concurrent access analysis, security problems. We'll discuss this one by one. So now it's time to move towards the PDF notes. But before this, let's read this also. Why we use DBMS? 3 points are mentioned here. Data integrity. DBMS ensure data consistency. How it ensures this, we will see in few minutes. DBMS ensure data consistency, accuracy, reducing the risk of data redundancy and inconsistency. Data security, data access. Okay, so it's no point of reading in such a manner. We will first move to the PDF notes. Here we have discussed already what is data and information. Now we will moving to the concept of file system versus DBMS. Should I mention the case, or I hope you are all well aware of why we say data is the new oil, because information is important for us. Based on the information we take decision. That's why companies are willing to pay millions for the data only. Data is nothing but some facts and organized some figures and all these things, but when we derive information, it becomes valuable for us. We make decision based on the data. Okay, so data is the new oil, and that's why this chapter, this subject DBMS is important for us. Now let's see what problem did we face in the traditional file system approach and how DBMS overcame their problems. So let's take the example. I hope you are all well aware of what was file system approach, or what I should do. I should first discuss the file system properly. Okay, so what is file system? Storing data in files and folders. Well, that was file system. So when we save a file, the OS provides proper structure of that file in the memory. What OS do? It saves that file into the memory. So what file system does? Stored and organized data. We can read, write, and delete operation. So this is what we have done in our basic classes. When we first started using computer, we can see the files. We were taught how to rename a file, how to delete a file, how to create a file. You remember those classes where the teacher used to say, so how we create new folder onto the desktop, we do a right click and then go to the new folders, all these things. So that was exactly the file system. We store and organize data using the file system. We can read, write, delete, and file system also gives the access permission. You have heard the name of chmod 764. So we give access permission based on that, with like read, write, execute, or only read, write, or only the read permission. So we can also give permissions in that. Let's see some examples of file system. Windows file system like FAT32 and NTFS. Linux file systems. You can read all this. So let's say if I create a text file named, let's say, ufc.txt. So it is the responsibility of file system to see where we have to store that, what will be the name, what will be the size, what access permission I have to give. So this is what file system does. So in file system, data storage happens in files and folders. How it is organized? It's simple and manual. Security, we give basic level security. Access permissions are given. And in case of retrieval, it's better than DBMS for smaller data. concurrency and security are limited. Now, you know the meaning of concurrency. If I say the textbook definition, it is the ability to execute multiple transactions simultaneously while maintaining the data consistency. So this is what concurrency is. If I give you an example, let's say two people are doing a transaction from the same bank account. Let's say in the bank account, initially I have $5,000. Now, this is me and this is my friend. We are accessing the bank account at the same time. So I withdraw $2,000 from the bank account and my friend withdraw $1,000 from the bank account. Now what will happen? This transaction will try to update the bank account balance by 3,000 because out of 5,000 I have deducted 2,000, and this transaction will try to update the transaction amount to 4,000. But what happens? This transaction does the effect, and then this transaction comes and then it writes on that. So it overwrites the previously written value. What will happen now? 3,000 was there and then it changes to 4,000. So here these transactions are not maintaining the concurrency. I hope you are getting the idea what I mean by concurrency. So in file system, the concurrency is limited, security is limited. And if you are getting the idea that file systems are only those file systems which we see in our Windows operating system like this, let me show you. If you are thinking that this is only the file system, this is not the case. File system can be remote also. So remote file system, the examples are NFS, network file system on Unix. Now let's see how file system. Concurrency in file system means multiple people or process can access or modify the same file at the same time without causing issues. There the issue was there, issue was present because it was not maintaining the account balance into a consistent state. Okay, so unlike DBMS, file system have limited concurrency control, but they can still handle it using different techniques. Let's see. Examples are Google Drive or OneDrive. If two people edit the same file, either one's changes may get overwritten or the system create multiple versions to avoid conflict. Either it will be overwritten or multiple versions will be created so that conflicts can be avoided. So how file system handle concurrency? This was the example of why concurrency was limited in the file system, because when two people try to access or modify the same file, then either overwritten, we will see the changes are overwritten, or multiple versions will be created. So how file system handle concurrency? File locking prevents two processes from writing to the same file at the same time. We can use locks. So the second is append only mode, allow multiple writes without corrupting the file. Journaling file system. So this is all the theory. What point I want to make is the concurrency is limited in file system. Security is limited in the file system. Why? Because in file system, the file system totally relies on the OS based permissions. So the point which I was making, like chmod 764, 7 means owner, 6 means group, and 4 means others. Read, write, execute, read, write, and read only. These are the permissions. We can use basic locking, containerized file access, the isolation or dockerization, antivirus protection. So these are the basic things from which the file system feels safe. But when you think about the student login or admin login, when you switch on your PC, when you see the login permissions or the login passwords, when you enter the password, and that part will open up. So that is not the file system role-based access control. This was OS-based role-based access control. Are you getting the idea? Getting the point which I want to make? See, the file system is kind of individual, based on individual file protection. But when we see this OS-based role-based, this is for a whole. See, when you switch on the computer, you see the student login or admin login, then you click on, if you're admin, then you click on admin, and then you enter the password, and then you'll get all the privileges. But when you enter on the student login platform, then you may not get all the privileges. So this was the OS-based RBAC, which is role-based access control. But when you look at the specific file, and there you get this read, write, execute, or read, write, or read only permission, that is file system access controls. Okay, so I hope you got the idea what is the difference between file system access control and OS based access controls. Now I hope you have understood what is the file system. Now let's come here. Suppose this is the files processing system of a college. Here register, department, users, registration, application program, and this is registration department files, exam department user, exam application program, and exam department files, and same way for the library. Now what happens? Suppose a student name and roll number, a student come to the student is admitted to the college, and his name and roll number had to be stored. So in case of file system, when there is no combined or a single database, we have to store the name and the roll number into all these different files in registration also, exam departments, and library department also. So this is the clear representation of redundancy, and when redundancy exists, it can give birth to inconsistency. How? Suppose the roll number is updated and updation has only occurred in the registration department but not in exam department and library department. Well, this can happen when we are not using a single database. So this is what inconsistency is. Some other data written here and some other data written here for the same name. So this is what inconsistency is. And another big problem is application programs were created based on the files. See, here application program is based on registration department files, exam application program is based on exam department files, and library application program is based on library department files. If the file gets changed, then this will also be changed. The structure, let's say in exam department files, some data type had to be removed. Then in application program also, we have to change that data type in the structure also. If you're not getting, do not worry, just understand that application program in file system are created based on the files. When files are updated, we have to update the program also. And this is not the logical thing to do. Now, what comes in the database approach? We use a single database and only one middleman, that is DBMS. Now what happens? So we use single database for all these files, registration department, exam department, and library department files. And there comes our hero, DBMS. It is the collection of programs to manage data and users. And what we say about database, it is a collection of logically related data. Now, how DBMS is overcoming the overcoming the shortcomings, I should say, for file system. Data sharing at a single database. So no need to maintain different databases. The first point is data sharing is allowed in DBMS approach. The second point is redundancy is reduced. You have to store the name and the roll number only at a single place. No need to have redundancy. And when redundancy is reduced, the problem of inconsistency will also reduce. See, I'm not saying that redundancy totally vanish in this database approach. It exists, but it is reduced to a major extent. Better data integrity. What is integrity? That you cannot enter some data which should not be entered, like voter ID, age cannot be less than 18. There is no such constraint in the file system. I can enter whatever I want, but in databases, constraints are present to ensure better data integrity. So voter ID age cannot be less than 18. Better data consistency. If data is updated at one place, DBMS will reflect the change all over. This was not the case in the file system approach. If the roll number was updated in the registration department only, then we have to change it again and again in all other different departments present manually. So this was a tedious task, and file system does not support the things that DBMS support, like data sharing, reduction in redundancy, program data independence. Okay, so if database changes, if some change happens in the database, no need to change these programs. DBMS will manage. Okay, so now we have to understand how DBMS is ensuring or providing all these benefits over the file system. We have to understand how this works. So this DBMS approach has to be implemented using this database environment. And what is present in this environment? Software part, data part, and user part. we'll see this. This is the software part. We have application programs and DBMS in that. Now end users interact with this application program which have some UI, and in backend the request is sent to the DBMS of what to get and how to get. DBMS and database will interact and give the whatever end user wanted. So in user part we have end users which interact with the application program. We have application programmers which design the application programs. We have the DBA, database administrator, which have the full knowledge of how the data flows into the application programs, and he helped he or she, the database administrator, help the application programmers to design the application programs. He helps to maintain the DBMS and also help database designer to design the database. Okay, so we have three parts: the software part, the data part, and the user part. In software part we have application programs and DBMS. In data part we have database, and in user part we have end users, application programmers, DBA, and database designers. Okay, so this is what database system looks like. In actual database system, this is what the DBMS is, which have database management system plus the database. And this whole picture is of the environment, the database environment, which have software part, data part, and the user part. Okay, so I've also written the important points. The DBA has entire knowledge of the data flow and helps the programmer to create and design database, and also maintains DBMS. So the question is, why we have to design the database? So this question is similar like why we have to include the bookshelves in the library. Why not just we dump the thousands of books into the library? Database is like the structured format to store data. Like in the library, we first ensures that bookshelves are present, and then we insert the books into the bookshelves. Why? Because retrieval is the problem. We need a structured database. Similar, like we need bookshelves in the library so that we can retrieve the book easily. That's why we need a structured database. The next topic is the three levels of data. The first level is real world data. Suppose there is someone named Charles, which has a age of, the name is Charles Oliveira, age 27, and there are two title defenses. This is what the real world data looks like. And what is metadata? The data about data, extra information about the data, like struct, character name. This is the we have used a character array, and then for age we have used int, and for title defense we have used int, and we have written here f1 and f2, which symbolizes two fighters. So this is what the real data was. This is what the metadata is. And then comes the third level, that is data occurrences. When we write f1.name equals to Charles, f1.age equals to 27, now that the data is occurring. Now you are getting the idea. Now this data makes sense to the computer. This was the real world data. This was the metadata. So this metadata acts like a bridge. And when the data occurs, that is f1.name equals to Charles, now for the computer Charles exists, whose age is 27, and the title defenses are 2. The question arises, you have heard about the name schema. Are schema and metadata same? No, schema is the bigger picture. Metadata is for an individual thing. For example, if I say schema is the blueprint of the building, then metadata will be the description of a room. Are you getting the differences between the schema and metadata? Schema is the blueprint of the building, or I should say the blueprint of the database, and metadata can be the description of a table. For example, in database we have student table which have student ID, name, age, department, and department table which have department ID and department name, courses table which have such and such thing. But when I move to the metadata, what does this say? The table name is student, column ID, name, age, data types are int, varchar int, primary key is the ID. So the metadata gives description of a room if the schema is the blueprint of the building. I hope you got the idea. Schema defines the structure of database. Tables, columns, relationships, constraints, and metadata gives some extra data about individual entity. Okay. Now DBMS system, the database system. This system is what the DBMS is, and the database can be divided into two parts, structured and unstructured. Structured data, it can be tabular data, like the data of Indian Railways, IRCTC data, the university data, and unstructured data can be some website which doesn't have any proper format. Sometime videos come, then text come, then image come, then again image come, then text come. This is what unstructured data is. Unstructured data can be even tabular, it can be even the key value pairs. Okay, so we'll see the different types of structured data patterns. So the database system, database and DBMS. Database can be divided into two, structured and unstructured. DBMS, SQL Server, Oracle 9, 11, 12, MySQL. Apart from tabular storage, different ways to store structured data can be key value pairs for high-speed lookups, column-oriented database. In tabular format, we are basically row-oriented. So instead of storing data row by row, we store data column by column. Graph database, in which data is stored in the nodes and relationships are depicted by the edges. For example, social media recommendation systems. Okay, let's say the person 1 is the friend of person 2. In that manner, this is what graph databases are like. Document oriented database, which we use in the MongoDB. Object oriented database, in which we store data as objects. So for conclusion, if you need strictly tabular structured data, relational database management system is the best choice. However, if you need better performance, scalability, or special use cases, these different databases can be the alternatives. Okay, so we have already seen these things. Concurrence in the file system we have seen. Now a final table which shows the differences between the file system and the DBMS. So if you need a basic data storage, file system is enough. If you need structured data management, transactions, scalability, DBMS is the best choice. For smaller data, file system is good. For larger data with other different facilities we want, then DBMS is a good choice. A file system is the storage mechanism that stores data in files and folders. We have already seen that. What is DBMS? It is a set of programs or software used to store, retrieve, and manage structured data efficiently. From this point, the definition is clear. Now, data organization. In file system, it is stored in hierarchical structure. We created the folder first, and then in folder, there can be other different folders also. In that folders, there can be different folders. And in that different folders, there can be different files. So a kind of hierarchy is made. So data is stored in the hierarchical structure. And in the DBMS, it is stored in tables, rows, columns for structured access. In file system, the data redundancy is high. Same data can exist in multiple files. To some extent, redundancies try to be stopped in this file system approach. For example, in the same folder, we cannot save the duplicate files with the same name. We have to change the name, but it is allowed to change, just change the name, and then the same data can be stored again. But DBMS comes with various constraints. We will see in later part. We cannot store the same tuples again and again in the same table, or the same records cannot be duplicated in the same table. Database comes with a constraint so that redundancy can be reduced. And normalization is a specific professional technique to reduce the data duplication. Data consistency, no automatic consistency control in file system. Due to this, potential data mismatches. For example, in registration department, if I change the name do not automatically changes in the exam and library department, but here in DBMS it does. DBMS ensured data consistency through ACID properties, atomicity, consistency, isolation, and durability. We will see them in detail later part. Data integrity checks are manual and error prone, but here in DBMS, again it comes with the strong integrity constraints. Concurrency handling limited, risk of file corruption, conflicts if multiple users edit the same file. But here we have a strong concurrency control techniques, locks, two-phase locking, conservative locking, time stamping protocol, Thomas Wright rule. We will see all those in detail. Security, basic security file, using file permission like read, write, execute. But here in DBMS, advanced security with user authentication, role-based access control. For example, let's see, I have I have some Amazon database. This is our DBMS, and here this is the database, and this is the DBMS, and different viewers are there. For example, the viewers of logistic department, the viewers of customer service department, and some others. So the logistic department only need to see the name, the phone number, and the address. But the customer service department need to see the name, the phone number, the address, and the products bought, or the history, I can say. When we talk about scalability, limited scalability in file system and struggle with large data set. Well, this is not the case in DBMS, because in DBMS we use three-tier architecture, which and along with three-tier architecture we use distributed databases, which makes our system highly scalable, and it support big data. Data retrieval speed, in case of file system, is slower. It requires searching through multiple files, while it is faster. And in DBMS we use indexing and optimize queries, that is SQL, for faster access or faster retrieval. When we talk about backup and recovery, manual backup is required in file system, while we have automatic backup and several other recovery mechanisms too in DBMS approach. There's no direct way to manage relationship between the files. For example, in this folder I have two files, student and course. Can I establish some relationship in file system? No, but I can in DBMS approach. In DBMS, I can name one table as parent table and one table as child table, and child table refers to the parent table. By using foreign key and joins we can efficiently manage the relationships. For complex queries in file system, we require custom scripts and programming to process data. While in DBMS, we have SQL with filtering, grouping, and aggregations. Don't worry, I am just reading this. We will see this in detail. So in later part of the course, you will get more and more idea about this. Transaction support, no built-in support for transaction, while in case of DBMS, we have full transaction support, full concurrency mechanisms that ensures data integrity. Integrity means correctness, and rollback capability means suppose something unexpected has occurred, and so the capability roll back to the previous checkpoint or the previous state. Best used for simple data storage, logs, and documents, while DBMS handling structured data, multi-user applications, complex transactions, DBMS is useful. Examples: NTFS, FAT32, HDFS, while for DBMS I have MySQL, PostgreSQL, Oracle, and MongoDB. Now let's revise, and then we will see our next lecture, that is DBMS architecture in DBA. So what we have done in this lecture, we have learned about the data versus information, file system versus DBMS, how file system brings redundancy, and then redundancy give birth to inconsistency, and there is no kind of data independence. So when we change the file, we have to update the program also, that is not logical. And as soon as we move to the database approach, we have moved on to the single database and one middleman. What is database? Shared collection of logically related data. And what is DBMS? Collection of programs to manage data and users. So to implement this approach of database approach, we need the database environment, and we have three parts: software part, data part, and the user part. In user part, we have end users, application programmers, DB, and database designers. In data part, we have database, and in software part, we have the DBMS and application programs. And then we saw three levels of data. There we have data occurrences, metadata, and real world data. Then we saw the difference between schema and metadata. And then we learned about the structured and unstructured data. Then we moved to the different types of structured data. And then the file system and the difference between the DBMS and file system. Now it's time to move on to the second lecture. Okay, so the DBMS architecture, the different level of schemas. We will first understand what abstraction is. Abstraction is hiding details from the end user for security and simplicity. Whenever I remember about this topic abstraction, I remember my initial college days when when I was going from my home to college. At that time, I was learning about how data is fetched from the backend and showed on the screen or the front end. And the next day, I saw in the train, I saw a child. He was around 3 or 4 years old. He was he was watching YouTube shorts on his mother's phone, and I saw this child know nothing about how infinite scrolling is implemented or how data is fetched from the server, but he's facing no problem in using that application. And this is what abstraction is. See, end users are naive, and if your application is complex, then it won't be a commercial success, because people from different fields use that application and they don't want to learn about the details. When you ride a bike, do you want to learn about the engines? No. This is what abstraction is, hiding details from end users for simplicity. And I have given you an example of Amazon database. In Amazon database, we have like name, phone number, age, liking, disliking, credit card, debit card, UPI ID in case of India, and the history and much more. But for logistic department, they saw only name, phone number, and address. And for customer service department, they see name, phone number, address, product bought. So this we call is the view. The view of the database for logistic department is just this, and for customer service department just this. Why we did so? The first and the foremost purpose is the security, and then comes the simplicity. For security, do you want the logistic department people see your UPI ID? No. In the same way, do you want the student see the admin? Do you want the student to see what admin sees in the college database? No. So this is the point I want to make. Abstraction is also important for security. Okay. So and one another thing, does end user at logistic department care that name is stored in single or in string or character array? The name is encrypted or not? Why would he care? So when we want to achieve this type of abstraction, we use three schema architecture. In this three schema architecture, we include the first level, that is external or the level for end users. Then comes the conceptual level, and then comes the physical level. In physical level, this tells us how data is stored at the DBMS. At conceptual level, we see how data looks to us, and the end user, we see like different views, like we have here the logistic department or the customer service department. Now let's see the different levels. So the first and the foremost level is, or the lowest level is, physical level or internal level. Suppose the Facebook profile picture, the Facebook team want to store it as a compressed image. How this picture is stored in the disk? Initially you click the picture, it was around 1 MB, and then the picture which was stored was around 50 KB. Do you want to know as an end user how they have used the run length encoding for the compression? No. This is what internal level is. Which type of data structure you have used, the type of indexing, where you have stored that file. This is what the physical level or internal level about. Lowest level of abstraction, how data is stored. It involves physical schema, which describes the physical structure or physical storage of the database. Then comes the logical level or the conceptual level. Okay, let's understand this with the help of example. Logical level describes how data looks in the database. Okay, see, in disk, files are stored, but when we see the database, we see tables. How that happens is what conceptual level mapping is. And this is the logical or the conceptual level, where we see tables, constraints, keys, relationships. Okay, for example, in physical level, this is written Dan 10 155 light, Pentoja 1 125 fly. Are you getting the idea what this is? No. But as soon as I map these with names or the attributes like name, ranking, weight, division, then this table start making sense. This is what conceptual level mapping is. Now the table looks like this. Dan, name Dan Hooker, rank 10, weight 155, division lightweight. Name Alexander Pantoja, rank 1, weight 125, division flyweight. And in this level, in this conceptual level, we can also maintain relationships. Like from this rank, I can see the bonus which the player will get. For rank 1 in division flyweight, the player will get $30,000 bonus. So to describe relationships, tables, keys, constraints, we use logical or conceptual level. User at logical level need not to be aware how data is stored at the disk. Even if the format changes, like you have changed from one indexing type to another indexing, you have changed the data structure, you have shifted from one hard disk to another hard disk, or you have shifted from hard disk to SSD. Conceptual mapping will automatically change, but logical view will remain the same. This is what the data independence is. Let's say name, rank, etc. will be in different files. Okay, so I have changed the structure. Firstly, I was storing like this. Now storing like this. Now what I was doing, I am doing this. I'm keeping this in one file, this in another file, this in another file, this in another file. Then what will happen? Conceptual level mapping will change, but the final output which we see will remain same, because we as a user at conceptual level do not bother or do not care how the data is stored at the physical level. Okay, then comes the view level, highest level of abstraction. It provides different view to different end users, simplify user interaction with system. Suppose I have this table, and for end users, what I want them to see, I want them to see just these two columns. This is what the external level is. Provide different view to different end users. It simplifies user interaction with system. Remember the Amazon example? Different view schema for logistic and customer service department. So this is what I was talking about. The views, external. This is for the end users. Conceptual or logical schema. This is for the DBA and the database designers. And for internal level is for the DBA or the database administrator. And one more thing I want to make, one more point I want to make. In external level, I can show those things also which do not physically present in the database. Okay, so let's see, we have a date of joining and we have system date, but in database there is nowhere present the experience column. So if we want to show the users the experience they had in the company, what we will do, will from system date we will subtract the date of joining, the amount of time they have spent in this time, or this amount of time is what their experience is. So this experience doesn't physically exist in the database, but we have shown this. So view can also present those things which are not physically present. Okay, and different people can see different views. For example, let's say I remember a name, Rifleman Jaswant Singh Rawat was Indian Army soldier in Indo-China War, and he single-handedly stopped the Chinese soldiers, 300 Chinese soldiers, for 3 days. So it was literally a 1 versus 300 battle, and when he had the last bullet, he shot himself not to get caught. So let's come back to the topic, Rifleman Jaswant Singh Rawat, and I want to show different people different views, so I can also show them like JS Rawat or R.J.S Rawat. The point I want to make is, in view I can show anything I want from this conceptual level. Okay, now another point, do you think tables are made in the hard disk? No, tables are not present. Tables we use to show people so that they can understand, so that the data start making sense. So in databases, files are present, like I have shown you here. This kind of things is present in the database, but what you see this kind of thing. So in conceptual view, we see what data is stored inside the database, and physical view we see how data is stored. The advantages of this 3-schema architecture, the biggest advantage is the data independence. Changes at the lower level doesn't affect the upper level. This is what data independence is. For logical, if I say if I added a different column, let's say here I added a different column named country. Then you remember the example, the first user, what he was watching, he was just viewing this. And after adding this country column, he will still see this only. So this is what the data independence at logical level is. If I added a different column, it will not affect the view. The data independence at the internal level, then if I change the data structure, if I change the indexing, if I change from hard disk to SDT or one hard disk to another hard disk, it will not affect the conceptual schema. Conceptual mapping will change, but the view which we are seeing at logical level will remain the same. And security mechanisms are applied at the view level. This is another point. Whatever we want to show, we will show. Prevent user from accessing certain part of the database that they should not see. So this is what the three level schemas are: the physical schema, the logical schema, and the view schema. Now comes another topic, the instance of the database. What is instance? The logical view of the database at time t. Suppose at time t I want to see how database looks now. Order ID, item, amount, customer ID. This is kind of snapshot of the database at some time t. This is what the instance of the database is. Okay. Now database schema. What is this? This is the overall design of the database. It includes attributes of the table, consistency constraint. Programmer construct application by using logical schema. See, database schema includes physical schema, the lowest level which we saw a few minutes ago, the conceptual schema or the logical schema, and the view schema. So programmer construct application by using logical schema. Let me give an example. Suppose I want to create an application and this is what my logical schema looks like. So how I will write the code? I will write class orders, int order ID, string item, int amount, and int customer ID. So by seeing this logical schema only, I wrote the code. So programmer construct application by using the logical schema. So what database schema is? It's the overall design. It includes logical schema, physical schema, and the view schema. But to describe this design properly, what we need data models like ER model, relational models, ORM, which we say object relational model, and object oriented models. And another point, to interact with the DBMS, we need language. For example, to interact with the computer, we need high level languages. Similarly, to interact with DBMS, we need language like data definition language, which is used to specify the database schema, constraint checking at the updation. What kind of constraint? The integrity constraint. For example, in voter ID, I want to enter an age. Let's say I enter an age 13. Then it will generate an error that the age should be greater than 18 only. So this is a kind of constraint. So at every time the updation has occurred, the DDL will check the constraints. Then DML, data manipulation language. It's used for database queries and updation, for retrieval, insertion, updation, and deletion. But don't think like that. Okay, we have DDL and DML as different languages. We have a single package named SQL. Another point, that the application, the host application which you write is in JavaScript, C++, Python. But what DBMS understand? SQL. So how they are going to interact with each other? With the help of an interface. Like for Java, we have JDBC, Java Database Connectivity. And for C, C++, we have ODBC. Microsoft developed this Open Database Connectivity. Now comes the DBA, Database Administrator. He has the central control of both data and the programs. He exactly know how data flows in the system. He has a central control of both data and programs that access the data. He works at both conceptual and internal level. You remember? They're the front-end designers, external front-end designers, conceptual database designer, and DBA. DBA, database designers, and DBA. And then at the internal level, DBA works. So DBA works at both conceptual and internal level. What are the functions of DBA? They may ask in the interview. The logical schema definition or modification, authorization control, routine maintenance, backup, security patches, etc. Physical storage management, indexing, security policies, data integrity constraints. So this was all about the schema architecture, and the database administrator. Now let's see from the slides. We will explore the three schema architecture again, or it's a way of revising. In database management, the three schema architecture provides a structured approach to data abstraction. This architecture separates the user's view of data from its physical storage, enhancing data independence and simplifying database management. It consists of physical, logical, and view levels, each serving a distinct purpose in how data is defined, stored, and accessed with the database. We have seen that. The physical level, deep dive into data storage. We have lowest level of abstraction here, how data is stored, which data structure you have used, the type of indexing you have used, deals with the data compression and encryption. This is the physical schema, defines the storage structure, and it focuses on efficient access algorithms. Okay, so what is the purpose of physical schema? How the physical schema is designed for the motive of efficient accessing. Then comes the conceptual schema. It's like designing the database blueprint. It describes the data relationships, describes data stored in the database, the tables, the constraint, the keys, the defined relationship among data, hides physical level structure from users. Then we have learned about the role of DBA, database administrator. DBA use the logical level to decide what information to maintain in the database, ensuring ease of use and accessibility. I have told you that DBA works at both internal level and the conceptual level. So what DBA does at the conceptual level? DBA use the logical level to decide what information to maintain in the database, ensuring ease of use and accessibility. View level, tailoring data for different users. It simplifies user interaction. Sub-schemas and security mechanisms, we have seen that. Then comes the functions of database administrator. Schema definition, storage, structure, and access methods. You can all read this. And then routine maintenance task for optimal database health. This is also a function of database administrator. Periodic backups, security patches, and upgrades. In this lecture, we will learn about different type of architectures, tier 1 architecture, tier 2, and tier 3 architecture from our notes. So we have two machines, the client machine and the server machine. The client machine is the machine where end user works, and the server machine is where the actual database system is running. So if you have started learning development, then you will see the instructor tells you to run this application on localhost. There, the client machine, the server machine, and the database is all present at the same computer or the same machine. The client, the server, the database, all at the same machine. This is what tier 1 architecture is. And when we discuss about tier 2 architecture, this is where client machine invokes database system functionality at server by queries. See here, the user use this client machine, and over the network, this machines send the SQL query, and JDBC helps to this database server, and there the processing happens. The query results are sent back to the client machine then. So what happens? The user uses this application, the client application, and this application sends the SQL query over the network to the database system or at the server machine, where the processing of the query happens, and then the result is sent back to the client application. So the client machine invokes database system functionality at server by queries. This is what the tier 2 architecture is. And tier 3 architecture, this is suitable for the large scale applications like Facebook, Instagram. Client machine is just the front end, and it doesn't contain any direct database calls. Here, this is the client machine, the application client. This is just the front end or the user interface. The application server, or this application server, is present at the business layer. This is where the actual processing of the query happens. The query processing doesn't happen at the database system, which was in the tier 2 architecture, but here it doesn't happen. So the client machines send requests to the application server. Application servers filters out the malicious queries or does the processing and send that part to the database system. Retrieves information, send back to the client machine. This architecture is scalable because we can have multiple servers, multiple clients. Data integrity, app server act as the middleman, and reduces the chance of data corruption. Also, it increases the security as client cannot access the database directly. Here, the client application was directly accessing the database, and some malicious query can corrupt the database because here is the direct interaction, but here application server is present, and the client machine doesn't interact with the database system directly. Application servers comes in the middle, at the business layer. So the tier 2 architecture may fail if some users send malicious query to corrupt the database, but this will not happen in tier 3 as app server will filter out such queries. So we use tier 1 architecture for testing and learning purposes, tier 2 architecture for few devices. Let's say for we are creating something for our home when the number of devices are less, or for example, let me give you a different example in few minutes when we will revise. And for tier 3 we use for large number of users. For example, in Indian Railways ticket booking, in a day around 2 to 3 lakhs or 2 to 300,000 tickets are booked in a single day in India. So for that amount of load, for that amount of pressure, tier 3 architecture is the best suitable. Now let's revise again. You know, all the tier 1 architecture is for the testing purposes, where the client, the server and the database all present at the single machine. In tier 2 architecture, we have clients which use some interface which will help client to fetch data from the server, and JDBC and ODBC helps to secure the connection and the processing happens at the database server. Query will be processed here. Okay, so now let's see examples. In older times when the database systems was not that much advanced, we used to book ticket by going to the railway station. Not me, my father and the older generation people, they used to book ticket by physically going to the railway station, fill the form, and from that form they submit to the window, and the authorized user, the clients, will fill the details or the railway staff, they were the clients, they will fill the details and send that details to the server. Server will process, generate the ticket and send back to the client. This is what happens here. These are the railway staffs, the clients. Here are the users or we people. We tell information to the clients. The clients, these are the authorized clients, will directly interact with the database server. Like here, the client will fill the details and send to the server. Server will process. Processing happens at the database server, generate the ticket and send back to the client. Or another example, when we physically go to the bank to credit or debit by form or check filling, the authorized client, the clerks, will fill the info, send it to the server will credit or debit the balance, send info back to the client machine. Okay, so in tier 2 architecture, there will be limited authorized clients, limited database. So the maintenance part was easy, but security was definitely a concern because client interact with the database directly. In 3-tier architecture, there are the users, these are the client machine. Here the client is just the front end. The middleman is the app server. The client machine tells the app server whatever it wants. App server does the processing, fetch data from the database, send it back to the client machine. Here, the business layer query will be processed here. Client is just the front end, and this is the database. The business layer will show the user the data, in whichever format the user demanded. Okay, so client will not interact with the data direct or the database directly. Business layer comes in the between. Maintenance becomes an issue, but architecture is scalable and secure, and nowadays we have budget and enough manpower, so we will manage that maintenance part. But the important things, which are scalability and the security, that we have achieved with this 3-tier architecture. Now, before ending this lecture, let's discuss some basic terms which will be helpful for us in the future. The first is data dictionary. The data dictionary is database about the database. Data dictionary stores the metadata or the schema, the file specification, the name, size, access, permission. Okay, so data dictionary, you remember the entity where the metadata or the schemas are stored. This is what the data dictionary is. Database about database or information about the actual database. Intention and extension of the database. Intention means the schema, and extension means populating the database with data or data feeding. In schema, changes are not frequent, while in data feeding or extension, changes may be frequent. What is database model? The schema. Same name, it's just the synonym. What is data model? tools to describe the database model or the schema. Data model is complete if it answers three questions. The first one is storage, and for example, in relational model, it answers that I will store the data using tables and I will store data in the structured format. Second, manipulation language, how I am going to update, create, or not create, just retrieve, update, insert, delete. For that, the RDBMS, relational data model, answers as SQL. And for integrity constraints, there are different integrity constraints in this. What is integrity constraint? First, let's understand this. Integrity means correctness, and constraint means that restricting the user to enter the incorrect data, or restrictions which allow correct data to be fed. These are the different integrity constraints, like domain constraint, entity integrity constraint, referential integrity constraint, or key constraint. Let's see them one by one. Domain, for example, I am constructing the database for voter ID. So I will restrict the age, I will restrict the domain of the age from 18 to, let's say, 130. Or for mobile number, I'll restrict the length to 10 characters. Next constraint is entity integrity constraints. This tells that in a table, primary key should exist, or I should say there should be at least one attribute which is unique and not null. This is entity integrity constraint. Third is referential integrity constraint. They say if you have a relationship between two tables, then the child table which refer to the parent table have the values in the subset of parent table. And the next is, or I should describe more when we learn about the keys, relationships, then we will see more. Just remember that child table refers to the parent table, and there should not be any value present in the child table which is not in the parent table. Okay, so this is what referential integrity constraint is. The last one is key constraint. It says there should be at least one candidate key with have at least one unique attribute. This was all about some entity or the integrity constraints. In the next lecture, we'll learn about ER model. Let's revise this lecture. In this tier 1, tier 2, and tier 3 architecture, the client server all at the same machine, then tier 1 architecture, tier 2 architecture, when application is partitioned into components, the client and server, and tier 3 architecture, when application is divided into 3 logical components, client is merely the front end communicating with application server, which then interacts with the database. Advantages of tier 3 architecture for web application: scalability, data integrity, and security. You can read. So the key takeaways from this lecture and the last one is the 3 schema architecture provides a robust framework. What were the 3 schemas? The external level, conceptual schema, and the physical schema. A robust framework for managing data abstraction, enhancing data independence, and simplifying user interaction. We have also understood the roles of physical, logical, and view levels. And then the selection of a suitable architecture is also important. For example, in tier 3 architecture is essential for ensuring scalability, data integrity, and security. Particularly in web applications, regular maintenance and DBA functions are vital for maintaining optimal database health and performance. In the next lecture, we will start with ER models. In the last lecture, we have completed our unit 1. From this lecture, we will start our unit 2, which is entity relationship model. We'll first learn about the data model. Then we will move to ER model. We will understand what is entity relationship, attributes, cardinalities, constraints. Then we'll move toward the extended ER model, which include specialization, generalization, aggregation, attribute inheritance. Then we will practice the ER model for banking system and social media platform. So we'll first start with understanding what is a data model, and then we will learn about the entity and the relationship. So from here we'll learn the data model. You have to remember 4 things about the data model. It is the collection of conceptual tools for, the first thing is describing the data. The second is the data relationship. Third is constraint, and the fourth is the meaning. So data model is a tool for describing data relationship, consistency, constraint, and data meaning. Okay. Then what is ER model? Here E means entity. It's an object. For example, the student, car, anything. Object, real world object. It is based on the perception of real world object. and the relationship among those objects forms the ER model. It's a high-level data model. What is the meaning of high-level data model? Which means even a non-technical person can understand what this model wants to convey. So ER model is a high-level data model based on the perception of real world. It consists of collection of basic objects and the relationship among them. You got the idea? Now we have talked about what does a complete data model offer. It tells you about the storage, the manipulation and the constraint. But ER model does not tell you about the storage and manipulation language. It only tells you about the constraint. So I can say it is not a complete model. Then why are we studying this? Because ER model acts kind of bridge to understand the relational model, which is complete model. So ER model is not a complete model itself, but we can create high level design, and from that high level design we can implement the relational model. Okay. Now what are the tools or constructs in this ER model? We have entities, attributes and relationships. Entity. What is the meaning of entity? Entity in itself is a vague term. You have to specifically tell what do you mean by entity. Either you mean entity set, entity instance or entity type. For example, in a table, let's say the student table, this is the entity type. When you enter some value, let's say Kshitij, age 21 and another values. So when you enter these values, this becomes the entity instance. For example, here the roll number, the name, the age and the course, these value makes the entity instance. And then entity type, which is the table or class blueprint. Entity set, set of all these instances. See here the example. Here we have is a student table. That when we define the class blueprint, it is entity type, the roll number, which is the primary key. What is primary key? For now, you understand it's like a property of that entity type from which we can uniquely identify an instance. For example, from roll number, I can uniquely identify any student in the college. Name, age, course, this is the entity type, the class blueprint. And when I talk about the instance, which means you have filled the values for them, the roll number, the name, the age, and the course, this becomes the instance. And when I talk about the set of all instances, it becomes the entity set. Okay. Now, symbol for entity types. Remember, there is no symbol for entity instance and entity set. There is only a symbol for entity type, which is this rectangular box, and here you write the table name. Now there can be two different type of ETs. From now we will call entity type as ETs. Strong ET and weak ET. Strong ET means this table can exist independently. The instances of this table can exist independently, while for the weak entity type I cannot say so, because they have no individual instances. They depend on the existence of strong entity type. For example, your RFID card of college. You have RFID card, which is the main card or the central card. You also have the library card. You also have the mess card where you can eat, and you also have a hostel ID. When you leave the college, this entry is removed, and as soon as this entry is removed, the depending entries, that is your entry from the library database, the mess and the hostel ID, are automatically removed. Or take another example. Suppose a person works in the company, and company also offers medical benefits to its dependents. For example, his mother, his father, wife, or some children. Now, when the person leaves the company, the dependents will not receive the medical benefits anymore. So they have to remove those dependents from the database. See, this weak entity type is not some kind of drawback of ER model. It seems so, but it is not the drawback. We want such dependency. That's why we have created these kind of entity types, which are dependent on some strong entity types. So when I remove this dominant entity instances, then the subordinate entity instances will also be removed. For example, person A has the dependent person B, C and D. So when person A entries will be removed from this table, then B, C, D will automatically be removed from this dependent table. Okay, so the employee, this strong entity type, strong ET, has primary key of its own. The entity instances of this strong entity type, we call them as dominant, while for the weak we call them subordinate. The dependents, the weak entity type doesn't have a primary key of its own. We also call them as a regular or independent entity type. Here we call them as dependent entity type. Same example I have written. A company gives medical insurance to the employees and his dependents. So here the dependents entity type depends on the employee ET. When the employee leaves the company, the existence of dependent for the company also vanishes. Okay. So we have learned this. Now we are going to study about the attributes. Attribute mean the properties of the entity type. For example, fighters, they have the attribute of ranking, weight, reach, record, age. These are the properties which describe this fighter. And when you fill the values of these properties, they becomes the entity instances. Here in the above table, the roll number, the name, the age, the course, these are the attributes. And when you fill the values, they becomes the instances. Okay, so here is the example. This age, height, weight, reach, these are the attributes. And when you fill the values, it becomes the instances. Now, setting the domain of a specific attribute is also important. We call them as domain constraint. For example, in a voter ID, I set the age value to should be greater than 18 and should be less than 130. And if I try to enter 500 as age or 12 as age in the voter ID database, it should throw an error. This is what the domain constraint is. So domain is set of values an attribute can hold. The value of attribute must come from its respective domain. Now we'll learn about different type of attributes. The first one is simple attribute, which are atomic, which cannot be further subdivided. For example, either male or female. Composite attribute, which can be further subdivided. For example, name can be divided into first name, last name, or middle name or last name. For example, address can be divided into street, the locality. Then comes the single valued and the multi-valued attribute. Single value, as the name suggests, they can hold a single value. For example, roll number. And for multi-valued, they can hold multiple values, phone number and email. Stored attribute and derived attributes. Stored attributes means that they cannot be derived from some other attribute. For example, date of birth. You have to know date of birth, but you can derive the age from date of birth. So I'll say age is derived attributes and this date of birth is stored attribute. This is system date. Let's see this example. Student entity type. The roll number is the key. What is key means? From this, I can uniquely identify a tuple. Age is the derived attribute, and we show the derived attribute by dotted oval, and multivalued attribute by double oval. And then date of birth is stored attribute. Section, name is composite, it is divided. Address is composite, it's divided. Class is single. Okay, so these are and a special type of attribute which is descriptive attribute. Attribute of a relationship is called descriptive attribute. For example, see here. Employee works in department. Now I want to add since. So can I add since here in the employee? No, I cannot, because an employee might have worked in the different department at different times. So can I attach this since to departments? I cannot do that, because this will also raise an issue, because multiple employee can work in the same department. So what is the best solution? We make this attribute since as the attribute of a relationship which describe a relationship. Hence we call it as descriptive attribute. Okay. Now an important point, that null can also designate that attribute values unknown. Null, either it is unknown or not applicable. You already know that. Now symbols for attribute in the ER model. Simple, single valued and stored, just a single oval. Simple, single valued and derived, like we did with age, then it is the dotted oval. Simple, multi-valued and stored, double oval. Composite, single valued and stored, like this. Composite, multi-valued and stored, like this. Okay. Now we'll learn about keys. What is the meaning of key? A property or attribute which is used to uniquely identify an instance of a particular entity type. In a table, if you want to uniquely identify a record, you have to know the value of an attribute. If you know that value, you can uniquely identify. So that value or that property or that attribute is known as the key. It can be either group of attribute also. For example, if you know the roll number of a student, then in the college database, from so many instances, you can uniquely identify a single instance. This is what key is. Attribute or attributes that help in uniquely identify a record in the entity set. It is that differentiating agent which differentiates the different entity instances. Different type of keys, the super key, which is the most general key, an attribute or set of attribute which uniquely identify a particular instance of an entity type. So when I say key, I mean by super key. Then comes the candidate key. What is the meaning of candidate key? Minimal super key. Minimal super key. I am not saying minimum. I am saying minimal super key. Minimal and minimum are different things. Minimal is related to the property, while minimum is related to the number, cardinality. So what is minimal super key? That if you remove a single attribute from that set of attributes, it will dissatisfy the condition. You will not be able to uniquely identify a tuple. So for super key, which means key, the set of attributes which uniquely identify a tuple, and for candidate key, the minimum number of attributes which help in unique identification, which is what the candidate key is. See here the example. For example, I can say roll number is the candidate key. If I say name and roll number, will it remain the candidate key now? No, because I can remove the name and I will still be able to uniquely identify a tuple. So this is not minimal. What does minimal mean? That, for example, see this. If you remove even a single tuple, or if you remove even a single attribute from that set, you will not be able to uniquely identify them. Here I am able to remove and still able to uniquely identify. Let's assume in the whole database, the name and the father's name, the combination doesn't matches ever. So I can say the name and the father name can also act as candidate key. Maybe the name can be common, but when you combine name and father name, the chances are less. I assume that in the database, there are no two persons which have name and father name common. So this can act as the candidate key. Is it minimal super key? Yes, because if I remove name, well, father name can be same. If I remove father name, name can be same. So I won't be able to uniquely identify. That's why the combination I will require. And is it satisfying the property? What property? Minimal property. That even I remove a single attribute, I won't be able to uniquely identify. So this will be a candidate. Name. A single name can be common, so it is not a key. More than one candidate key is also possible. For example, here from roll number I can also identify. From name and father name combo I can also identify. Every candidate key is a super key, but vice versa may not be true. How? For example, let's say you took the set of all attributes. Will it become a key? Yes, because in a table, in an entity type, no two instances can be completely same. So if I take all the attributes as my differentiating factor, will they yield different tuples every time? Yes. So will they act as unique identifier? Yes. So all the attribute combo, will they act as super key? Yes. Now if I try to remove one attribute, will it still act as super key? Yes. Let's say the roll number is preserved here. I keep removing from them until I am left with this roll number. So this roll number still remain a super key. But with roll number, let's say I am adding name. Will it remain candidate key? No. What I want to say is this is super key and this is candidate key. This is super key and this is candidate key. So every super key is not candidate key. We have different values here also present. But every candidate key is in this bigger circle. Let me draw. This is candidate key and this is super key. So here are different values. Are they candidate keys? No. But here whichever values are present, they are in this bigger circle, which is super key. So I can say every candidate key is super key, but vice versa may not be true. I hope the idea is clear. Primary key. One of the eligible candidate key is chosen as primary key, and remaining keys will then become alternative or secondary keys. For example, I have this candidate key and this candidate key also. Among them, I will choose one candidate key as primary key. For example, let's say generally we choose the shorter one. So let's say we choose the roll number as the primary key. Then this candidate key will become the secondary key or the alternating key. This is alternative or secondary key. Okay. Now primary key must have two constraints followed. First one is primary key must be unique, and the values in the primary key cannot be null, because primary key is the one on which we do the searching. Values can't be null here. Primary key must follow these two constraints, that is uniqueness and not null. And another mandatory thing is, when table is defined, the primary key should be mandatorily defined. Okay. So now I can say the super key is the bigger circle, and then the minimal super key is the candidate key. And among the list of candidate keys, I choose one candidate key as primary key. So you understand this relationship? Now we'll learn about the foreign key. Attribute of one entity type which is acting as primary key in the other entity type. See here. In this entity type 1, I have a primary key B and a foreign key A. So here, this foreign key is acting like a primary key in the other entity type. So here, this is what I've written. Attribute of one entity type. This attribute of one entity type which is acting as a primary key in another entity type. What the idea? Let me repeat. The attribute of one entity type. See, this attribute of this table is acting as a primary key in the another table. This is what foreign key is. Let me give you an example. See here. Suppose I have this table 1 department info, where I have department ID, department name, department location, and department budget. And another table have employee info, which has employee ID, employee name, employee date of birth, employee city, and department ID. See here, this department ID is the primary key in other table, and this department ID is acting as a foreign key in this table. Attribute of one entity type acting as a primary key in another entity type. This is what foreign key is. So this is foreign key. Now, what is the purpose of this foreign key? The purpose of the foreign key is to reference another table. What does I mean? What do I mean? See here, employee ID, employee name, employee date of birth, employee city. Now I want to know in which department Ayush works. So someone say department 101. I say, I don't know department 101. You tell me he work in IT department, electronics admin, or account department. To tell the name, I have to reference another table. So from this Ayush, I will know the department ID, and then I'll reference another table. Department ID means the IT department. So then I can say Ayush works in the IT department. Are you getting the point? So child refer to the parent. That's why we call it as child table, and this as parent table. Parent table will have the primary key, and child table will have the foreign key. Remember this analogy. Child refer to the parent, and child will have foreign key and parent will have primary key. Okay, and this parent table is also known as referenced table, which is referenced, and which table is referencing the child table. Okay, so primary key need to be unique, but there can be duplicate values in the foreign key. See, we have implemented that unique and not null constraint on only. Foreign key can have duplicate values. Foreign key can have null values. Primary key cannot have null values. Primary key cannot have duplicate values. Did you got the idea? We have implemented the constraint on primary key only. Foreign key can have null and duplicate values. But see the case here. Suppose I am searching for this Ayush works in which department? So I see here Ayush. Here it is written department 101. But as I reference the parent table, this entry is not present. What will happen? Integrity constraint, referential integrity constraint. Violation will occur. Error will be generated. Ayush 101. I cannot see an entry here by the name of 101. Then what will happen? Referential integrity will be violated. Foreign key entries of one table need to be the subset of primary key entries of another table. I cannot have some different value which is not present here in the primary key. So foreign key entries of one table need to be subset of the primary key entries of another table. Okay, so understood what we mean? What do we mean by foreign key? Then we will learn relationship in our next lecture. Let's revise what we have learned. We first started with data model, collection of conceptual tool for describing data, relationship, constraints and meaning. There we learned about ER model, we learned about entity, attributes. What is entity? Entity is a vague term. You have to specifically mention entity set, instance or type. Then we learned about the strong entity type and weak entity type. Then we learned about the attributes. What are attributes? Properties of entity type. Domain constraint we have seen, different type of attribute. Example we have seen. Descriptive attributes which is attached to the relationship itself. Then we learned about symbols of attributes in the ER diagram and different type of keys. Super key, the key itself. Attribute set used to unique identify particular instant of entity type. Candidate key, minimal super key, that I cannot even remove a single attribute from that set. Otherwise, the unique identification will be removed. Then we learn about the primary key. Out of several candidate key, we choose one key as the primary key, and primary key is unique and not null. Then we learn about the foreign key, an attribute of one entity type which is acting as a primary key in the another entity type. One entity type acting as a primary key in the another entity type. Okay, and the values of the foreign key must be the subset of the primary key. And if it doesn't happen, then the violation of referential integrity occurs. Let's understand relationships now. If I say customer places order, professor takes course, student enroll course, citizen has vehicle, or in banking system, let's say we have three entities: customer, loan, amount. Then I say customer borrow loan, customer deposit amount. What I'm trying to do here is to establish some relationship between two entities, between entities like customer and loan, customer and amount. And what is the relationship name? Borrow, deposit, place, take, enroll, has. So these are the relationships between the entities. These are the entities, and this is the relationship. Relationship is an association. Relationship is an association between instances of different entity types. Okay, we use diamond symbol for the association. According to the definition, yes, one thing I want to mention, the relationship is between the instances of the entities, not between the entities. According to definition, it is present between the instances of entity types, but entity instance have no symbols in ER model. Only entity type have. So we have entity type symbolized in the ER model, not entity instances or entity sets. So we can only show the relationship between entity types. That's why we show the relationship between entity types. And the relationship is symbolized by this diamond symbol. Okay. We have different type of relationship: unary, binary, and ternary. Unary means student is the roommate of student. Okay. Or if I write like the user profile is the friend of user profile, then user is a friend of user profile is a friend of user profile. Or student is a roommate of student. Employee manages the employee. Let's say among 10 employees, I choose one employee to manage all the team. So employee manages the employee. Student is the roommate of student. To show these type of relationship, we use unary relationship. Binary, we have seen employee works in department. Teacher teaches the subject. And for ternary, teacher teaches the subject and the class is also defined. So how are we going to write the name? Choose the first letter and write like this, TCS. Okay, for ternary relationship. Now, cardinality of binary relationship, this is an important topic. It is defined on two things. The first is the maximum cardinality. Based on maximum cardinality, the second one is based on the minimum cardinality. For maximum, let's see this one-to-one cardinality. What does this mean and how are we going to read this? This one-to-one doesn't mean exactly one. We are segregating based on maximum cardinality. So what can be the maximum cardinality? At most one. So this one male can marry at most one female, or one female can marry at most one man. Okay, it can be possible that a man doesn't marry anyone. So that's why I've written at most one. It could be zero also. One-to-many cardinality. One customer can place many order. Many student can join one college or single college. So this was many to one and one-to-many cardinality. Here zero or more can be the name. Many to many cardinality. Many student joined many course, or I can also define like both ways. See, one student can join many courses and one course can be joined by many students. So this one to many or many to one, when they both mix up, it becomes the many to many cardinality. Got the idea? Now, how we represent this? Either you write like the symbol one, many, one, or many. You can write like this, or there's another method that to symbolize one, you can use this arrow, and for many, keep the line simple. So this represents one and this represents many. Okay. So we have understood all these four. Now, based on the minimum cardinality, what does total participation constraint mean? It means that there cannot be, let's understand with an example. Suppose I have this department and this employee. This department has many employees. This department has only a single employee. So if I implement the total participation constraint on department, then I should say that in a department, there must be at least single employee. If this employee leaves, then this department will be shut down. This is the meaning of total participation constraint. We have minimum cardinality of 1, which means at least 1. Here one-to-one means, one-to-one cardinality means at most 1. Here total participation constraint means at least 1, because it is based on the minimum cardinality part. Partial participation, minimum cardinality can be 0. Gives more flexibility, and this is the by default setting. Employee can exist who are new joining and their department are not allowed. So let's summarize the meaning of total participation and partial participation. Partial participation mean, suppose if I implement partial participation on this entity, then there can be instance of this entities, there can exist the instances of this entity which are not related to instance of other entity. But if I implement total participation here, there cannot be any instance of this entity which are not in relationship with the another entity. Okay, entity type A will be in total participation if there cannot exist any instance of A who is not related to any instance of B. And if such instance can exist, then I say it was partial participation. Symbols are for total participation, double lines; for partial participation, a single line. Okay, see this example. Total participation from a student entity that is not related to any course. So course may exist without any student due to this partial participation, but every student must be enrolled in at least one course. Okay, I'll repeat again. For total participation, if I implement total participation on a student, then there cannot be any student which is not related to the entity type B, which is course here. Okay, now the concept of strong and weak entity type. Do you remember the employees and the dependent, or RFID and the college, RFID and the mess ID, hostel ID, library ID example? So strong and weak entity type. These are the few questions that need to be addressed. The first one is cardinality of the relationship. So what is the answer? 1 to many. From strong side 1 and from many side weak, or so from weak side many. See here. Another example of strong and weak. The existence of apartment depends on the existence of bed. And to describe the identifying relationship, we use this double diamond. And to describe the weak entity set, we use this double rectangle. Okay, so Building is the strong entity type here and apartment is the weak entity type here. So what will be the cardinality? 1 to many. From strong side, 1 here, see here. One employee can have many dependents, but it cannot be possible that a dependent has no employee. You got the idea? Okay. An employee can have 0 or more dependents. Dependent must have at least one employee. There can't be any dependent with no employee. Okay. Next question. Weak entity type doesn't have its own primary key. We have discussed previously. Then how are its instances uniquely identified? See here. A building can have many apartments. How are we going to identify a particular apartment? Or an employee can have many dependents. How are we going to identify a particular dependent as they do not have their own primary key? So what are we going to do? Every weak entity type, for example, here the discriminator was door number. Here the discriminator is dependent number. With the help of the discriminator and primary key of strong entity type, we identify the instances of weak entity type. So the key for weak entity becomes, or we derive the key of weak entity set from the discriminator and the primary key of strong entity type. Getting the idea? Let's say if company says that they will benefit only one dependent, then there is no need for dependent number also. Yes, this is important. Let's say 2, 3, 4. Now, if I say that dependent number 3, so I'm not able to identify a particular dependent. Are you talking about this dependent or this dependent? So I need the employee ID also. If I say I'm talking about the employee A dependent number 3, then I can uniquely identify, oh, you are talking about this. Getting the idea? That's why we need employee ID and dependent number, the combination of both to identify a particular dependent. But let's say if I only have single dependent, then do I need dependent number to identify a particular dependent? No. I can directly say the dependent of employee A or the dependent of employee B. So there is no need for discriminator also at that point. So the question was, weak entity type doesn't have its own primary key. Then how are its instances uniquely identified? With the help of discriminator and the primary key of strong entity type. But if weak entity has only a single instance associated with a strong entity, then there is no need for discriminator also. The primary key of strong entity type will do the work. Okay, third question. What are the owner or identifying entity instances? These are the instance of employee entity type. Okay, what are the owner or identifying entity instances? Instance of employee entity type. Okay, there is a misconception that I want to clear. People think that owner entity type and the strong entity type are same. They are not the same. The definition of strong entity type is they have primary key of their own. And the definition of owner entity type is that they indulge in the identifying relationship with a weak entity type. I'll give an example to clarify. So the third question was, what are the owner or identifying entity instances? Instances of employee entity type in our case. Name of relationship between strong and weak entity type and its symbol. The identifying relationship symbol was the double diamond. Is owner always a strong entity type? No. Okay, see this example. Owner need not to be always strong entity type. Suppose I have account. Based on that account, I have taken a loan, and for that loan, I do the payment. So here, payment will not exist if I do not have a loan, and loan will not exist if I don't have an account. Do you think this loan is a strong entity type? No. But is it the owner entity type? Yes, because it indulges in the identifying relationship with a weak entity type. Is this account owner? Yes. Is this account strong? Yes. Is this loan owner? Yes. Is the loan strong? No. A loan is the owner of payment, but not a strong entity. A loan must link to an account, whereas an account can exist without a loan. Okay. Associated with a loan. Focus on the total participation. An account can have multiple loans, but each loan belongs only to one account or EMI, but each payment is linked to a single loan. So our question was answered. Is owner always a strong entity type? No. Next question. Can we make a weak entity type as a composite attribute of a strong entity type? The question is asking is to directly make this an attribute of a strong entity type. Can we do that? Yes, we can do that, but with a condition. What is the condition? That this attribute should not further indulge in any kind of relationship. If that's the case, then yes, we can make this as the attribute of a strong entity type. Okay. In this case, we should discuss another point, that what will be the key for this payment. So what will be the key for loan time, or the key for loan and the discriminator of the payment? So primary key of account and discriminator of loan, this becomes the key for loan, and the key of loan plus the discriminator of the payment will act as the key of payment. Got the idea? Now see this. So the question I was asking, can I transform this into this? What I did, I directly make the dependent as the attribute of employee and not be in the further relationship with other entity type. Only in that case we can always show like this. Okay. Weak entity type will always have a total participation. I've already told you that weak entity type will always have a total participation. Total participation is must from weak entity side. Why? Because a payment cannot exist without loan. A loan cannot exist without account. What is total participation said? It said that there cannot be any instance of this entity which is not associated with the entity type B. So here this entity is A, this is B. So there cannot be any payment which is not associated with loan. There cannot be any loan which is not associated with account. That's why total participation from weak entity side is must. Existence dependent. Whenever any entity type A has total participation with entity type B, then A is existence dependent on B, because the existence of weak depends on the existence of strong. The existence of dependent depends on the existence of employee. The existence of payment depends on loan, and loan depends on the account. The existence of apartment depends on the building. Hope you are getting the idea. This means that instances of A cannot exist without being linked to instances of B. Okay. Now, this existence dependence can be segregated into two parts: identified dependency and referential dependencies. The previous four examples which I have given you about loan payment and the apartment building was regarding identified dependency between strong and weak, where primary key of weak, or I should say the key for weak, cannot be null. And because if key has become null, how are you going to identify that particular record? So key for the weak entity type cannot become null. And how it won't become null? By discriminator and the foreign key not being null. Getting the idea? See, what was the foreign key? First understand that. What was the foreign key? Here, the account attribute of this loan will act as a foreign key, because in account there will be primary key regarding that. So the foreign key, this cannot be null and this cannot be null. Getting the idea? So for identified dependency, the key for weak cannot be null, and for that individually they cannot be null. So this was the identified dependency. Then referential dependency. This is between the strong and strong. We are talking about existence dependency. It can be of two types: between strong and weak, and between strong and strong. When I'm talking about being strong and strong, then it is about between two strong entities: student, book. Firstly, understand this diagram. Student has two attributes: student ID and student name. It is indulging in a relationship where total participation has been applied on this book, which has to attribute book ID in the title. Okay, so it is just an example. It may not be that much meaningful, but it will give you an idea what I want to convey. So to fill this student data, student ID and student name, I can freely feed the data. For book ID and title, I can freely feed this data. But will it respect this total participation? No, it will not. What does the total participation mean? That but by applying the referential integrity constraint. On book side, I cannot have any book which is not issued to any student. To implement this, we can use foreign key. So what I did, the primary key becomes the foreign key in this book table, and this foreign key now cannot be null. Now there cannot be any book not issued to any student. So by using the primary key of strong entity by using the primary key of strong entity as the foreign key in another strong entity to respect that total participation is what the referential dependency here is. Okay, so now here total participation is respected because there cannot be any book not issued to any student. Because so if I fill like this book ID, the title, I have to fill something because I have implemented a not null constraint on a foreign key. See, foreign key can be null. Foreign key can contain duplicate data. But when I apply not null constraint on foreign key, then it will act as implementing the total participation. Because now there cannot be any instance of book which is not given to any student. In a way, total participation respected. Let's learn more about the foreign keys. We call it as referencing relation, the parent table as reference relation. Primary key column of the parent. Reverse need not to be true. This I've already told that child table, the values in the child table under the foreign key column should be the subset of the values of the parent table under the primary key column. You got that? Deletion and updation from parent and insertion into child may cause the violation of above rule. What I want to say, let me write that child table, I'm writing in layman term, don't start pointing out mistakes. See, I'm just writing like that. Okay. Child table, let's say in a simplifying manner, is a subset of parent table for the foreign key column here and primary key column here. Now, when this rule will be violated, when I delete or update at the primary key column in the parent table, or I insert something new into child table which is not present in the parent table. Let me repeat, if I delete something from the parent table which the child table is referencing, first case that one, or I update something, second case. The third case is if I insert something new at the child table which is not present in the parent table, then the referential integrity constraint will be violated. Foreign key may refer to the primary key of the same relation. Another point is, for example, self-referential. Employee number 2, Sai. Manager number 1, looking here, Ajay. So employee number 2, Sai, has the manager Ajay. Okay, you got the idea. So the foreign key can refer, or the child table and the parent table can be same. Foreign key can refer to the primary key of the same relation, self-referential. Okay. An important point, on delete cascade, set null and set default. See this example. A is the primary key. C is the foreign key referencing with on delete cascade. Let's first understand the meaning of on delete cascade. These are the conditions set on the foreign key when due to updation or deletion happens in the parent table that violates the rule, then corresponding value of the child table are updated or deleted. On delete cascade. Cascade means one after the other. If something is deleted from the parent table, then the same thing from the same record from the child table will also be deleted. If I update something at the parent table, then the same record at the child table will also be updated. Okay, or the same value under the foreign key column at the child table will be updated or deleted respectively. Okay, so this is what on delete cascade is. Set null on delete violation. When this condition is set on foreign key of a child table, the value corresponding rows are set to null on deletion. Let's say if I deleted something from the primary key, primary key of parent table, which was being referenced by the foreign key of the child table. And if that value is deleted, then I will insert null values at that point under the foreign key column of the child table. See this example. Suppose like that. If okay, so set null on delete violation, set default. When this condition is set on foreign key of child table, then the foreign key value of corresponding rows are set to default value rather than null value. See, firstly, what we were doing, we were deleting that or updating directly. When some updation or deletion has happened in the primary key column of the parent table, that value was being referenced by the foreign key of child table. If that is the case, then we will automatically update or delete the value of the foreign key. If the condition is set null, then instead of deletion or updation, what we will do, we will set null. If it is set default that instead of updation or deletion, instead of setting that null, what we will do, we will set the default value. But if the default value is not present, then this will cause the error. Violation will occur. When this condition is set on foreign key of child table, the foreign key value corresponding rows are set to default value rather than null value. But if this default value is not present under the primary key column of the parent table, then violation will occur. I want you to imagine a proper example. Primary key column, foreign key column, foreign key column. Okay. The first case was on delete cascade. Suppose here 2, 2. So this foreign key was the 2 is deleted. If 2 is deleted, then this entire record will be deleted from the child table. Okay. Case number 2, set null. If 2 is deleted, then the entire record won't be deleted, just null will be set here. And if it is the set default condition, then null won't be set, but the default value will be set. What will happen if the default value of primary key is not mentioned prior? Then it will cause the violation error. See this example. Here A is the primary key, C is the foreign key referencing A on delete cascade. This is the example of self-referential. So if 2, 4 is deleted, all the tuples where C equals to 2 must be deleted. Let's say if I delete this 2, 4, then all the tuples which have 2, 2 will be deleted. So this delete 2, 4 since C equals to 2 is referenced, 5, 2 and 7, 2, they must also be deleted because we are talking about on delete cascade. And if 5 and 7 are deleted, to delete more, so these 3 tuples will be deleted. You're getting the idea? See, 2, 4 was set to delete. Now check wherever 2 is there, delete that tuple. If I delete that, then 5 and 7 are also deleted, which means wherever 5 and 7 are referenced, that value is not also present. Then this 5 and 7 is not present. So these 3 tuples had to be deleted. So the correct answer will be 5, 2, 7, 2 and 9, 5. So this is a homework question. In our previous lecture, we have covered the basic ER model. In this lecture, we will learn about the extended ER model. But before that, let's revise from these slides first. What we discussed, try to remember. We first started with the data model. So what is a data model? Blueprint the structure, how data is stored and accessed. It provides conceptual tools for 4 things I told you to remember: describing data, relationship, semantic and constraint. Data, relationship, semantic and constraints. And ER model is a high level data model. What does high level mean? That even a non-technical person can understand. Based on real world entities, the objects and relationship among them. What were entities? The core building blocks. The real world object that can be identified. They have primary key. We have also discussed about the weak and strong entity type. Entity sets, grouping similar entity instances or the set of all entity instances. They have shared property, type consistency, organizational structure. Attributes, what were the attributes? The properties of the entities. They have, each entity has a set of attributes. Each attribute has a domain of permitted values, which is known as the value set, and they have a description. Attribute describe the entity properties. We know different type of attributes: simple and composite, single and multi-valued, derived and stored. What a relationship? Establishing an association between different entity instances. But you know that there is no symbol for entity instances in ER model. That's why we describe the relationship as association between entity types. So it describes the association, entity partition, relationship strength. You can all read this theory. We have also learned about the degree of relationship, unary, binary, and ternary, and then relationship constraints, cardinality ratios based on maximal cardinality, which is 1 to 1, 1 to many, many to 1, many to many, and minimum cardinality, which was total participation and partial participation. So till now we have learned about the entity, type, instances, and set. Then we move to attributes and then relationship, which is connection between the entities. Okay. Now let's start with our extended ER model. In this lecture, we will learn about generalization and specialization. Generalization differentiates the entity type into subgroup. Okay, so let's say I have an entity person, and if I differentiate it into employees and customers, then this is the super type and these are the subtype. This is just the entity type. We are segregating the bigger entity into two smaller ones. Person is divided into employees and customers. Person is the general or super type, where employees and customers are the sub or specialized type. And what is the symbol for this? Generalization or specialization? This triangle. So person have attribute PID, PName, and age, and it is subdivided into employee and customers, where employee have salary and customers have attribute name, product bought. Now, one important thing is all the attributes of the general or super type entity will be automatically inherited by this subtype entities, which means employee also have PID, PName, and age. Customers also have PID, PName, and age. We have segregated the person based on the differentiating attribute, which is salary and product bought. Specialization and generalization are the basically same things. They differentiate on the perspective. Specialization is a top-down approach and generalization on the other hand is a bottom-up approach. In specialization, we start with a bigger entity and break it down into more specific sub-entities. So when we talk about employee, when we talk about customers, they are more specific. For example, we may begin with a person entity and then classify it into employees and customer based on their roles. Whereas for generalization, we start with multiple specific entries and then we look for the common attributes to form a higher level general entity. For instance, we have employee and customers as separate entities, and we notice that they share many attributes common. So we can create a person entity that generalizes the both. So specialization and generalization are basically the same thing. It depends on the perspective. If you are looking at the top-down approach, then it is specialization. Or if the database designer find out that between these two entity types, various attributes are common, so you start with the bottom-up approach. You start with the specific entities first, and then you generalize into a bigger general entity. Then it becomes the generalization. This is what specialization, generalization, they have a common symbol, that is a triangle. Symbol representation same, it is just the matter of perspective. Attribute inheritance, that I've already talked, that all the person attributes, age, ID, name, will be automatically inherited to the employee and customer entity type. Okay, so specialization is top-down approach, generalization is bottom-up. In specialization, we find differences between the instance of the same entity type. Where in generalization, we start with the different entities, find common element, find common attributes, and then build up the bigger general entity or bigger super type. We will find similarities. In generalization, we find similarities between instances of different entity type. So in specialization, we start with the bigger entity, we will break it down, while in generalization, we start with a smaller specific types and then build a general type. Generalization or specialization is a specific type of relationship. Why I say specific type? Because in normal relationship, like we had, for example, a student owns a book, so student may have books. But here, the subtype do not have instances of their own. I will repeat this line, that subtype do not have instances of their own. Out of the instances of the general entity, we segregate these instances into two different types. Let's say they become the employee and they become the customer. So out of the instances of the general or the bigger entity, we basically segregate them into two different specific entities like employee and customers. Okay, participation inheritance. If a parent entity participate in a relationship, then its child entity set will participate in a relationship automatically. Okay, so we have learned about two different things: attribute inheritance and participation inheritance. What was attribute inheritance? Means that all these attributes will be automatically inherited by the children. And what was participation? That if this person entity is indulged in a specific relationship, then they will be automatically considered to be in that relationship. This was participation inheritance. Okay, see this example. A person have attribute name, phone number, and address, and it is segregated into two: employee and customer. Customer have email, customer ID, credit, while employee have employee ID and salary. But these attributes, phone, name, and address, they will be inherited by both specific types. Can a supertype be enrolled in more than one is a relationship? Think about it. Is it possible? Yes. An employee can be divided into full-time and part-time, and it is also divided into two: manager and secretary. Supertype with more than one is a relationship. We also call it as multiple specialization. And see, by looking at this, you cannot tell in which manner we have moved. Either it was top down or bottom up. So what we do to symbolize specialization, we use symbols like this, that we are moving top down. And to symbolize generalization, we specify like this, that we are going bottom up. So the question was, can a supertype be enrolled in more than one is a relationship? True. Can a subtype be enrolled in a relationship with more than one supertype? It's basically asking, can an entity have more than one parent? Yes, it's possible. We call it as multiple inheritance. A subtype in multiple relationship with supertype. For example, a owner can be either person, a bank, or a company. That's why we have used union here. So what will be the key for this owner? Will it be the combination of person, bank, and company like this? The answer is no, because if I do like this, and you know that key cannot be null, so BID, PID, and CID all will be present. And if all are present, then our meaning was destroyed. What was the meaning? That either a person or a bank or a company can be employed, can be the owner, but not all. This was symbolizing that owner will be bank, person, company at the same time. So what will we do? We will use here the concept of surrogate key. That is, we will do like this, make an attribute OID, owner ID, and we call it as surrogate key, which can be either bank or a person or a company, not all. Owner will not have its own instances. The instance of person, bank, and company will be union. So this was the answer of question number 2. Can a subtype be enrolled in a relationship with more than one supertype? Yes, the concept of multiple inheritance and by using the surrogate key. Here the car booking, car owner can be person, a bank holds a position on a car, or a company. Category subclass owner. Here owner is a subset of union of these three superclasses: company, bank, and person. A category member must exist in at least one of these superclasses. Okay, so the owner should be in person, bank, or company. Must exist in at least one of the superclasses. At least one of the superclasses. Okay. Question number 3. Can an entity type act as both supertype and subtype at the same time? Yes, but not within the same hierarchy, but in different. See this. What example should I give? Like a vehicle can be car or bike, and car can be further divided into petrol car or a diesel car or electric car. So here this car is acting like a supertype for this petrol and diesel, but it is acting like a subtype for this vehicle. So can an entity type act as both supertype and subtype at the same time? Yes. Now we'll learn about the constraints on generalization and specialization. The first one is membership constraint. Attribute defined and user defined. Let's see this example. For example, an employee can be either full-time or part-time. If I decide where this instance will go, as you know that the full-time and part-time do not have instances of their own, they will inherit the instance from the employee, that from various different employees, some will become the part-time and some will become the full-time. If I choose a criteria, if I choose some attribute on which I decide that this employee will become part-time and this will become the full-time employee. This is what attribute defined membership constraint is. Based on attribute, to which subtype a particular instance will go. And if I do this randomly, I will say this is user defined. So membership constraint based on, if it is based on attribute, that instance of the super type will go to which subtype, then it is attribute defined, otherwise user defined. Disjointness constraint. Then I will say that if I apply this disjoint constraint, which means that the employee can be either full-time or part-time, but not both. An entity can belong to only one subtype. It will be either part-time or it will be full-time. Overlapping, an entity can belong to multiple subtypes. For example, some of the full-time employees are working part-time in different department under same company. It may be possible. Then I will say it is overlapping, otherwise disjoint. You know the meaning of disjoint, right? Disjoint means either this or that, but no overlapping thing. Here, overlapping is present that some of the full-time employees are also working as a part-time in different department. Employee can be full-time and part-time both at the same time. But here, employee will be either full-time or part-time, can't be both. This was the disjoint and overlapping constraint. Then completeness constraint. Total generalization and specialization, which means that every instance of the supertype must exist in at least one of the subtype. And for partial, some of the instances of the supertype may not belong to any subtype. Okay, so let's revise now. First one was the membership constraint, that if you set up some criteria, based on that criteria or that attribute, the instances of the supertype are going to a specific subtype, then I'll say it is attribute defined. Otherwise, user defined. The second one was disjoint constraint. Disjointness constraint, disjoint, which means either this or that, but not both. Overlapping, an entity can belong to multiple subtype. Total constraint, then each and every employee will belong to at least one subtype, will be either part-time or it will be full-time or maybe both, but at least one membership is important. It should belong to at least one of the subtype. This is the total constraint. And for partial constraint is, some of the employees may not be, let's say, they are not working either full-time or part-time, but have you heard of the concept of outsourced employees that works on the payroll of a different third party? Outsourced employee, neither full-time or part-time. Here I've written the definition. Outsourcing employee or employee outsourcing is a business practice where a company hires external talent or agency to perform a specific task or function rather than employing them directly. So they are neither full-time nor part-time, but yes, they work in the company or they are employee of the company, but they are not full-time or part-time. In that case, I'll say the partial constraint. But here, an employee will be either full-time or part-time, no concept of outsourcing, then I'll say it is total completeness constraint. You got the idea? Okay. Now see this. Here is the example. For example, let's say 100 employees were present. What does this represent? That each and every employee will belong to either full-time or part-time or maybe both, but they will belong to a particular subtype. What does this represent? That it will be either full-time or part-time, but not both. So what does it mean? That employee equals to full-time employee plus part-time employees. 100, 40, 60. So you have to understand this and combine their constraint and find a common constraint, which is each and every employee will be either full-time or part-time, and employee cannot be both at the same time. Okay, so this is clear now. Second one, overlapping is possible. So each and every employee will belong to either full-time or part-time or maybe both, but they will belong to a particular subtype. This is what it says. Overlapping says it can be either full-time or part-time or both. So let's say we have, out of 100 employees, 40 were working in full-time and 60 were in part-time. And out of these full-time employees, 30 are also acting as a part-time employees in different departments. So I'll say employees are less than equal to part-time plus full-time. So 100, here the 90 is the part-time and full-time is 40. So is less than. Okay. In total participation, every employee will be either full-time or part-time. See here. Now it's partial participation. That some employee may be present which are which do not belong to any of the subtype. Okay, so let's say 100 employees are there, 30 are working as full-time, 40 are working as part-time. Then what does this disjoint say? Then that they are either full-time or part-time, but not both. So these 30 and 40 are disjoint. So 100 will be greater than 30 plus 40. And the employees, they have no, and the partial and full-time set has nothing in common, no employees common. Then this overlapping is also possible, and they are in partial participation. So out of 100 employees, let's say the first case is 40 employees are working full-time and 40 employees are working in part-time. Out of these 40 full-time employees, 30 are also working as part-time in different department. So 70 employees plus 40 employees. So I will say 70 plus 40 is greater than 100. This is one case. Another case is, let's say 100 employees are there. Out of the 40 employees, only 10 employees have gone to act as part-time in different department. So now it will 40 plus 50, 100 is greater. The relation keeps on changing, so no relation is present here. But here you can see equal to, less than, greater than, no. Suppose a manager want to manage a combination of employee, job profile and branch. A manager want to manage employee, job profile and branch. So should I do like this? Employee, branch and job profile. Is it a good thing? No. This will create a redundancy because manager do not want to manage employee and branch and job profile. Manager want to manage a combination of an employee who is working in a specific branch, have a certain job profile. Are you getting the difference? By doing like this, I am imposing redundancy. Why? Because manager do not want to manage employees. Manager do not want to manage branch or job profile. Manager want to manage a combination of all these things. An employee working in a certain branch under a certain job profile. Okay. So if I do something like this, I am not exactly doing the same thing. Actually doing the same thing. I want to manage the combination, but here manager is managing the employee, branch and job profile separately. I want something like this. So what I'll do? Aggregation is basically creating a high level entity. So what we will do? We will just make this as a black box entity. Manager do not know what's inside it, but what manager is doing? Manager is managing this entity as a whole. So this will be a better choice instead of doing like this. So we make this as a separate entity. Name works on. So we have to give an entity a name. So what name we will give? Based on the relationship name. Okay. So we need to show relationship among relationship. So what is abstraction? Abstraction. What is aggregation? Aggregation is abstraction through which relationship is treated as high level entity type. Okay, so abstraction is applied to treat relationship as higher level entity. We call it as abstract entity. So this will become an abstract entity named works on, and will manage this works on abstract entity, high level entity. And aggregation obviously help in reducing redundancy by aggregating relationship as entity itself. Okay, so this was our first approach, which was bringing redundancy, that manager ID, employee ID, branch ID and job profile. But what we have done, we have created a higher level entity that is works on employee ID, branch ID and job profile ID, and manager now interacts with, or manager manages this entity works on. So what manager will have? Manager ID and works on ID. So this is a better approach. You got the idea? Let's see another example. I want that subject of a student should depends upon the semester he or she is enrolled in. So student attends the semester, and this whole entity has subject now, because subject depends on semester wise. In each semester you have different subject. So I want that subject should depend upon the semester in which the student is present, or the student attending that semester. You got the idea? Aggregation is abstraction through which relationship is treated as high level entity type. See this? An employee works on a certain project, and I want to know that which software employee is using. So this software doesn't separately depend on employee or the project. It depends upon the combination of both, that is employee and the project. On whichever project employee is working, based on that I will find out the software. So I will make this as an abstract high-level entity name works on. Instances of this relation are only those employees who are working on some project. Have you listened what line I have said? Instances of a relationship. Now we have learned a new thing, that even relationship have instances. Do not worry if you are getting confused. We will see this in detail when we will learn relational model. Okay, let me repeat. In aggregation, what we do? We create this as an abstract high-level entity, name it as works on, and this works on entity will only have the combination of the employee and the project. So in this entity, only those instances will be present, only those employees who are working on some project, like here. Combination of employee working in some branch and job profile. Combination of student who is attending a specific semester, based on that subject will be decided. Similarly, the combination of employee and project, based on that software will be used. Okay, so in the next lecture, we'll first revise whatever we have learned, and then we will learn how to formulate and think the ER diagram. In this lecture, we'll learn how to think and formulate ER diagram. We will see the ER diagram of banking system and Facebook, or I should say social media platform. So these are the 4 steps that you have to follow. Identify the entity sets. Identify the real world objects that will be there. And then identify the properties of those objects. Identify their attributes. Also think about their types. And then think of the type of relationship you would establish. And when you have established the relationship, think of the cardinality and participation constraint. If you have followed these 4 steps, you will have your ER diagram. Now let's see for our example 1, the banking system. I should say this as the step 0, that we will first gather the requirements. How are we going to do that? By interviewing the clients and the stakeholders. So let's say these are our requirements for the banking system. Branches will be present and each identified by a name. Customer will have account in the bank. Customer can apply for loans. Customer will be associated with bankers or managers. The bank will have employees, which include manager and bankers. Account will be of 2 types, savings account and current account. Loan will be issued by a specific bank. A single loan can be associated with multiple customers, joint loans. Each loan will have a payment schedule. So what will be the first step will be the find entity sets. Branch, customer, employee, loan, savings account, current account, and payment. And I think you have guessed by now that we are going to merge this into a general entity, which is account. Okay. Now we have identified the entity types. Now search for the attributes. What all attributes will be there to describe a particular entity set? For branch, name, city, asset, and liabilities. As branch name are all different, that's why I should say the name will act as a primary key. For customer, customer ID, name, address, contact number, date of birth, age. And as you are defining the attributes, you should at the same time think of the type of that attribute. For example, the address could be composite, contact number can be multi-valued, age can be derived. For employee ID, name, contact number, dependent, years of service, start date. So this can be derived, this will be stored. Contact number can be composite. No, contact number can't be composite, it's wrongly written. It should be multi-valued. Okay, and savings account, current account, or yes, contact number, like you're doing like this, for example, line 1, and then you're writing the number. Well, this can be the way, but in general, we do not take contact number as composite. Savings account, current account. For savings account, we will see account number, balance, interest rate, daily withdrawal limit, and for current account, we'll see account number, balance, per transaction charges, and overdraft amount. But what we are noticing here is that account number and balance are the common properties. So we have started with specific subtypes, and we are identifying the common properties, and then we are trying to create a general bigger super type. What is this? Bottom up approach, which is generalization. And from here then we will delete these properties and we will add to the account. So account will have account number and balance and two super types, savings account and current account, which will only have these properties or these attributes. Okay, then loan will have loan number and loan amount. Payment will have payment number, date, and amount. And payment will be weak entity type. If you remember that payment will only be there if loan is present. Now you have to identify the relationship at constraint. Customer borrow loan. Can loan exist without any customer taking the loan? No. That's why total participation is present. One customer can take multiple loan, and multiple loan can be paid by, or single loan can be paid by multiple customers. This is the meaning of many-to-many relationship. You have to think from both sides. One customer can borrow multiple loans, and a single loan can be paid by or borrowed by multiple customers. For example, joint loan, when the couples take the house loan, it is the responsibility of both husband and wife to pay the loan. So this kind of situation. Loan originated by a bank. So multiple loans can be originated by a single branch. So one branch can originate multiple loans. But can a loan be present without having its relationship with branch? No. That's why total participation is there. For here also, for loan to exist, it must be borrowed by some customers, at least one. For loan to exist, it must be originated by some branch, at least one. And you know that between loan and payment, weak relationship will be there. Identifying relationship will be there. Payment will be the weak entity. And you know, from the weak entity side, we will always have a total participation, and the cardinality will be one to many. Customer deposit in amount in account. In a single account, multiple customer can deposit, or a single customer can deposit in multiple accounts. So whenever many-to-many relationship is there, you have to think from both sides that one customer can deposit in many accounts, and in a single account, many customer can deposits. For example, a joint account. Customer, banker, employee. One employee will act as a manager for multiple customers. Okay. Employee managed by employee. Multiple employee will be managed by a single employee. By reading this, you must have guessed unary relationship. Okay. So till now, have you feel any difficulty in thinking all those things? No, because we have just followed these conditions. We first started with identifying the entity sets, then various attributes possible, and then we thought of identifying relationship like customer borrow loan. So here it is written that a single loan can be associated with multiple customers. So all those things, all those relationship we have defined based on the requirement. So you have to just understand the requirement, and based on that, you identify the relationship, cardinality, and constraint. Okay, and more you practice, the better you get at it. So these are the relationship we will have. And one more thing, that ER diagrams are not unique. For banking system, there can be multiple ER diagrams based on the requirement. Okay, so this could also be ER diagram for a banking system. But for our case, this will be our ER diagram. Okay, so we first started with customers. Customer have multi-valued contact number. They can be multiple contact number. Customer ID as the primary key. Name, date of birth, age as derived attribute, and address as composite, where address could be divided into street and pin code, where street can be further divided into street number and street name. And then we had relationship like customer borrow loan, and from loan side we will have total participation, many to many. Wherever you find many to many, you have to think from both sides. A single customer can borrow multiple loan. A single loan can be paid by or can be associated to multiple customer. Okay. And from loan, this was the identifying relationship I was talking about. A payment will totally depend on the existence of loan. So from payment side, we will have the total participation. Payment have the attribute like payment number, payment date, and payment amount. The loan will be originated by a branch, and a loan must be associated with at least one branch. That's why total participation here. And we define the attributes of branch. We have city, assets, name, and liabilities. And customer, first relationship of customer was with loan. The second relationship will be with the account. So customer can deposit in an account, where account have account number, balance. And here is the generalization I was talking about. Account can be current account or a savings account. And this account number and balance will be automatically inherited to both of them. These two attributes will be automatically inherited by current account and savings account. Okay. And then customer is also associated with this manager employee. So many customer have a single banker. So employee will have attributes like start date, employee ID, name, contact number, years of service as derived attributes, because we have start date with us. So with system date minus start date, I can easily get years of service. And unary relationship in this, a single employee will manage the multiple employees. So this was the ER diagram. And you know why we say ER diagram is high level design? Because by understanding this, or by looking at this, even a non-technical person can understand what this diagram is conveying. Okay. Now, example 2, we will create an ER diagram for social media platforms. The first step was identifying the entities. But before that, you remember step 0, calculating the requirement gathering. We'll understand the features and use cases by talking to the clients and stakeholders. So they want user profile to be friends among each other. So a user profile is an entity which is friend with some other user profile. So this is a kind of unary relationship where user can post, like, and comment that post, and post can have text, images, videos. Now identify the entities. We will have user profile, user post, post comment, and post like. Now if you have paused and tried earlier, then you may have did this mistake, like making this user post as an entity and this like and comment as the attribute. Well, this is not good, because here you have to associate a relationship between like and users. So different user will comment and different users will like. So it will be a kind of relationship between a user, which is entity and attribute. Relationship does not exist between entity and attribute. It exists between entity and entity. That's why we have to segregate this into a different entity itself. So this comment and post will become separate entities. So we have made different entities, post like and post comment. So this is the concept that you have to remember. Now we have identified the entity types. It's time to identify the attributes and their types. For user profile, I can have name, which can be composite, first name, middle name, last name, username for unique identification, email, password, contact number can be multi-valued, date of birth, age, which can be derived. For user post, I can have post ID, text, image, video. As you can see that there can be multiple images in a single post. For example, in Instagram, or even videos can be multiple, but here I have only taken images as multi-valued. Created timestamp, modified timestamp. So these can be the attributes for user post. For post comment, I can have post comment ID, text content, whatever you are commenting, and the timestamp, the time at which the comment was posted. Post like ID and timestamp. Now we have defined the attributes and their types also. It's time to establish the relationship, their cardinality and constraints. So a single user can be friend of different multiple users, and similar thing can be said from this side also. That's why many to many relationship. A user profile, post, user post. A single person can post multiple user posts. Okay, and a user post must be posted by some user profile. That's why total participation. It cannot be the case where there exists some user post which is not posted by any user profile. Okay, a user profile can like multiple posts, and similar thing can be said that there cannot be any like which has not been done by any user profile. That's why total participation. A user profile comments on post comment. So one user profile can perform multiple comments. That's why, and there cannot be any post comment which has not been commented by any user profile. That's why total participation. Similar thing for user post that has post comment and post like. Now it's time to create the ER diagram. We'll first start with the user profile. I have user profile which can be friend with some other user profile and many-to-many relationship. I have username for unique identification, date of birth, contact number, name, composite, email, password, age can be derived. And user profile can comment, post comment, which has post comment ID, text content, and timestamp. And one user profile can perform multiple post comments. Okay, and a user post can have multiple comments. And a comment to exist, there must be some user post. Similar thing can be said for post like. For a like to exist, there must be some post on that like was done. Okay, a user profile can have multiple posts like. Okay, so this is the ER diagram of a social media application based on our requirements. Okay, you can have a look properly. So I will say again, the more you practice, the better you get at it. That's why I have this. These are the 6 topics where if you have practiced the ER diagram on these 6 topics, then you will have a better understanding of ER diagram. And for some 7th new topic, your mind will be trained enough to create the ER diagram from scratch. In our last lecture, we have studied about ER model. We saw that ER model was not the complete model because it doesn't tell us anything about the storage format like relational model does. It says data will be stored in tables. ER model doesn't say anything like that. It tells us about the manipulation language that will be SQL. The whole relational algebra is defined. There, nothing of such sort. Then why we studied ER model? Because ER model act as a bridge. In thinking process, we think of ER model first. We create a high level design first. And then we start creating the tables. We first create the high level design, which is ER model. So we'll start with what is a relational model. And then we will learn how to convert ER model into tables. So the relational model developed by E.F. Code, the IBM scientist in 1970. System R was the first DBMS to use the relational model. RDBMS are the DBMS designed for databases that follow the relational model. Relational model says data will be stored in tabular format, where rows will tell us about the instances or records or tuples, while column will tell us about the attributes. Example of RDBMS: Oracle, MySQL, MariaDB, MS Access, Microsoft SQL Server, SQLite. In an RDBMS, we can design database efficiently. Another question: why is the relational model so popular? There are 3 main reasons. There are different RDBMS available in the market. You don't like the format of Oracle, you can use MySQL. If you don't like MySQL, you can use Microsoft SQL Server. The second one is simplicity, easy to use and understand. The third one is it is based on a strong mathematical foundation. We are studying relational model, so let's start by understanding what is relation first. See these 2 sets, A and B. Have you heard about the term Cartesian product? Cartesian product says that one will be related to A, C, M and N. 2 will be related to A, C, M and N. So all possible different kind of relations are included in the Cartesian product. So I can say relation belongs to Cartesian product, or the relation is the subset of Cartesian product A cross B. And then when we design tables, which relation we include? Which is in our area of interest. That relation we insert into tables. Okay, and also the concept of ordered pairs. That if I write 1 and C, then it is not similar to C and 1. 1 comma C is not equals to C and 1, but you can swap orders here. 1 comma C, 2 comma N, these orders can be swapped, but inside the brackets, it will not. What does 1 comma C represent? It represents the relation between 1 and C, that some sort of relation exists between 1 and C. 2 comma N says some sort of relation exists between 2 and N. Similarly, 7 and N, and 5 and A. If I ask you the maximum possible number of relations, then what will you say? Think about. Suppose there are m entries in set A and n in set B. The number of ordered pair will be m cross n. And each ordered pair will have a choice either to be present in the set or not. 1 comma C is also a relation. 1 comma C, 2 comma n is also a relation. 1 comma C, 2 comma n, 7 comma n is also a relation. 2 comma n, 7 comma n, 5 comma a is also a relation. So each ordered pair have a choice either to come, either to be present or to be absent. So I can say if there are mn ordered pairs and each ordered pair have two choices, then there will be total 2 raised to power mn relations. This is what I've written, where each and every relation will belong to the set of Cartesian product, and maximum number of relation possible will be 2 raised to power mn, because each pair will have a choice to be either present or absent. Suppose like A, B, 1, 2. So A, 1, A, 2, B, 1, B, 2. So these are the total possible ordered pairs, where each ordered pair have a choice either to be present or absent, present or absent. So 2 choices here, 2 choices here, 2 choices here, 2 here. 2 raised to power 4, that is 16. So the entries which we want to store will be stored in tables, which is our area of interest. And what is a relation then? Relation is the physical structure in which theoretically all valid tuples can exist based on the schema. Because relation could be equal to the Cartesian product. Relation could be just one single ordered pair also, or relation can be phi also. So in relation, it is a physical structure in which theoretically all the valid possible tuples can exist. But in table, what we store? The ordered pair which inclines according to our area of interest. So the practical form of relation is what table is. So here is the bookish definition. A relation is a mathematical set that is a subset of Cartesian product, meaning it does not store all the possible combination, but only those tuples that satisfy a given condition. A table is a practical form of that relation used in DBMS, where we store only the area of interest data as per our requirements. So relation can be either phi also, or it can be Cartesian product also. And what we will store in the table according to the condition which incline with our area of interest. Okay. So what is a table? Practical form of the relation. What is a relation? A sort of association based on some condition, in which all possible ordered pair can also exist, or no ordered pair can also exist. Okay. Cartesian product, all possible combo of relation. When we apply some condition which is according to our area of interest, we will get a particular relation, and the physical implementation of that particular relation will be our table. So I hope the idea is clear. You have understood the difference between Cartesian product, a relation, and a table. There is a minute difference between the structure properties of relation and table. In table, the null and duplicate values are allowed, but in relation, they are not allowed. So no null and duplicate values are allowed. In relation, order between the pairs is not important. Like 1, 2, 2, 3, 4, 5, they can come like here also. This is the same thing. Order is not important, but order within the pair is important. Like you cannot write 1, 2 or 2, 1 as equal. They are different. Okay. So ordered important in ordered pair. 1, 2 is not equal to 2, 1, but they are equal in tables. They are equal in tables. So this is the difference between relation and table. Their basic definitional properties. So every table is a relation, but vice versa is not true. Think about it. Okay. Now we will move to some basic terms. The degree of relation. It is also known as arity, which is the total number of columns in that particular table, or the total number of attributes, because in each column we store a attribute. Cardinality of that relation. Total number of rows or total number of records, tuples, instances. Tuple means record, which means a one horizontal entry. Attribute, property, okay, schema, the blueprint, domain, allowed values for attributes. I hope these points are already clear to you. Let's see this example. This is our entity set. These are the attributes or the column names. Key field, the attribute based on which unique identification will be done. These are the fields or columns. This is our table. One horizontal entry is what record is. This is the column value. These are the values of the attributes. This is what schema is. Okay, so I hope these basic points are clear to you. 6 basic properties of relation in RDBMS. I'm going to read this and you will understand. Each cell of a table must contain atomic values. You cannot write like this using commas. 52, 53. You cannot write like this because we are talking about ordered pair here. See this. When you do like this, it will not remain a pair now. 3 values are included. This is not possible writing with comma, because even if you write like that, it will be considered an atomic value, a whole. Each column must have unique name. Value of attribute must come from their respective domain. This was the domain constraint. The order of rows is immaterial. See this. You can swap these rows, nothing will change. You can swap these columns, nothing will change. The order of rows and the order of columns are not significant. Okay. Each row in the table must be distinct. Yes, each instance must be different from the other instance. They cannot be totally same. The order of the columns is immaterial. This I have discussed. Now, why relational model is the complete model? When we say a model is complete, when it answers 3 questions. The first one, storage format. The answer is through tables. How are you going to store data? Through tables. The second one is manipulation language. The answer is SQL. Third one is integrity constraint. So these are the different integrity constraints. Key constraint, primary key unique. Entity integrity constraint, primary key should not be null. Referential integrity constraint, foreign key values should be subset of the primary key, or child table values should be subset of parent table values. Null constraint, nullable or not null. When we apply null constraint, for example, this value cannot be null, so you cannot leave that value empty. Default value constraint, if left empty, then fill the default value. Uniqueness constraint, if applied with an attribute, then the attribute value cannot be same. Okay, it has to be different. It has to be unique. Domain constraint, value must come from domain. Okay, so if I set some value, if I set some attribute nullable, then null is always included in the domain. If the value is nullable, then null will also be the part of that domain. So here exception will be the null values. Okay. Domain constraint, value must come from the domain. For example, we have set the value of age from 18 to 130. So if I try to write 500, then error will be thrown. 12, error will be thrown. If the age is nullable, then here is the exception. We can leave the age empty. So here null will be indirectly considered to be the part of that domain. Okay, so you can think like that. Otherwise, we will say for domain constraint, null values are the exception. Now here, whenever we design database, it is done in 2 phases. The first one is we design the ER model. We have learned this part. The second one is now we convert ER model into relational model. Okay, let's learn this now. Entity types, each and every entity type, either strong or weak, is directly converted into a single table along with its simple attributes. Okay, so there will be few exceptions we will see later. Each and every entity type will have its own table. Remember this thing. What are we doing now? We have designed the ER model and then we are converting ER model into tables. So What you see in AR models, you see entities. So how are you going to convert that AR model into tables? So for each and every entity, one table will be required. So each and every entity type, whether it's strong or weak, is directly converted into table along with its simple attribute. Now what about composite and multivalued attributes? For multivalued attributes, you will require a different table. You will require a different table. I'll explain you how. Another question. Will I require different table for each and every multivalued attributes? The answer is yes, you do, but it is not compulsory. See this. For multivalued, how are you going to break this? For example, like manufacturing, the ID, and the locations are Atlanta, New York, Denver. So what are you going to do? You are going to segregate this table into two different tables. The first table will have primary key plus rest attributes. Except the multivalued attributes, the remaining attributes will come with the primary key in this table, and then the another table will be primary key and multivalued attributes. So what we have done, if you have found a multivalued attribute in your ER diagram, then what you will do, primary key plus multivalued, one table, primary key plus rest attributes, another table. Name of new table will be based on multivalued attributes. Okay, so what will be the name of this table? Location. And what will be the primary key of the new table? The combination, primary key of original table and the multivalued attribute. Okay, so primary key of original table and multivalued attribute, this combo will act as a key for this table. Okay, for multivalued attributes, you will always require a new table. For composite attributes, you have to adjust in that original table itself. For example, this salary has three different sub attributes like basic, dearness allowance, and house rent allowance. So what will you do? Ignore this and add this basic, DA, and HRA here. This salary will not be added as a different attribute or a different column. So what are you doing? Just erase this, add the sub attributes directly. This is how you tackle the multivalued and composite attributes. What we have learned till now, we have learned that we first design the ER model. How we design that, how to think and formulate, we have already learned. Now we are converting that ER model into relational model. How are we doing that? First thing is, whichever entity you see, you create a separate table for that entity. And if you see multivalued attributes, another table will be required. If you see composite attributes, you have to adjust those attributes into that table itself. So no new table required for composite attributes. Well, you can create for some normalization or reducing the redundancy, but it is not compulsory to create the new table. But for multivalued attributes, it is compulsory. For each entity, it is compulsory to create a new table. Okay, now if you encounter multiple multi-valued attributes, then should you make separate table for each? Then it depends. If the question it is asked minimum number of tables, then no need to put all multi-values into different table. You can put all that multi-valued in a single table with one primary key. You can do that, but this will include high redundancy. So it depends on the question. If they are strictly asking the minimum number of tables required when you convert this ER diagram into relational model, then what you do, put all the multi-valued attributes of that entity at one place in one table along with the primary key, and the rest attributes along with primary key will be formed in different table. But if they are asking about the efficient design, then what you do, you create separate tables. Okay, so why I'm saying so that separate tables will be good, because see this, employee has attribute EID, name, skills, and phone number. Suppose they have three skills. The employee have three skills and they have two phone numbers. So for each employee, you have to create 6 entries for, let's say, one employee. So like employee ID 1, skill, let's say they know HTML, and the phone number, one phone number. Then again HTML, another phone number. Suppose then the CSS, phone number 1, phone number 2 will come again. Then JavaScript, phone number 1, phone number 2 will come again. And all these for what? Just employee ID 1. High redundancy will be there. So it is good to create separate table, but if they are asking about strictly asking about the minimum number of tables, then No need to create different table for all multivalued attributes. You can create one separate table only. Now, a little discussion on surrogate keys. Suppose I have this table for school A, this table for school B, and I have to merge this into a single table. Then what I will do? I will create a artificial key. I cannot take a registration number as a key again, because 101 here also, 101 here also. See, I have written like AB101, but it could be there that registration number 101, registration number 101. It could be same. So then how are we going to differentiate each tuple? We create a different ID, that is the surrogate ID, which will act as a unique identifier. It doesn't have any real world meaning, but it will help us to identify each tuple differently. So 1, 2, 3, 4, 5. I hope you got the idea. What are we doing here? Registration number 101 can be same in the school table of school B, registration number 101. So registration number, the natural key, now can no more act as a primary key. So we have to create an artificial key, which is the surrogate key, which will act as a unique identifier, which doesn't have any real world meaning, but it serves the purpose of unique identification, just like the primary key. Okay. In our last lecture, we have learned how to convert the ER model into relational model. We saw that for each entity, you have to create a separate table. For each multivalued attribute, you should create a separate table. Or if you have different multivalued attributes, then you can put all those into a single table and the rest attributes into the original table. You can also do that. Then we have learned that for composite attributes, you have to adjust all the sub attributes into the same table itself. In ER model, we have entities, and the entity with all of its attribute will go to a separate table. Now, with entity attributes, we also have relationship in the ER model. What about those relationship? How are we going to show those relationship into tables? We will see that in this lecture. We will start with one-to-many relationship plus the partial participation from both sides. We will see this case that we have student which has SID and SName, the student ID and student name, where SID will act as the primary key. Student issues book ID and title as their attributes. Now, to link the two entities or two tables, what we have learned, how are we going to link the two tables? See, two things can be done. Firstly, we can create a separate table for relationship itself. But we don't want to increase the number of tables. Then what we can do? We can use the concept of referencing, the primary key and the foreign key concept, that the child table will refer to the parent table. In that manner, we can establish association. So we'll try doing the same thing, that SID, SName, BID and the title. How are we going to establish the association? We can do that by making a primary key of one table as the foreign key into another table. Now the question arises, whose primary key will become foreign key in which table? We will transfer, or we will use this primary key as foreign key here, or we will use this primary key as foreign key here. So remember our golden rule. Whenever partial participation is involved and one-to-many relationship is there, then primary key of one side will become foreign key at the many side. Primary key of one side will become foreign key at the many side. Remember this combo. Primary key of one side will become foreign key at the many side for partial participation. But what will happen if I make the primary key of many side foreign key at the one side? What will happen then? We will see why it is not a good idea. I'll prove it to you, that making this primary key foreign key here in the student table. The first thing is the relationship is one to many, which means that one student can have more than one book. So let's say student ID 101 can have book 101 and 102. It is possible. See this relationship, one to many. And one more thing, to represent one to many, there are several patterns. The first one can be like, you can also write one to many in this manner, or you can use this arrow. For arrow thing, I want to tell you another important part, that the position of arrow, whether you write arrow here or here, doesn't matter. The entity to which arrow is pointing, that matters. So if I write arrow here, then also it will mean the same thing, then that one student can be associated to many books. Okay, so the position of arrow doesn't matter. Whichever entity arrow is pointing, that will become one, and another entity will become many. Got the thing? Now we have seen that the relationship is one to many, which means that one student can have more than one book. Let's say A01, 101 can have 101 and 102. Now there are two rules that you have to follow, that the values should be atomic, and the second rule is primary key cannot be duplicate. But if you are doing this, that you are making the primary key of many side foreign key at the one side, then you have to break one of those rules. See this. If you want to store, see, S101 can have B101 and B102. So you can represent like this, but this is not allowed because atomic values are allowed only. Otherwise, what you have to do, you have to create a separate instance like this, 101 A B101, 101 A B102. But now we have seen that SID was the primary key, and primary key cannot be duplicated. Another rule. So you can think that it is not necessary so that SID should remain the primary key. It is not necessary. We can make the combination of SID and BID as the primary key. Like this. We can make the combination of SID and BID as primary key. In that case, the combination is not same. Like S101, 101, 101, 102. The combination is not same. Can it act as a primary key? Let's see. Here, there is no total participation, which means a student can exist which has not issued any book. Which means that there can be some student like S102 which have not issued any book, 103 which has not issued any book. But we have taken the combination of SID and BID as primary key, which means the BID is going null here. So it is not possible that BID becomes the part of primary key, because if we are imposing that BID should also become the primary key, which means that BID should not be null in any case. Which means we are imposing the total participation at book side. That there cannot exist any book which has not related to some student. Which means we are imposing the total participation as book side, which was not in the question. So whenever you got confused or you forget a rule that the primary key of one side should become the foreign key at many side, if you even forget this rule, you can always check like this. Okay. Now our method or correct method, that I have to make the primary key of one side the foreign key at the many side. This will work. Yes, it will work. Make primary key of one side, foreign key at the many side. This won't create any problem. One book can be associated to at most one student. Well, this is true. See here. One to many. Which means like one student can be associated to many books, can issue many books. But one book will be always given to a single student only. This is one to many, means that one book will be always attached to one student. Okay. So this was one book can be associated to at most one student. Let's say the book number B101, title Song of God. SID S101, this will act as the foreign key. And B102, Gift of Magi. S101, now this can repeat because it is a foreign key. Suppose the student 101 have taken two books, B101 and B102. This was the case. So when we make primary key of one side as the foreign key at the many side, then it will not create any problem, because there it will act as foreign key, and foreign key can be duplicated. Here the primary key is BID. BID is not null. and BID is not repeating. Okay, so remember this, primary key of one side will act as a foreign key at the many side whenever total participation is there. Okay, now another thing arises that in some question they ask us to find minimum number of tables to convert this ER diagram into relational model. Then they are not focusing on the efficiency or redundancy part. They are just asking that is it possible to create tables from this ER model, this minimum number of tables, like 2 tables, 3 tables. They ask in that manner. If this is the question, they are strictly asking about minimum number of tables, then you have not to think about efficiency and redundancy. You have to just think that is it possible to convert this ER model into this minimum number of tables? That's it. Okay. Now, let's see that if I am able to convert this ER model into just a single table, which means can I merge this student and book table? Can I do so? See here. So can I merge both this table? Try merging, and if you find a suitable primary key, you can merge. This is an important line. If you were asked a question that can I merge both this table, try thinking like this. Okay, merge if I'm finding a suitable primary key. It is not necessary that a single attribute will be primary key. Even if you combine the attributes like SID, BID, you make the combo of both, and that is working. Even it is allowed. You can, the primary key can be set of attributes also. So if you find a suitable primary key, then you can merge. But don't think that if I take all the attributes as the primary key, then it will act as a suitable primary key. No, it will not act, because primary key comes with a constraint, unique and not null. And if you apply those constraints on the attribute which is not necessary to have those constraints, then it will impose several other constraints on the relationship itself, like total participation was being imposed there when we are making BID as the primary key. Here, total participation was imposed at the book side, which was not even given in the question. So you have to think properly that will this primary key will be suitable without imposing different other constraint on the relationship itself. Student S101 name A, 102 B, 103 C. If we want to merge these two tables into a single one, let's say name it as issued books, then what will happen? What will be the primary key? Can I make SID as primary key? No, I can't make, because SID will, there is duplicate. Can I make BID as primary key? No, BID can be null. There can exist a student which has not taken any book, so BID can here be null. Can I make the combination of SID and BID as the primary key? No, I cannot make, because BID can be null. If you are making the combination as primary key, then both SID and BID should not be null. Their combination should be unique. Okay, but here BID can be null. So I can't make BID as primary key. I cannot make combination as primary key. I cannot make SID as primary key itself. So I will say safely that minimum number of tables required will be 2. Both these tables cannot be merged. Okay. Case 2. Now we are imposing total participation at book side. What does that mean? There can't be any book not issued to some student, which means book cannot exist without being related to some student. This is what total participation mean here. So book cannot exist without a student. Now we have to respect the total participation. So I have to make a little modification in our golden rule that primary key of one side will indeed become the foreign key at the many side, but the foreign key there cannot be null, because we have to impose this total participation constraint. If they can be null, which means book can exist without being allotted to some student. This will mean the partial participation, but here we are given with total participation. So primary key of one side will become foreign key at the many side, but that foreign key cannot be null. Okay, so there cannot be any book which is not allotted to some student. Okay, this cannot be the case that our SID is null. Now, can we merge the tables now? We have seen that how are we going to establish the relationship among them. What we will do? This Now the second question is, can we merge the tables now? Let me give you a important point again here. You can merge the tables if you have a combination like this. Like this. What does that mean? Total participation from one side. If that is the case, then you can merge the tables. Total participation from one side. If you see this combo, you can merge the tables. But here, total participation is from many sides. You cannot merge the tables. See here. Can we merge the tables, student and book table, into one? No. Why? Partial participation from student side, which means there can be students who have not issued any book, which means null at the BID, which was our potential primary key. But we still cannot find a suitable primary key. Why? Because this can be unique. This SID cannot be unique here. And BID is being null here. So we cannot still find a suitable primary key. Because the constraint is not on the student. It is on the book. So a student can exist without having any book. So this entry can be there. Should be there. It should be there. But SID cannot become primary key because it is duplicate. BID cannot become. Why? Because it is null here. Again, I'm not able to find a suitable primary key, so I'm still not able to merge these tables. Case 3. Can I merge now? Yes, you are seeing this combo. So what will we do here? Our golden rule was valid only till the partial participation. If total participation has come, then you have to think for individual cases separately. Now the question arises, why? Why our previous rule that the primary key of one side will become foreign key at the many side will not work here? Because we are imposing total participation here. Okay, so in this case, primary key of many side will come at the one side with a unique and not null constraint. Why is it so? We are doing so because if we send the primary key of one side, primary key of SID, to make foreign key at the many side, we will free the student table to feed itself whichever manner it wants, which should not be the case because we have to respect the total participation. What point I am to make here is, see, SID, S name. Suppose in this book table, all the books are allotted to the student 1 only. A single student has taken all the book. Let's assume this case. Can these students exist? They should not exist because each student should have at least one book, because we have total participation at student side. But if we are allowing this SID table to feed itself whichever manner it wants, who is stopping these students to come in this table? Who is stopping these students? There is no constraint. Total participation is not being respected here. So primary key of many side will become now the foreign key at the one side with unique and not null constraint. Why these constraint? Not null to respect the total participation and unique constraint to make that as the primary key. See, so what we have done, we have taken the primary key of the book side to make foreign key at the many side, foreign key at the one side. See, this was the case. So the primary key of many side will become the foreign key at the one side. Primary key of many side will become the foreign key at the one side with unique and not null constraint. Not null to respect the total participation, because if BID can be null, which means there can exist a student which has not taken any book, which means the total participation is not being respected. So we have to apply a constraint of not null to respect the total participation and unique constraint to make it as the primary key, because SID cannot be primary key here now because SID is being duplicate. Who will become the primary key then? Well, name can be same also. Who will become the primary key then? BID will become the primary key. So for that manner, for that motive, we will apply the unique constraint on the BID. Now, is merging of student and book table possible? Yes, it is totally possible. I can find a suitable primary key also, that will be the BID. So minimum number of tables needed will be 1 here. Remember, between two entities, if there is one-to-many relationship and there is a total participation from one side, then merge both entity tables and make primary key of many side as the primary key of the merged table. This is what we are doing here. We have merged both tables, and primary key of many side will become the primary key of the merged table, the whole table. If there is one-to-many relationship and there is a total participation from one side, then merge both entity tables, we have merged, and primary key of many side will become the primary key of the merged table. And if you see total participation from one side, then tables can be merged, and what will act as the key? Primary key of the many side. Okay, the point is clear. Case 4. What will happen when I have total participation from both sides? Then, if you see this, in this combo, which means you can be sure that there will be minimum number of one table required, that you can merge both these tables without any problem. But in this case, book can exist without being allotted to some student. See this diagram. Book can exist without being allotted to some student, which means that if there are 1,000 books in the library, then I will write like this: book 101, null, null, title, let's say A. If there are 1,000 books in the library which are not allotted to any student, then there will be 1,000 null, null, null entries there, which will be super redundant. So we do not generally do like this. We do not merge these tables. But if someone strictly asks that what will be the minimum number of tables, can these tables be merged? Will database will throw any error? Then in that case, you will say no, it will not throw any error. Although it will be redundant, but it is possible. Okay. So in that case, what will happen? In this case, we have done that primary key of many side will become the primary key of the merged table. And we want to impose the same constraint from this side also, which is their total participation at both sides. Then what will we do? We will make their combination as the primary key of the merged table. Okay, so if you see this combo, then you can surely say they can be merged, and the combination of both will act as the primary key of the merged table. And DID had not null and unique constraint. Why? Because one book can be issued to exactly one student. Total participation and 1. What does this say? It says that a book cannot exist without being allotted to some student. And this will say that each book will be associated with a single student only. So each book will be given to exactly one student. This is what it says. Okay, like this. Each book will be associated to some student, and a book will be given to exactly one student. Okay, so for this, the total participation should be respected. We have applied the not null constraint, and for this one to be respected, we have applied the unique constraint. Okay, and for SID, we have to just apply the not null constraint to respect the total participation, because the student can issue multiple books. So I cannot imply the unique constraint here, because student can issue the multiple books. That's why many is written here. So for many, I have not written the unique thing. For total participation, I have written the not null. Here, 1 and total participation both are there. So I will write not null and unique part. Think about this if you are getting confused. This is the easy part, you can get it. We need to make the combo as primary key so that no book can exist without a student. And for a student to exist, he must issue at least one book. So these types of tuple will not be allowed. Okay, so let's summarize our point. For one-to-many relationship, partial participation from both sides, 2 tables will be required. Partial participation from many sides, 2 tables will be required. Total participation from one side, both can be merged, 1 table. Total participation from one side here, you can see 1 table. That's it. So if someone strictly asks minimum number of tables, then you have to answer this. Otherwise, for efficient design, we do not seek minimum number. I have given you this example. If you have, let's say, 1 lakh books or 100,000 books which are not allotted to any student, then 100,000 null entries will be there. Redundancy will be there. Okay. In the next lecture, we will learn about one-to-one relationship conversion into tables. From the previous few lectures, we have been learning how to convert the ER model into relational model. We have learned how to show the entities, their attributes, and then we were discussing about relationships. To describe the relationship or to show the relationship into tables, we have two methods. The first one was using the concept of primary key and foreign key. The second one was creating a separate table for relationship itself. Till now, we have not faced an issue in our first method because we were encountering one-to-many relationship. When we will face many-to-many, we have to create a separate table for the relationship. In this lecture, we will learn about one-to-one type of cardinality. Okay, in our last lecture, we saw that if we have partial participation at both sides, in the case of one-to-many, we will require two tables. One for this entity, one for this entity. And what we did, we made the primary key of one side, foreign key at the many side. Okay. And then we have also tried merging the two tables. But we failed to find a suitable primary key. That's why the minimum number of tables required will be 2. When we had total participation at many side, same case has occurred. The minimum number of tables required will be 2. But when you see this combination, which combination? Total participation at one side, then you can surely say that both tables can be merged and minimum number of tables will be 1. So when I told you that you do not create a separate table for each entity in some of the cases, so this was the case in which there is no need to create a separate table for both entities. Even in one table, you can represent this whole diagram. Now, coming to the one-to-one cardinality. We'll first start with the partial participation case from both sides. We have this example of department has a chairperson or chairperson has a department. You can read from both sides. Department has department ID and department name, while chairperson has chairperson ID and chairperson name. So what we did in one-to-many case, we started with the primary key of one side and made foreign key at the many side. But here you can see there is no many side. 1-to-1. Where is many side? It is not present. So what will we do? You can choose any primary key and make the foreign key at the another table. Okay. So there is no many side. You can take any primary key and make foreign key at the other side with uniqueness constraint. Why uniqueness constraint? Because to show this one-to-one type of cardinality, you use the uniqueness constraint on the foreign key. And if you want to show the total participation, then you use not null constraint on the foreign key. Let me repeat. To show one-to-one cardinality, you use uniqueness constraint. And to show total participation, you use the not null constraint on foreign key. But here, total participation not present, just the partial participation. So there will be no constraint on participation now. We can just apply the uniqueness constraint and our work will be done. So department ID, department name, let's say department 101 has name X, department 102 has name Y. Can this tuple exist? Yes, because there is no total participation constraint. Department ID can be null, which means a chairperson can exist, which doesn't has any department. Okay, this type of tuple are normal, and opposite thing can also happen. Can this type of thing exist that in a department there is no chairperson? Yes, this can also exist. How will we show that? We will just see if, let's say, department 102 reference the parent table, and if you do not see an entry with department 102, which means there is no chairperson for that department. So this will solve the problem of converting this ER model into relational model. Second question arises. We have solved the first question was how to represent this ER model into relational model. We will create these tables and department. We will take the foreign key. We will take the primary key of department ID and we will make the foreign key at here chairperson table. So our first problem is solved to represent this. The second question is, can we merge both tables? So you can directly answer that until you see the combination of total participation at one side, you cannot merge. So here, you cannot merge until you see this combo, total participation at one side. Why we cannot merge? What will be the problem? The problem will be the primary key. Which primary key you will make? Can you make this DID? The primary key, no. DID can be null because there can exist a chairperson which doesn't have any department. So this type of tuple can exist. A chairperson can exist which doesn't have any department. So you cannot choose DID as the primary key. Can you choose CID as the primary key? No, because there can be a department which doesn't have a chairperson. So this type of tuple can also exist. CID can be null, DID can be null. So you cannot choose DID as the primary key. You cannot choose CID as the primary key. You cannot choose their combination as their primary key, which means you will require at least two tables to show this. Okay. Can you read this ER diagram? There is partial participation from department side, and this arrow says at most one. Partial participation doesn't impose any constraint, so we'll ignore that part and we'll just keep this at most one part. So I can say department can has at most one chairperson. Here, this total participation says at least one, and this arrow says at most one. If you combine at least one and at most one, it will give you exactly one. So a chairperson can has exactly one department. I hope you are able to read the ER diagrams. Okay. Now let's convert it into relational model. You can see 1-to-1 cardinality with total participation. 1-to-1 uniqueness constraint, total participation, not null constraint. Now question arises, which primary key will become foreign key? Should I choose the primary key of department or I should choose the primary key of chairperson? Think. I cannot let this chairperson entity freely feed data into itself. If I allow the chairperson entity to do so, it will also allow the tuples which will include the chairpersons which doesn't have any department due to this total participation. Can we say there is no many sides, so either primary key will become foreign key at another entity? Here we had the choice because here we had partial participation at both sides. So we can allow both department entity and chairperson entity to freely feed data into itself. But when we see this total participation, we cannot allow the chairperson entity to freely feed data into itself, because if we allow this to do so, then chairperson entity will also allow those tuples which doesn't have any department, which should not be the case due to this total participation constraint. So I cannot let the chairperson entity freely feed data into itself. I will make the department ID foreign key at the chairperson entity with not null and uniqueness constraint. This will surely stop those chairperson which doesn't have any department. See this. Will these tuples be allowed? A chairperson which doesn't have any department? No, because of the not null constraint. And here we had the exactly one constraint on us. At least one, at most one will give you exactly one. Which means you also have to apply the uniqueness constraint on department ID. Why? Because there cannot exist two chairperson which have the same department. Getting the idea? A chairperson can has exactly one department. So this, due to this 1-to-1 mapping, uniqueness constraint was important. Now the question arises, can we merge the tables? Of course, yes. We are seeing this combination, total participation at one side. We will merge them if we were asked to do so. When you see this combination, you will say, yes, we can merge. Which key I will choose? What will be the primary key of the table? Will I choose the CID or I will choose the DID? Think about it. So the answer is department can exist without chairperson, but chairperson cannot exist without department. If I allow this CID as the primary key in the merged table, then it will also stop those entries of the department which doesn't have a chairperson. Is it possible? Yes, it is possible. Department can has at most one chairperson. At most also includes 0. So there can be department which doesn't have a chairperson. So making CID will stop those tuple coming into our table. So I cannot make CID as primary key. If we make CID as primary key, then it cannot be null. How will the entry of department without a chairperson will come then? So we can merge, but we have to make the department ID as the primary key of the merged table. Okay. Case number 3. Department has a chairperson, total participation from both sides. We cannot freely allow both tables to populate themselves, which means department ID will become foreign key at the chairperson side and chairperson ID will become foreign key at the department side with unique and not null constraint. Why unique? Due to this, and why not null? Due to this. Got the idea? So is merging possible? Yeah, of course merging is possible because we are seeing this combination, total participation at one side. Merging is definitely possible, and it will mean that there will be exactly one chairperson for each department. Make either of department ID or CID as primary key, but ensure to apply the unique and not null constraint. Here we had the problem. We cannot make the chairperson ID as the primary key, but here we can make any of them the primary key because of the one-to-one mapping. Exactly one-to-one mapping. See, exactly one chairperson for each department. Make either of the department ID or chairperson ID as primary key, but ensure to apply uniqueness for the one-to-one and not null for total participation. One more thing to notice, there will be no unnecessary nulls present due to the total participation, and it will be like a perfectly looking table. So we will see the summary. For one-to-one, partial participation at both sides, you will require 2 tables, and whenever you see a total participation at one side, as there are both one side only, so when you see total participation at one side, you can safely say both the entity table can be merged into a single table, and you will definitely find a suitable primary key. One table, one table, one table. Got the idea? Case 1, we have department which has employees, or department will have employees. Department ID, department name, employee ID, employee name. We have learned that to show the entities, we will create separate tables. To show the relationship, either we can create a separate table or we can use the concept of primary key and foreign key, the parent table and the child table. We will first try that the method 1 will work. We will first see that. If the method 1 fails, then we will jump to method 2, which is creating a separate table for the relationship itself. Here you can guess that method 1 will not work. Either you try to make this DID as the foreign key here or employee ID as the foreign key in the department ID, they will not work. Why? Because you will fail to find a suitable primary key. See here. If I make this employee ID as the foreign key at the department table, first of all, a department can have multiple employees. Atomic values is allowed, so I cannot do like this. Then we have to create a separate instance like this 101A and E102. If this happens, then department ID will not be unique, then it will become duplicate. In that case, I have to search for a different primary key. I have to create a new primary key. Can I use this employee ID as the primary key? No. A department can exist which doesn't have an employee. Many to many, 0 is also allowed. So employee ID can be null. So employee ID cannot be primary key. Department ID can be duplicate. So department ID cannot be the primary key. So this combination will also not work. Then what will happen? Should we try doing the same thing here? Department ID become the foreign key at the employee table. Similar thing will happen. Similar thing. Because of the same relationship. Can you see the symmetry? Many to many, partial participation from both sides. So if from the one side it is failing, it will definitely fail at the other side, which means department ID when will become the foreign key at the employee table, then also you will fail to find a suitable primary key. So this linking using parent table and the child table is failing now. What will we do now? We have to create a separate table for the relationship itself. So when you see many-to-many relationship with partial participation at both sides, you will require 3 tables, 2 for the entities and 1 for the relationship itself. So we will create a table for this have. We will name it as have table. And what will be the attributes? The primary key of the both attached entities, which is DID and EID. And what will be the key? The combination of both. This will be the table like 101 has employee 101, 101 has employee 102, 102 has employee 101, in that manner. So which department has which employee and employee belong to which department? To show this, we have the have table. And it is like a junction between two tables. So this is also known as junction table. Department and employees both are allowed to freely populate themselves. Is it clear? The case 2, total participation from one side. People tend to mug up that whenever you see many-to-many relationship, you will require a separate table for the relationship itself. So there will be 3 tables whenever you see many-to-many relationship. But they forget that what is the participation constraint? Is it total participation or partial participation? That rule that you will require a separate table for the relationship will only work when you have partial participation at both sides. Whenever you have total participation, you have to think again. Because in this case, each employee must be associated to a department. Total participation is there. So we cannot allow employee to freely feed itself the data. Free population for employee is not allowed. In that case, I have to make this DID as the foreign key at the employee table. With which constraint? Not null constraint. I have told you to respect the one-to-one, we apply the uniqueness constraint, and to respect the total participation, we apply the not null constraint. So we have to make this primary key, foreign key here with the not null constraint. Here, even after many-to-many relationship, we will require just 2 tables. So always remember the full rules. Many-to-many relationship with total participation or partial participation. Do not just remember like this. If I see many-to-many relationship, I'll require a new table. No, this is not the correct manner. Also see the participation. So we cannot allow employee table to freely populate due to the total participation. There should not exist any employee who has not been allotted any department. So we will make DID as the foreign key at the employee table. And what will be the key? The combination DID and EID. DID will not be null because we have to impose the total participation at employee table because DID is acting as the foreign key. And at foreign key, we apply the not null constraint to impose the total participation. Have you noticed I have written not null constraint at EID also? Why is it so? Because we want to create a combination of the key. We cannot just make DID as the primary key. Why? Because there can be multiple employees at the same department. So E101, let's say name A, working at department 101. E102, name A, or let's say name B, working at department 101. So department ID can be duplicate. And just the department ID cannot act as the primary key then. So we have to make the combination as the primary key. And if combination is primary key, then the part cannot be null. That's why the not null constraint here also. Department is allowed to freely populate because there is no such participation constraint at the department. But employee is not allowed to freely populate. That's why we have applied the not null constraint at the foreign key. So this type of values will not be allowed then. E102, B, department null. The employee which doesn't have any department should not exist. This is what the not null constraint at DID is implying. Now the question, can we merge both tables? You can directly answer no. You can only merge until you see this type of combo. Total participation at one side. Try merging and find the suitable primary key. You cannot merge. Why? Because you will not find a suitable primary key. Department ID can be duplicate. Employee ID can be duplicate. Their combination. This will also not work because such type of tuples. This should be allowed. But by making this combination as the primary key, it will not allow this type of tuples. That's why it will not act as the primary key. Now we will move to case 3. Total participation from both sides. Many to many. Can we merge the tables? Now there is a twist. Yes, we can merge the table. Why? Because of this total participation at both sides. Think of it like an exception. Even after you are not seeing this combo, in this case only you can merge. When you see total participation at both sides. Department and employee should not be allowed to freely populate, which means we are doing like this. Department ID will act as the foreign key here at the employee table with not null constraint, and employee ID will act as the foreign key at department table with not null constraint. So both the tables kinda look similar and their combination will act as the primary key. Make the primary key of department foreign key at the employee and primary key of employee foreign key at the department, and also apply the not null constraint at the foreign keys to apply total participation. Well, uniqueness constraint is not required due to many-to-many cardinality. Okay, so not null constraint both applied at the foreign key, and their combination department ID and employee ID, department ID and employee ID. This should be unique, and this will act as the primary key here. So can we merge both the tables? Yes, both the tables can be merged. Why? Because of this not null constraint. These type of tuple will be automatically debarred. So department ID and employee ID will act as a primary key in combination. So even after merging the table, we are here finding a suitable primary key. Okay, so minimum number of tables required will be 1. So you don't have to be confused like this. Just follow the basic rules. Can we merge both the tables? Try merging them, and if you can find a suitable primary key, you can merge. So both side many to many, total participation at both sides, then just one table is enough. Many to many, total participation at both sides, just one table is enough. So if you see total participation at both sides, then regardless of one or many, minimum number of tables will be 1. Ignore either one or many. If you see total participation at both the sides of a relationship, then you may be sure that both the entities can be merged into a single table. Okay, total participation at both sides, minimum number of table required will be 1. Now let's discuss more on descriptive attribute with an example. I was kind of rewatching the recorded videos and I saw that a different example on descriptive attribute is necessary. For example, student enroll in the subject. Student has student ID, student name, subject have the subject ID and subject name. Now suppose I want to store grades also. Then where I will add this attribute? Should I add the grade to the student or should I add to the subject? Think, say that Rohan has achieved grade A in physics. But by writing this grade, I am making grade as the property of a student, which is not my motive. If I add the grade attribute to the subject, then what will happen? If I say grade B to physics, then I'm giving the subject physics as grade B, which I don't want to give. I want that Rohan, which is a student, has enrolled in subject physics, has achieved grade A in physics subject. So if I add the grade attribute to student and then I will say grade A to Rohan. I will not talk about the subject then. If I say like this, if I added the grade attribute at the subject, then I will be saying like this, grade B to physics. Then I will not be talking about the student. to properly describe my intention that I want to give grade to the student who are enrolled in so and so subject, I have to make grade the attribute of enroll. In such cases, we add this grade attribute to the relationship itself, and they are known as descriptive attribute. And one more thing, that this attribute is not counted in the cardinality of the relationship. Like we say unary relationship, binary relationship, ternary. This will not make this relationship ternary. It will still remain binary. This grade will not count to the cardinality or the type of that relationship. Like it will not turn into ternary. It will still remain binary. And we have to create a table for the relationship, because here we can see many to many part is there. So we will create a table for the relationship, and in that table we will add this grade as a different column. Now I can easily describe that student 101 in subject 2 has achieved grade A. Student 102 in subject 1 has achieved grade B. I hope you have now understood the importance of descriptive attributes. In this lecture, we will learn to transform unary relationship into tables. Case 1, one-to-many, partial participation. Can you read this ER diagram? At most one, many, which means an employee can have at most one manager, an employee can have at most one manager, or one manager can manage many employees. Now to show this into tabular format, for employees we can create a table. But for relationship, what we have done, primary key of one side will become foreign key at the many side. But here, just a single entity, then what will we do? In unary, it will happen in the same table itself, which means employee ID will again come as the new attribute to become the foreign key in this employee table itself. And you know that two columns cannot have same name. That's why we are renaming it to the manager ID. This will do the work. Now, see this table. Multiple employees have same manager. Is it possible? Yes. One manager can manage multiple employees, or say this like vice versa. Multiple employees have same manager. Can it be possible that an employee doesn't have any manager? Yes. What I've written here, at most one, which also includes 0. So this table is respecting like this ER diagram properly. And we have not applied any constraint on foreign key, because foreign key can be duplicate also, and foreign key can be null also. Okay. Case 2, total from many side. Total from many side. Partial from one side and total from many side. Just think about it. Is it like possible? At a single entity, you are referring that some instances will be in partial participation and some instances will be in total participation. Is it possible from the same entity? It's not possible that some of the instances are in partial participation and some are in total participation, because it's like applying a nullable and a not null constraint on the foreign key at the same time. Nullable and not null constraint at the same time. So this is like not logical. Total participation and partial participation at the same entity, which means nullable and not null constraint at the same time. In unary relationship, one side total, another side partial is not allowed. Either it will be total partial or it will be total from both sides. So I have just copied this. That's why it's total participation from both sides. What does this say? This represents at most one, and total participation says at least one, which means an employee must have exactly one manager. An employee must have exactly one manager. Now what will we do? Same thing, but at manager ID we will apply the not null constraint. This is allowed. Apply not null constraint at the manager ID, because there cannot be any employee which doesn't have any manager, because here we are implying exactly one. Okay, exactly 1. Null is not allowed. See this total participation. So there cannot be any employee which doesn't have any manager. That's why we applied not null constraint. Case 4. One-to-one relationship, partial participation from both sides. What does this say? A student can have at most one roommate. It's also possible that a student doesn't have any roommate. So we will do the same thing like we did in many cases, but what difference we will do this time? Think about it. We will do the same thing. We will make this SID foreign key in the same table using a different column name, let's say roommate ID, RID. What constraint will apply now? We will leave it as it is, or we'll apply not null constraint, or we'll apply uniqueness constraint. So the answer is we'll apply uniqueness constraint. It's an easy question. We have applied not null constraint in the case of total participation. We have left it as it is in the case of partial participation, either one-to-many or many-to-many case. But when you see one-to-one case, you have to apply uniqueness constraint. When you see total participation, you have to apply the not null constraint. Uniqueness constraint for one-to-one. So we'll say RID will be unique, duplicate values are not allowed, and null values are allowed because of partial participation. So this cannot be case that student 103 have roommate 103 and student 104 have roommate 103 again. Okay. And I also want to clarify one thing, that the example of ER diagram which I am using is just to make you understand the concepts. Don't seek like proper meaning in those ER diagrams, like in real world it doesn't happen like that. Or are you getting the point? These example I'm just choosing to make you understand the point or understand the concept or fundamentals. Okay. Total participation 1-to-1. In this case, it says a student must have exactly one roommate, exactly one. It cannot be like 0, it cannot be more than 1, it will be exactly 1. So what I will do? Make SID as the foreign key with a different name, let's say roommate ID, and we will apply not null due to the total participation, and 1-to-1, that's why uniqueness constraint. We'll apply the uniqueness and not null constraint on the foreign key. Not null for the total participation, uniqueness for 1-to-1. For all unary 1-to-1 case, minimum number of tables required will be just 1. We will not require a separate table. Even if in one-to-many case we have not seen that will require a separate table. Now let's understand many-to-many. A student can have 0 or more roommates, which means partial participation from both sides, and many-to-many. I hope you can remember that whenever you see many-to-many with partial participation, a separate table will be required. If you make RID as the foreign key in the student table, then primary key won't be just SID because of many duplicate values. So this SID will not now act as the primary key, because if we make the SID as the foreign key with the name RID, then a student can have many roommates. Let's say S01, S101 have roommate R103, and S101 have now a separate roommate, let's say R104. It's like one student can have many roommates, and atomic values are not allowed, so we have to create a separate instance. And if we make a separate instance, then SID will not now work as primary key because of duplicate values. If SID cannot be primary key, we will seek for the different primary key, let's say for the combination of SID and RID. But in that case, RID cannot be null. And if RID cannot be null, which means we are imposing total participation, which means there cannot be any student without roommate. But this is not the case. So we cannot adjust in the single table itself. We will require a new table. What will we do? We will, from SID, we will take an SID here and with a different name RID here. Now I can freely populate the student table, and with no restrictions I can do like this. student 101 has roommate, let's say 102, 101 has roommate, let's say 103. So there will be no restrictions. Now every problem is solved when we have made a different table for the relationship many to many, partial participation from both sides. And I've told you that if you see total participation at both sides of a relationship, ignore just one to one and ignore many to many or one to many. If you see total participation from both sides, then the two different entity tables can be merged. Here it's just a single entity, so we will just require one table to represent this. Total participation from both sides, there cannot be any student without a roommate. So what will we do? We'll impose a not null constraint, which means SID, SName, RID, where RID cannot be null. So these type of tuple will not be allowed and their combination will now act as the primary key. Okay, why the combination? Because many to many cases there. Duplicate values for SID will be there. So SID alone cannot act as the primary key. And RID is not null. So we can just make the combination of SID and RID and it will become the key. Now let's summarize for the unary part. One to many, partial participation, just the single table. For each case, you will require a single table only, and except this many to many, partial participation at both sides. For this, you will require a separate table for the relationship itself. Now let's move forward. Generalization, specialization, and aggregation. So we'll begin with the generalization or specialization. We will learn three different ways. See this ER diagram. Let's say phone number will act as the primary key. So what will we do? Make the primary key of supertype, foreign key at the subtype with unique and not null constraint. This will act as the method 1. What I'm saying, make the primary key of supertype, foreign key at the subtype with unique and not null constraint. So what will we do? Phone number here, and when phone number will act as a. Now let's see the case of generalization, specialization, and aggregation. We'll begin with generalization and specialization. We'll learn three different ways. Let's see the first one. In the method 1, what will we do? Let's say phone will act as the primary key. So we'll make the primary key of supertype, foreign key at the subtype with unique and not null constraint, and there it will act as the primary key. Okay, so phone will now work as the primary key in the subtype entity tables for employee and customer. Okay, this will act as the method 1. Method 2, use attribute inheritance. Do not make table for the supertype. Let the subtype inherit all the attributes, which means along with the attributes of subtype, inherit the supertype attributes and then make table for each entity. So we'll make table for employee and customer only, no table for person. What will we do? We'll inherit these attributes: phone, name, and address to employee, and phone, name, and address to customer. So phone name, address to employee, phone name, address to customer. This is the perfect example of attribute inheritance. But there is a kind of problem in this. It will not work on the partial participation, because in partial participation, a person can exist who is neither employee nor customer. What will we do then? Okay. Method 3, just create a single table for the supertype, add the attributes of subtype in the same table along with an additional attribute, employee or customer. We call it as subtype discriminator. What will we do? We will create just a single table, all the possible attributes there. So we'll write like phone, name, address, employee ID, salary, credit, customer ID, and email. And we will also add an additional attribute, which is subtype discriminator, which will tell us that it's employee or customer. If the subtype discriminator is simple, which means disjoint constraint is applied here. If it is composite, then overlapping constraint. If someone asks you to ask for the minimum number of tables, what will you reply? Just one table, which we got from method number 3. Okay. Now let's learn about aggregation. Employee works on a project and uses a specific software. So let's think like this. We'll begin by creating the tables for the entities first: employee, project, and software. Now, many to many, that's why works on will also have a separate relationship table. Works on due to many to many. And now, what about this uses? So firstly, we have to understand what this uses table will have. So from uses, we want to show the employees working on a specific project using a specific software. So we will make this use table like employee ID, project ID, and software ID. An employee working on a specific project using a specific software. And this whole combo will now work as the primary key. So how are we going to represent aggregation into relational model? Make the table for separate entity, and for the aggregation relationship also you have to make a separate table which will have the employee, project, and the software ID as the primary key, the combination as the primary key. Okay. So now it's like almost over about the relational model. Relational model have told us how to store. Data will be stored in tables. We have seen all the different type of constraints. And now it's time to understand the manipulation language, which is SQL. But we cannot just directly start the SQL language. We have to first get the foundational knowledge. That's why we'll begin with relational algebra, tuple calculus, domain relational calculus, and then we will jump to the SQL. In this lecture, we will start our new unit, relational algebra, which is like the foundation for SQL. I can say SQL is based on two theoretical languages, relational algebra and tuple calculus. Relational algebra is also known as procedural language, which tells us or which answers both the question, what to do and how to do, while tuple calculus only answer what to do. That's I have written here, procedural language answers both the question, but tuple calculus just answer what to do. See, I know that you may not get this properly, but when we will learn about them individually, then you may get the proper idea what we mean by this. Okay. In relational algebra, we'll deal with three things: output, input, and operators. We'll learn about different type of operators. Input will have one or more relations, while output will always contain exactly one relation. Okay. Then let's move to the types of operators. The operators can be defined into two parts: fundamental and derived. All these derived operators are derived from these fundamental operators. That's why the name derived. And fundamental operators are the basic operators. We will learn about selection, projection, union, set difference, Cartesian, and renaming. So we'll not waste any time and we will start with our fundamental operators. The selection. Selection, as the name suggests, is used to select. Now select what? Rows. This is the key point. It is used to select rows tuple of a relation. See, rows doesn't have any name. We do not name the rows like row 1, row 2, row 3. So we apply some condition. Based on that condition, we filter out the rows from the database. Similarly, if we want to filter out the columns, then there is one different thing. That column have names. So we'll just write the columns and it will output those columns. But selection operator will only work with horizontal selection. For column selection, we'll learn about the second operator, which is projection. Selection, horizontal; projection, vertical. Remember this thing. Selection, it is used to select rows tuple of a relation. It is a unary operator, which means input as well as output is just one relation. This was our table. Feed it to the selection operator. It will output you your desired rows. This is the syntax or the way to represent. See, in relational algebra, it is just theory. There is no sort of compilation. So for standard things, you have to use the standard things. And for basic things like representing and like this or like this, it's on you. Okay. There's no compilation process here in this. Okay. So this is our syntax. Selection operator. This P will represent the condition and it is applied on the relation. just one relation, that's why unary operator, and it will output the rows of that relation. So this will also be, the output will be also one relation. Since rows do not have any name in the table, so to select rows we have to apply a certain condition or predicate. It's clear? The degree of a relation equals to the degree of the output. Think about this. The degree is what? Number of attributes or the number of properties. While doing horizontal selection, the number of properties will remain same, 1, 2, 3, 4, 5. So the degree of relation will equal to the degree of output. But the cardinality means number of tuples or number of instances or number of rows. So when we filter out some of the rows based on the condition, obviously rows will become less than the original or maybe equal than the original. That's why cardinality of the relation is greater than equal to cardinality of the output. I hope this thing is clear. Suppose this was our table and I want to extract the rows of the status junior. Then the number of rows which will come in the output will be just row 1 and row 4. But focus here that the number of attributes have remained same. Cardinality have reduced from 4 to 2. That's why the degree remains same and cardinality may decrease. Okay. So how to now represent this? We have a student table, 4 attributes, and out of those 4 attributes, I want to select those rows in which status is junior. So I will write sigma condition, and in condition I will write status equals to junior and the relation. What was our syntax? Sigma PR. So sigma here is the sigma, P is the relation, P is the condition, status equals to junior, and R was the student. Okay. Now I want to apply one more condition on that. Out of those junior, I want that junior which has an ID of 1, 1, 2, 3. Again, what I am doing? Filtering out the rows. Selecting the rows based on some condition. Then I have to again apply the selection operator. So on this relation, I will apply a selection operator with some condition. So you can also do like this. Suppose initially we have started sigma P1 R1, and what this will result? A relation again. Let's say this relation is R2. Now I'm applying another condition. Instead of showing like this, you can directly show like this. Sigma P2. That's what we have done here. This will output a relation, and on that relation we have applied another condition. Now what will this output? Just this row, just a single row. Okay, and selection operator is commutative, which means either you apply this condition first or this condition first, it doesn't matter, which means sigma P2 P1R or sigma, I should write like P1 P2R, both are same. And one more thing, instead of using two sigmas, what you can do, you can apply AND operator in the condition itself, like this, ID equals to 1, 1, 2, 3 and status equals to junior. This will also work. So all these three are equal. Another question, give the list of those employees whose salary is 10,000 and age is greater than 30. Now we are applying two conditions here. Again, you can either use like this, you apply the condition first and then on that condition you apply again the selection operator. You can do like this, like age is greater than 30 on relation employees, and then that you can apply salary is 10k. You can do like this, or you can use the AND operator. Now again, I have told you there is no, this is just a theoretical model and there is no compiler. So either you can represent AND like this or AND like this, just the way to represent. When we apply the sigma, all the columns will be in the output. All the columns will be in the output. Here we have seen all the columns will be in the output. Suppose I just want to extract a single column, or let's say 2 columns. Then what will we do? I've told you for vertical selection, we use the projection operator. So when we apply sigma, all the columns will be in the output. So for horizontal row selection, we use sigma. Now, if we want only specific columns to be in the output, then we will use the projection operator. It is used to select columns or attributes of the table or relation. Again, it is a unary operator, which means it will take one relation into the input and will give just a single relation in output. Since each column has a unique name, we can specify name of the column which we want in the output. Why we have used condition in the selection operator? Because the rows do not have any name. How we are going to filter out the rows? But column have names. So we will just write the name of the column which we want and we will get that. Since each column has a unique name, we can specify name of the columns which we want in the output. Rows didn't have their own name, so we had to specify a condition based on that rows were filtered. Again, here we have name for each column, so just specify the name and you will get the column in the output. See this. We have this table. Now I want to extract just the 2 columns out of this. The name and is active. So we'll apply projection. Just write the names of the column which you want and you will get that. Also remember that a column value can be duplicate, but a whole tuple in the relation cannot be. This is an important point. See, you are extracting 2 attributes, which is name and column. Name and is active. That's why no tuple is duplicate of other. Like John true, Tom false, Mike false, Smith true, Don false. When you see the combination, no tuple is duplicate of other. But let's say if you extract just this column, like is active, then what will happen? Forget about this. Just see this. You are seeing that true, false, false, true, false. It's violating the basic property of a relation, that rows cannot be duplicate of each other. This row is duplicate of this row is duplicate of this row. What will we do? We will eliminate the duplicate rows. So projection eliminates duplicacy. If I extracted just the is active part, then there will be multiple true and false values which are duplicate and hence will be removed. So output will be just this. Projection eliminates duplicacy. That's why you must have guessed in the cardinality part, cardinality of relation may be greater than or equal to the cardinality of this projection output. Why? Because projection eliminates duplicacy. Here the cardinality was 1, 2, 3, 4, 5. Here the cardinality is just 2. Cardinality has decreased. What about degree? Degree has also decreased because here the degree was 1, 2, 3. Now the degree is just 1. So the degree of a relation is greater than equal to the output. Cardinality of the relation is greater than equal to the output. Now you must have guessed. Works magically with the select operator. For example, give the name of all those employees whose salary is greater than 5,000. So what are we doing here? First we are applying the condition, and then what this will result? It will result all the attributes. Now out of those all the attributes, I want just the name. This will give me the proper result by name. How to get the attribute which we want? Just mention the name. Projection, name the attribute which you want. I want the attribute with name, and then the relation itself. And in this relation, only those rows are present which has a salary attribute greater than 5,000. Another question, are they swappable? Can I first extract the name and then apply condition? This doesn't make sense. It's illogical that if I extract the name first, then the table will only contain the name attribute. Now, even if I apply salary greater than 5,000, there is no salary attribute. So you can guess this is not swappable. They are not swappable. If you do like that, you will just get the name. There is no salary attribute. Okay. The set operations like union, intersection, and set difference can only be applied if both the tables are compatible. Now we have moved to our third operator, fundamental operator, that is union. And before we understand the union operator, we have to understand the union compatibility between the tables. You cannot add any two tables, or you cannot just union between any two tables. They must be compatible. And how we decide the compatibility? Same degree and same domain. Same degree and same domain. Well, names could be different. Like here, if I write AB and CD, names can be different, but degree should be same. And the domain should also be same. Like this. If A is int and B is float, now degree is same, but here the A is character and B is float. Will it work? Will they be union compatible? No. Will they be union compatible? No, degree is not same. Here degree is 2, here degree is 3. So they are not union compatible. Suppose A and B and C and D, they have same domains, and we can count that degree is same, 2 and 2. Then what will be the result of the table? In relation R1, we have A1, B1 and A2, B2 as tuples, and R2, we have C1, D1 and C2, D2 as tuples. Then what will we do? The result will only contain two attributes. It will not be like this. It will only contain two attributes. Which one? The first one. Okay. So A1, B1, A2, B2 will be exactly copied here. C1, D1, C2, D2 will be copied here. R1, C, D, R2, A, B. If I have written C, D first, then C, D will be the name of the attributes. Now you may wonder that these tables, are they different? Then let me tell you. This is the table which you are seeing. In the file, just these entries are stored. We have talked about this when we have learned the conceptual schema. In the disk, just these entries are stored. And I have told you that the order of rows are immaterial or insignificant. That A1, B1 comes first or C1, D1 comes first, it does not matter. So they are the same tables. Okay. So I can say that union is commutative. Just the name of the attribute will be different. Okay. Union also eliminate duplicacy like projection. These are all set operations, and you know that duplicate values are not allowed in sets. Conditions for union compatible. Number of columns should be same. I have not written the name. Name can be different, like we have seen here. A, B and C, D. Name are different, but number should be same. Degree should be same. And column data type with order should be same. Here, if this is int and this is float, then I cannot have this as float and this as int. The column data types with order should be same. Okay. Book and stationery. We are asked, find SID of all the students. Whenever you are given questions like this in relational algebra, the first and foremost step is to identify the table. SID of all the student. Just the student table will be enough. Relation, attribute, projection operator. This is our answer. B. Find SID of all the students who have issued at least one book. What will we do now? Step 1. Choose the table. We are asked with the SID. Does book have the SID? Yes. Will book itself be enough? Yes, because we were only asked with the SID. So find SID of all the students who have issued at least one book. SID as the required attribute, book as the relation here. But will this projection operator tackle this at least one part? Think about this. Suppose book 101 is with the student S101. Book 102 is with the student S101. Book 103 is with the student S101. When I will apply the projection operator and will extract the SID part, then this S101 will come only once. So at least part will be covered. Okay. Even the S101 come once or it comes multiple times, the projection operator removes the duplicacy and will count only one in the final output. Find SID of all the students who have issued some stationery or book. Here it is or book. Step 1. Identify the table. we will require these two tables, book and stationery, because we want SID from both these tables. What will we do now? We will use the union operator because we want the SID from both the tables. We want SID from both the tables. Can we directly put union between these two relations? No, because we are not strictly or explicitly given that they can be union compatible. Are you given both tables are union compatible? No. So what we will do? Instead of merging both the tables, we will first extract the SID from both tables, SID from book and SID from stationery, and then we will merge the SID. Let's say for book we have SID S101, S102, S103, S104, and for SID for stationery we have S101, S102, and S105. So in output we will have 101, 102, 103, 104, and 105. Because union also removes the duplication. Union can be commutative and associative, like A union B equals to B union A. And for associative, either you first do A union B and then do union with C, or do B union C and then do union with A, will be same. And you have noticed that degree will not change. Here the degree was 2, 2, and in the output also degree remained 2. But the cardinality, what about cardinality? R1 plus R2 cardinality will be greater than equals to R1 union R2 cardinality. Why greater than equal to? Because of the removal of duplicate elements. See, we have S101, 102, and 103 here. And in R2 we have S101, S103. For if we do the addition, then it will 3 plus 2 will be 5. But 5 is greater than equal to what will be the union result? 101, 102, and 103. Just 3 only. So 5 is greater than equal to 3. You're getting the idea? And why equal to? Because it may be possible that the elements of R1 and R2 are completely distinct. So they will both get the entry like S101, S102. Here we have S103, S104. So 2 plus 2 will be 4 here. Okay. Moving to the next operator, set difference. Again here compatibility is must. And to understand the set difference, we can see like this: A minus B. All those elements which are present in A but not in B. A set difference B means elements present in A, remove the element from A which are in B. Remove the element from A which are in B. For example, 1, 2, 3 is in A and 2, 3 is in B. So the output of set difference will be just 1. Okay, all those elements which are present in A but not in B. A minus B is not equals to B minus A. You must have guessed till now. For example, 2, 3 was or B and 1, 2, 3 was or A. If I do the set difference here, the output will be phi. Got the idea? A minus B minus C is obviously not equals to A minus B minus C, which means set difference is neither commutative nor associative. And what about degree? The degree remains same. R1, R2 and R1 minus R2, the degree remains same. What about cardinality? If they have the common instances, for example, 1, 2, and here also 1, 2, this was in R1, this was in R2. If I do the set difference, I will get phi. So if R1 and R2 have common instances, then the cardinality of R1 minus R2 will obviously be 0. And if they have disjoint instances, then R1 minus R2, let's say 1, 2, 3 minus 4, 5. The output will be 1, 2, 3, which means the R1 only. So the cardinality of set difference R1 minus R2 will be from 0 to R1. 0 in the case of common instances and R1 in the case of disjoint when R1 and R2 have no common instance. In the next lecture, we will see different questions based on this, and we will also start our Cartesian product. Let's start with an example now. We are asked with find student ID of all those students who have issued stationery but not books. In the last lecture, we have discussed about set difference, which means A minus B. Remove all the elements of B from A. Similar question is asked here. all those students who have issued stationery but not books. Remove all the SID of books from stationery, which means extract the SID from stationery minus SID from books. This will output the SID of all those students who have issued stationery but not books. I hope you got the idea. Now, the level of question will obviously increase and you may get confused what will be the output. So, to get the precise output without confusion, the technique is make Venn diagram and mark the areas. Suppose we have 3 tables, student, book and stationery. This will represent the book, this will represent the stationery and rest the student, which means student contain all this. Obviously, we are talking about SID here. So, the student will have SID of both book and stationery. Okay. Book will have SID of all those students who have issued book, and stationery will have SID of all those students who have issued stationery. Now, there may be students who have issued both book and stationery, which will be represented by 3. There may be students who have issued just book and no stationery, which means this part, only book part. And there may be students who have issued just stationery but not books, will be represented by this part. See this. SID of book minus SID of stationery. SID of book is 2, 3. SID of stationery is 3, 4. 2, 3 minus 3, 4. Remove all the elements of B from A, which means 3 will be removed, 2 will be as the output. Okay. So 2 represent book minus stationery, which means this part. Similarly, 4 will represent this part, stationery minus book. Now, student minus book minus stationery. Book minus stationery was 2. Student was 1, 2, 3, 4. This will give all those student ID who have issued stationery but not books. And they have issued both. So this is a kind of complex language. Pi of SID student minus SID of book minus SID of stationery. This will represent all those students who have issued book but not stationery. And that part we are subtracting from the student, which means we are subtracting this part from the student. So what this relation is giving us, all those students except those who have issued just book. Are you getting the idea? All those students except those who have issued just book. This will be represented by 1, 3, 4, 1, 3, 4. Pi of SID of student minus book and then minus of stationery. This will be represented by 1, 2, 3, 4. Book will be represented by 2 and 3. So this will output 2 and 3 will be removed, 1, 4. Now 1, 4 minus pi of stationery, which is 3, 4. 1, 4 minus 3, 4. 4 will be removed, just 1. All those students who have issued neither book nor stationery. Okay. Pi of SID minus SID of book minus SID from stationery. Book minus stationery. This is like this, A minus B. Do you recall this formula? A minus B. This is the formula of intersection, which means we have now derived intersection with the help of set difference. That's why we have called intersection as the derived operator. Okay, are you getting the point? A minus B equal to intersection B. That's why we have called intersection derived operator, because we have derived this with the help of set difference. Think about this. Book intersection stationery. What will be the area? The 3. Which means all those students who have issued book and stationery. Now let's see whether we are getting the same answer from this. Book was 2, 3. Stationery was 3, 4. So 2, 3 minus 3, 4. Remove 3. Answer will be 2. Now 2, 3 minus 2. Remove 2. Answer is 3. Which we have initially got. Okay. SID of book minus stationery minus book. This is like A minus B minus A. A minus B minus A. Now think about this. First solve this. Remove all the elements of A from B. Now B will contain only those elements which are not present in A. let me repeat, B minus A will give all those elements of B which are not present in A. Now B have contained all those elements which are not present in A. If I subtract A minus B, this will contain all distinct element, this will contain all distinct element, and they have nothing in common, so this will represent just A only, which means this part can be ignored. Let me repeat. This will give me all those students who have issued stationery but not books. And this will give me the IDs of all those students who have issued books. So this will give me book minus all those students who have issued just stationery, which means this minus this. Let me repeat. This minus this. So it will output just this. I hope you have got the idea. SID of book minus SID of stationery union, SID of stationery minus SID of book. Just you can solve this. 2, 4 will be the answer. This part and this part. Okay. Now we will learn about Cartesian product. We have already discussed what is the meaning of Cartesian product. Cartesian product will give you mathematically all possible tuple combination. Whether in real life that makes sense or not, but mathematically all possible tuple combinations will be given as output. See here, A1, A2, B1. A1, A2 will be combined with 7 and 8. 3, 4 will be combined with 7 and 8. 5, 6 will be combined with 7 and 8. So these are the all possible combination can be made from these two tables. Similarly here, let's say A has 1, 2, B has 3, 4. So 1 will be matched with 3 and 4. 2 will be matched with 3 and 4. So 1, 3, 1, 4, 2, 3, 2, 4. All possible tuple combinations. Clearly seen, the degree of R1 plus degree of R2 will be the degree of R1 cross R2. The cardinality was 3. Here the cardinality was 2. 3, 3 into 2 equals to 6. The cardinality of R1 cross R2. It can be obviously seen. Okay. Now see here. Let's say we have a relation with a column name A, B, C, and another relation with a column name C and D. So when we will take the Cartesian product, the columns are put side to side like A1, A2 and B1. Suppose the column has name A1, B1 and C1. Here also the column has C1 and D1. So these columns will be in the same table A, B, C and C, D. This will be the table structure. But you know that the two column name cannot be same. That's why we use another term which is known as qualifier. Qualifier segregate the similar name columns. Like this C will be represented as A dot C, which means this is the C which belong to A. And for this C we represent like B dot C, which means this is the C which belong to B. Now the table names will be, or the column name will be A, B, A dot C, B dot C and D. I hope you got the idea. Now let's see the use case of Cartesian product. We have a table name student and book, where student have student ID and student name, book have book ID, the title and student ID, which will act as the foreign key to this primary key. Okay. Now the question is, find name of all those students who have issued at least one book. Now we are not asked with the student ID, we are asked with the student name. We can easily get the ID through though, but not the names. For names we have to look at the different table. So when we have to reference to the different table or we have to use the different table, then we use the Cartesian product. Student Cartesian product book. This will give me all possible combination. Different combinations will be given, but out of those combinations only few will be valid and the rest of them will be invalid. Why? See this. When you will take the Cartesian product of these two tables, it will give you S101A, B101X, S102. Do you think it has some meaning? Student ID S101, S name A, book ID 101, title X, book ID, book.sid S102. See, S101, S102. What is the meaning of this? Book 101 is given to S101 or it is given to S102. What is this? This doesn't make any sense. Then what will we do? We will ensure that these two are same. In that case, I can surely say that book 101 is allotted to student S101. We have got a kind of trick to identify which tuple is valid and which is not. So S101 doesn't have the book 101, but this gave a different idea. So to check whether the tuple is valid or not, just check if student ID student.sid equals to book.sid. If I'm getting the same student ID at both the side, which means it is a valid tuple. So to get these tuples, we can use a condition student.sid equals to book.sid. Now this will give me the valid tuples after the Cartesian product. So this will give me a table. Now we have got a table of all the valid tuples, but what we want the name of all the student. So we will just extract the S name from that table. From this table, I will extract the S name. So copied here, phi of S name. This will give me the name of all those students who have issued at least one book. Projection operator will automatically remove duplicacy. I hope the point is clear. Let me repeat. With the help of Cartesian product, we kinda join two tables. And after applying a certain condition, we can identify all the invalid tuples. And the remaining valid tuples will form a table. And from that table, whichever column or whichever operation you want to perform in that table, you can. Okay, let me give you an additional information. You can rename a table also. If you write like this, rename operator and write any name here, let's say A. Now this table will be A. So you can directly write pi S name A. Let me repeat. After the Cartesian product, you have identified valid tuples. Now this will give me a table of all the valid tuples. I can rename that table also with the help of rename operator, which is like shown with row symbol. And then you can name the table also. Let's say I want to rename the table as A. So this table will be named as A. Now A will contain all those valid tuples after the Cartesian product. Now I can just extract name directly from A. This will be our final answer. Okay. Now we will see a series of questions which will give you a solid understanding. Okay. Let's start. We have book ID, title, year of the publication, user, card number, name, city, borrow. We have borrow or the book ID, card number, and the date of issue. Supplier, we have book ID, S name, price, and date of supplier. So we have 4 tables with us. Now we will see different questions and how we will get the answer of those questions. Find title of all the books supplied by Ilya Topuria. So what will we do? Title of the book is we can get with the help of book table. I have told you step number 1 was to identify the table. Identify the table now. Title of the book. You can get the title from here. Here is the name. You can get the name from the supplier. S.name. So we will require two tables, the book and the supplier. So the book and the supplier. Now we want the title of all the books supplied by S name. We need to do the Cartesian product of both these book and supplier tables. And then how we identify the valid tuples with the help of this BID. If the BID matches at the both sides, which means we can say this is a valid tuple. So book.bid equals to supplier.bid, book into supplier. This have given us all the valid tuple. Now I want to filter based on the supplier name. So I will write the name s.name equals to Ilya. And then the same condition or the same table was copied here. Now this will give me all the books, all the tuples which were supplied by Ilya. But what I want just the title of the books. So I will apply the projection operator here. This will give me the answer. Now I told you do not have to use 2 times the selection operator. You can just use AND operator to simplify things. So you can write, I want title from this table. Which table? Cartesian product of book and supplier, in which book ID equals to supplier ID. This will give me now the valid tuples, and the condition is the name should be Ilya. and you will get all those titles. Find book ID of all those books issued to Pooja Tomar. Find book ID of all those books issued to Pooja Tomar. Now, identify the tables. Book ID, I want book ID. So where can I have book ID? From book and from the supplier and from the borrow also. So I will require just user and the borrow. Here I have book ID and here I have name. But see this. I'll just require user and the borrow table. Is there any attribute common? Yes, card number is common. So what I will do to identify the valid tuples, see if the card number from user and the card number from borrow is same at both the side. If they are same, then I can identify the valid tuples easily. Identify the tables, user and borrow. Cartesian product, filter valid tuples. So these are the 4 steps you have to apply. First, identify the tables. You have identified the tables as user and borrow. Second, apply Cartesian product, filter valid tuples with the help of this user.card number equals to borrow.card number. Then filter based on the condition. What is the condition? The name is Tomar. And then apply projection for asked attribute. What is the asked attribute? We need book ID of all those books. So I will need book ID. So the book ID is projected. Let me repeat. Identify the tables, user and borrow. Apply Cartesian product. And then filter the valid tuples based on this condition. Filter based on condition. Now the condition was that name should be Tomar. And then apply projection for asked attribute. Okay. Find title of all the books issued under the card number C101. Now card number is present. What will I do? Card number. So card number is present here and here also. And book ID is present here, here and here. The first step was to select the tables. I will just require books and the borrow table because I want title of all the books. Title is present in books. Issued under card number 101. So I have card number attribute in the borrow table also. So what I will do? Which is the common attribute? The book ID. In the borrow and books, which is the common attribute? See, the borrow and book have common attribute as book ID. So I will write as borrow.book ID should be equals to book.book ID. This will filter out the valid tuples and then apply the condition C101. The card number should be 101. And then project the titles from this table. Easy question. Find title of all the books issued under the name or issued to Max Holloway. What I will do? Books, Holloway, username. From user and supplier, we have name at 2 tables, user and supplier, but there is no meaning to use supplier here. So we will use 2 tables, book and user. See the tables, book and user. But when you do the Cartesian product, how are you going to identify the valid tuples? They do not have any common attribute. What is the common attribute? Title or name? No. Title and name is not the common attribute. Year and city? No. So book and user doesn't have a common attribute. What will we do now? We will take the help from some another table. What will we do? We will take the Cartesian product of these 3 tables. And then to identify the valid tuples, you can do like this. Book.bid should be equals to borrow.bid and user.card number equals to borrow.card number. You can do like this. Or first, do the Cartesian product between book and borrow. And then match the book ID from both the tables. And then when you will get the table into the output, you can match the card number after doing the Cartesian product with the user. So either you can do like this, book cross borrow, match the BID, and then let's say this table is A, and then do like this, user A and match the card number. Or you can directly do like this, book cross user cross borrow, and then apply condition, book ID should be same and card number should be same. This will result into the valid tuples. See here, book and user was needed but doesn't have any common attribute. We will need an intermediate relation. We will use borrow. So we'll use like this, user, borrow, book, and then book.bid it should be equal to borrow.bid, user.card number should be equals to borrow.card number, and we will also apply the condition based on that filtering will be happen. Name should be equals to Holloway. Now what I want the title, so project the title from this table. See that this is not an efficient approach. Let's say user have 10 tuples, borrow have 20 tuples, and book have 10 tuples. So this will result in 2000 tuples, and based on 2000 tuples, you have to do the filtering. This is not an efficient manner. What will we do first? We will first multiply user and borrow, or you can also do like this, user or borrow or book. You can also multiply borrow or book first and then multiply with user, or you can do like this, user and borrow and then multiply with the book. Both these are optimized approach. What we want, before doing the Cartesian product, minimize the tuples as much as possible. Let me repeat, before doing the Cartesian product, minimize the tuple as much as possible. This will result in less number of multiplication. So this will result in less number of tuples. So to search, we will have to access less number of tuples. So this will result in an efficient approach. User cross borrow, user.card number equals to borrow.card number, and we have applied here only the name equals to Holloway, and then extract the book ID from here. Now you only contain the book ID. This is the table, book ID of all those books which are issued to Holloway. And now books.book ID equals to a.book ID. We have represented this table as A. So books.bid equals to a.bid, and then extract the title. Got the idea? One more point I want to make, that for string literal we use single quote only. We do not use double quotes. We use double quote for column names like here title or the book ID. But to represent the string literal, we use the single quote only. The name of all those suppliers who have supplied at least one book issued to Dimitri Bihul. Again, we will require three tables: supplier, borrow, and user. To identify the valid tuples, we will equate the book ID from supplier and borrow table, the card number from user and borrow table, and what is the additional condition? The name should be Dimitri Bihul. And what I want as the output, the name of all those suppliers. So I will project that as name attribute. Okay. Find the name of all those users who live in same city as Nishant Dev. The problem is we do not know the city where Nishant Dev lives. If we have known the city, let's say he lives in the city Bikaner. By the way, I also live in Bikaner, and it's a beautiful city famous for its fort, museums, old architectural style buildings, and its cuisine, the food. So if you ever got the opportunity to visit Rajasthan, India, you should come to Bikaner and let me know. We'll connect and have fun. I will become your personal guide. See this. You can go to the image section and see the different images. Okay, let's come back to the topic. If we have known the city in which Nishant lives, we could have directly done like this. City equals to Bikaner, user, and we'll project the name of all those users who live in the city Bikaner. But we do not know where Nishant Dev lives. We have to first find where he lives. What we will do? Name equals to Nishant Dev, user, and we will project the city. This will give me output like this. City equals to Bikaner. Now we have known that Nishant Dev lives in the city Bikaner. How are we going to find the name of all those users who live in this particular city? Let's rename this table as A with the help of rename operator. And then take Cartesian product, and now apply the condition that A.city, which means Bikaner, should be equal to user.city. Bikaner, this will represent the Bikaner, and equals to user.city. So whichever user who live in city Bikaner will be, that tuple will be selected. And name should not be equal to Nishant Dev. Why? Because it will be implicitly present there only. We want the name of all those users who live in the same city as Nishant Dev. So the output, we do not want again the name of Nishant Dev come in the output. That's why we have removed the tuple where name equals to Nishant Dev. Now we have got a relation of all those users who live in the same city as Nishant Dev lives. But what I want just their name, so we'll project the name. Another point, that not equal to can also be represented like this. There is another way to solve this problem, but you will not get the idea directly by reading this. That's why I have taken some of the entries in the table. Let's say the name is ABC. We want the name of all those users who live in the same city where ABC lives. What I will do now, listen carefully. I will just copy the table with a different name. Let's say this table is now U1 and I will copy the table with different name, let's say U2. Now what I will do, take the Cartesian product between U1 and U2. I have renamed the table user as U1 and U2 and took the Cartesian product between U1 and U2. Now I want the name of all those users who live in the same city where ABC live. So I will first specifically specify the condition that U1.name should be the ABC. So all these tuples, all these below tuples will be discarded. Took the Cartesian product, it specified the name that I want to compare for. This U1.name should be ABC. And then compare the city, that the city of U1 and U2 should be same. This tuple was eliminated. Now the name should not be equals to ABC. That's why the first tuple was also eliminated and we have got this tuple. But what we want just the name of all those users. So we have projected u2.name. Okay. Now moving to the next question. Find the title of all those books supplied by Dustin. We have already done such kind of questions, but in a non-efficient manner. With Cartesian product supplier, where book.bid equal to supply.bid, where name is Dustin, and project the title. It was an easy question, but this is not an efficient manner. Before Cartesian product, try to minimize the number of tuples in your tables so that in the output you will get less number of tuples, and for applying the condition or searching will become easier for you. Efficient manner. Okay, so what we will do, instead of multiplying supply directly to the book, we will first apply the condition that name of the supplier should be Dustin only. Now we have limit the number of tuples in the supplier, and now we will multiply this to book. So S will be the renamed table where supplier name is only Dustin. So we will now take the Cartesian product between S and book, and we will equate S.bid equal to book.bid and output the title. Find title of all the books issued under card 101. What is the motto? Before Cartesian product, try to minimize the number of tables. So we will minimize, like, first the card number should be 101 only. So borrow card number should be 101. Let's rename this table as B. Now multiply with the book, and now equate the book ID and project the title. Find title of all the books issued to Tony. Here we require three relations. What we will do, similar manner, first set the name. Let's say the name is ABC or Tony, whatever the name is. Now we have limited the name as Tony only, and then apply, or we have to rename first. So A is the table which have only name as Tony, and then apply Cartesian product. Identify the valid tuples A.card number equal to borrow.card number, and then rename again, let's say B, and then apply Cartesian product again, and then identify the valid tuples, project the titles. Okay, the more you practice, the better you get at it. Title of all the books issued to Tony. User, borrow, book. I want to first limit the user tuples by restricting the name to be Tony only, and rename that table, let's say A, and then I multiplied with the borrow, identify the valid tuples, and then renamed it as B, multiplied to book, identified the valid tuples, and then projected the title from that. In this lecture, we will learn to solve these type of queries of finding smallest and the largest. Let's learn with the help of an example. Find price of the highest price book supplied by Mehrab. To solve such question, you have to follow a pattern. Okay, so focus and try to establish a pattern here. We were asked to find the price of the highest price book supplied by Mehrab. So firstly, list the price of all books supplied by Mehrab. So we will apply the condition S name equals to Mehrab on relation supplier, and then we'll project the price. Now we have got a table which has the list of all the books price supplied by Mehrab. The price of all books supplied by Mehrab. So we have $2, $3, $4, and $5. Now rename this table into A and B, which means duplicate and then rename. So we have duplicate this table and then rename it to B. Now we have two tables, A and B. Okay, we have two similar tables, A and B. Apply cross product on those two tables, which means 2 will be matched with 2, 3, 4, 5. 3 will be matched with 2, 3, 4, 5, and then similar 4 and 5. Okay. Now apply a condition that A dot price should be greater than B dot price. As soon as I applied this condition that A dot price should be greater than B dot price, which means like this, then you can notice that 2 will not match with any of the entry of B. These all entries are not allowed because I wanted entries where A dot price should be greater than B dot price. So all these entries will not be allowed. Similarly, these entries will also not be allowed because I wanted A dot price should be greater than B dot price. So I can say that the minimum entry of A will not match and the maximum entry of B will not match. So we will get a table like this. So this was the cross product result. And then as we applied the condition, we will get a table like this. 3, 4, 5, 4, 5, 5. You can see 2 is missing here. And you can see 5 is missing here. Which means the minimum value is missing here and the maximum value is missing here. Have you got till now? What we have done? We have list all the prices of the books supplied by Mera. Okay. And then we have renamed the table into A and B, applied cross product and set the condition A dot price should be greater than B dot price. Now what we are doing? We have noticed that the minimum value is missing here and the maximum value is missing here. So whichever part you are asked, for example, you are asked here the highest, and you can see that the maximum value is missing here. You extract that column. Let me repeat. If you are asked maximum, then you extract that column where maximum price is missing. If you are asked with minimum, then you extract that column where minimum price is missing. So you have extracted B dot price from here. Now what are you doing? You are subtracting total minus B dot price. B dot price contain all the values except the maximum. And total will contain all the values. So total minus, it's like total minus maximum. So you will get the maximum. Are you getting the point? This is the total list. Prices of all the books supplied by Mera. And this is the total list except the maximum priced book supplied by Mera. So you subtract total minus B dot price. In B dot price, the maximum value is missing and rest all the values were present. So from total, rest all the values will be subtracted except the missing, which is the maximum. So you will get the maximum value as the output. So this will give you price of the highest price book supplied by Mera. This is the maximum. Now if someone asked you the minimum, then what you have done? You would have extracted A dot price where the minimum value is missing. So if you do like this, total minus A dot price, where A dot price is total minus minimum, total cancelled, minimum will be the output. Okay, so this is the final answer. Total minus, rename the table A and B, apply the cross product, apply the condition, extract whichever part you want here. We wanted the maximum, so we have extracted that column where maximum value is absent, and then we subtracted that from total, and there we got the value. See here, total was this. This relation resulted into this table, 2, 3, 4, 5 minus 2, 3, 4. What I have told you here, all except the maximum, all except the maximum. So if you subtract 2, 3, 4, 5 minus 2, 3, 4, you will get the 5, which is the maximum. For minimum, you would have extracted A dot price. 2, 3, 4, 5 minus 3, 4, 5, you will get the 2, which means this will contain all except minimum. This will contain all, you will get the minimum. Okay. Now let's see an inefficient method also, which is instead of applying Cartesian product specifically, you have applied on the whole relation. That is, you have applied on the supplier directly. You have renamed the table supplier into A and B, applied the cross product, and then set the relation that A dot name should be equal to mera, B dot name should be equal to mera, and then A dot price should be greater than B dot price. This is an inefficient method. Suppose we have 100 tuples in the supplier, here also 100 tuples, we will get 10,000 tuples after cross product. And then on that you have to search for A dot name equals to mera, and then B dot name equals to mera, and then you have to apply the condition A dot price should be greater than B dot price on those 10,000 tuples. Okay, we have discussed this part, so we will not focus much here. I want to focus on this point. Do not try to remember that whenever A dot price is greater than B dot price, then extract B dot price for maximum. No. You have to think, you have to understand that why we are subtracting B dot price here, why we have subtracted A dot price here. Okay, you have to kind of remember this formula: total minus whichever part you want to get. If you want to get the minimum, write minimum here. If you want to get maximum, write maximum here. So whichever part you were asked, for example, you were asked the maximum part, then extract that column in which the maximum value is missing, and then when you will subtract that column from total, you will get the maximum value. Okay. So this is what I have discussed here. Now let's see some more queries on Cartesian product. This was the schema on which we were discussing. Now find the name of all those suppliers who have supplied books issued to DC. Let me repeat again. Find the name of all those suppliers who have supplied book issued to DC. So DC is the user here. All those suppliers, we want the name. So we want S name, user. What will be the connecting attribute? You will get the user from here, name from the user, and supplier name from here. There is no connecting attribute, so we have to find one. We will find the book ID. So book ID will act as the connecting attribute. So what we will do? User cross borrow cross supplier, where user.card number equals to borrow.card number, supplier.book ID equals to borrow.book ID, and name equal to DC. We have already done such type of queries. I have taken this again for the sake of revision. Okay. What we were doing here, we want the name of all those suppliers who have supplied book issued to DC. DC is the name we will get from the user table. We will get the name of supplier from S name, but we do not have a connecting attribute. That's why we have included the relation borrow here. So we'll first set up the valid tuples between them, which means user.card number equals to borrow.card number, and then set up the valid tuple between them. Supplier.book ID equals to borrow.book ID, and then apply the condition, which is name should be equals to DC, and then project the name. So you will get the, I think we should have projected S name. We will get the name of all those suppliers who have supplied book issued to DC. Okay. The efficient method would be, first do like this: user cross borrow. You apply the condition early so that you will have less number of tuples before doing the Cartesian product. You have applied name equals to DC, and then extracted the book ID. Then extracted the book ID from book ID and S name from supplier. Now you have tables of book ID and S name. You have a common attribute. Equate that common attribute and extract the S name. You can also do like this. This is a more efficient way. So how you will find the efficient and inefficient way? Before doing the Cartesian product, try to find a way to minimize the number of tuples. Okay, so we have applied the condition, which means all those tuples will be discarded whose name is not DC. And then we applied the cross product. Find the name of all those suppliers who have supplied books of the same title as issued to Mighty Mouse. The name of all those suppliers. So we want S name in the end. We want to extract S name in the end. Who have supplied books of the same title, which means title we want. We have to equate the title, which means book table is involved. Issued to Mighty Mouse, username, user table is involved. So you have to think of a roadmap first, what you are going to do. books of the same title, which means you have to equate the title, and then extract the name of supplier, which means extract the S name. So what you have to do, make two tables. The first one is list the title of all the books which is issued to user Mighty Mouse, and then title of all those books supplied by all the suppliers. Title of books issued to Mighty Mouse, title of books supplied by the suppliers, and then equate the title, extract the S name. User connecting attribute BID from borrow, and then title from book, name, BID, and then title. User.card number equals to borrow.card number, and then borrow.book ID equals to book.book ID, and then apply the condition name equals to Mighty Mouse, extract the title. From this, you have got a table which contain the title of all the books issued to Mighty Mouse. So this table will look like this, title. Okay. And then title of all the books supplied by all the suppliers. Book cross supplier, book.book ID equals to supplier.book ID, extract the title and S name. Why S name? Because we want to, after the Cartesian product, we want to extract this S name. Why the title? Because we want to equate the title. So what we will do, let's rename this as A, this as B, apply cross product, equate the title, extract the S name. Let me repeat what we wanted. We wanted the name of all those suppliers, which means S name, who have supplied books of the same title, which means we have to equate the title of the books issued to Mighty Mouse to the title of the books supplied by the suppliers. Title of the books issued to Mighty Mouse, equate the title to the title of the books supplied by the suppliers. After equating title, extract the S name. This we have done. Find the name of all those users who have issued books on the same date as issued by borrower Eddie Alvarez. We have to equate the date of issue. What we will do, extract the date of issue from book cross user, where borrow.card number, find the name of all those users who have issued books on the same date as issued by borrower Eddie Alvarez. We have to equate the date of issue. Name of all those users. अरे यार दिमाग खराब हो गया यार, गैप नहीं आ सकता. Find the name of all those users who have issued books on the same date as issued by borrower Eddie Alvarez. On the same date, which means we have to equate the date of issue. So what we will do first, list all the dates on which Eddie Alvarez has issued books. So what we will do, borrow cross user, name equals to Eddie Alvarez, and then to set up the valid tuples, equate the common attribute which is card number. So borrow.card number equals to user.card number, and then extract the date of issue. From this, we have got all the dates on which Eddie Alvarez has issued a book. Now, all those users who have issued the books, borrow cross user, borrow.card number equals to user.card number, date of issue and name. This will give me a list of all the names and all the dates. Now what we will do, apply the cross product, equate the date of issue from table A and table B, and then extract the name. Let me repeat, name of all those users who have issued books. This table will give me the name and the date, and then date of issue of Eddie Alvarez. This table will give me, equate the date of issue, extract the name. Now the question is, can you read the queries from the relational algebra? Suppose we are given with supplier table, rename it to A and B, apply the cross product, and then S1.price is greater than S2.price, S2.name equals to Anshul Jubilee, and then we have projected S1.name. By the way, people are hating Anshul Jubilee nowadays because in his 2 continuous UFC fight, he has faced defeat. See, the people do not understand that apart from hard work, luck also plays an important role. The way he fell down, referee thought it was a knockout and he did a kind of early stoppage, but the people have not stepped into a cage ever. and those people are hating Anshul Jubli, they do not have a right. The man has reached to the UFC. This is an important thing. Yeah, he deserves support and a positive criticism, but the way people are behaving with him in the Instagram is not quite right. Okay, let's come back to the point. Can you read the queries? We are given with two tables, A and B. Supplier renamed, and then we have applied cross product. S1.price is greater than S2.price and S2.name equals to Anshul Jubli. And then S1.name is projected. This query kind of seems complex, and whenever you feel that way, take the instances. Take a table, fill any sample values, apply this query on that table, and then see the result. And then try to read what this result is trying to say. This is what we will do here. Let me tell you first the answer. The answer is project the name of all those suppliers who have supplied at least one book. This projection operator tells us at least part. Name of all those suppliers who have supplied at least one book with a price greater than the least price book supplied by Anshul Jubli. If you are a pro, you can directly read, but to understand this properly, we will take an example, and with the help of that example, we will try to understand. We have taken this as the supplier table. Now, it's your work to apply that query on this table. Cross product, and then S1.price should be greater than S2.price. Remove all those tables who are not following this condition, and then also set S2.name equals to AJ. The final table which you will get will be this. Now try to read what this table want to say. S1.name. This will contain all those names who has supplied book with a price higher than 100. See this. 200 is greater than 100. 150 is greater than 100. 260 is greater than 200. 260 is greater than 100. And these all books are supplied by whom? Anshul Jubli. That's what we have set here. S2.name should be Anshul Jubli. So S1.name will contain all those suppliers who have supplied at least one book. At least one. Why? Because of this projection operator, we will remove the duplicacy. At least one book with a price higher than the least price book, which is 100, supplied by Anshul Jubli. So include the name of all those suppliers who have supplied books with a price higher than 100, AJ, X, and Y. So name of all those suppliers who have supplied at least one book with a price higher than the least price book supplied by Anshul. So you may not get these type of queries directly. Then what you have to do? Take the sample table, apply the query, and read the table. This is what you can do. Now, what would have happened if we have done like this? S2.price is greater than S1.price. See this, we have modified our original query and we are projecting S1.name only. All those suppliers who have supplied book with a price lesser than the highest price book supplied by Anshul Jubli. Again, you can do the same. Take the supplier table, apply all these conditions, and then try to read this, what this table is saying. All those suppliers who have supplied book with a price lesser than the highest price book. What is the highest price book supplied by Anshul? Let's say 150 is the highest price book. So all those suppliers who have supplied book with a price lesser than, that's why AJ, X, and Y is included in this table, and we are projecting S1.name only. You cannot directly understand just by looking at this video. You have to take the pen and copy and then try to solve by your own. Take the sample table, fill values by your own, and then apply that query on that table, and then try to read what the answer is saying. Okay. And another important point, you do not have to remember like this, that if I apply this symbol, which means greater than the least, if I apply this symbol, which means lesser than the greatest, do not try to remember like this. Slightest change will confuse you. Try to understand. Okay. So what you have to learn from this, whenever you are given with a question where you have to read the query, or you are given with algebra and you have to give the English query, then take the sample table, apply that query on that table, and then try to read from the answer table what that answer table is saying to you. Now let's move to the intersection operator. Again, it's a kind of set operator. Union, intersection, set difference. All these operators, union compatibility is must. Okay. Compatibility is must. Intersection operator will only include the common tuples. And why we are saying that intersection operator is a derived operator? Because we can derive this operator with the help of fundamental operator, which is set difference. R1 minus R2 will give you R1 intersection R2. So with the help of set difference, you can get the intersection operator. There can be other way also with the help of union and set difference. The basic point was to prove that why this operator is said as derived operator. Now let's see with the help of example. Find name of all those students who have issued book as well as stationery, the most basic example. What we will do? First find the SID and then cross product with the student, find valid tuples and project the names. SID of book, SID of stationery, take the intersection. This will include the student ID of all those students who have issued book as well as stationery. And then let's say we rename this table as ID. Do the cross product of ID and student and then equate the student ID, project the name. The degree of intersection is same as the degree of relation on which intersection is performed. So R1 degree equals to R2 degree equals to R1 intersection R2 degree. What about cardinality? Let's say we do not have any matching tuple or any common tuple, then an empty relation will be in the output. The maximum cardinality of intersection possible will be minimum of R1, R2. If you are not getting this, let's say R1 has 3 tuples, R2 has 2 tuples. All the tuples of R2 is present in R1. So what will be the output? R2 itself. So I will say minimum of R1, R2. In the next lecture, we will learn about joins. Let's learn about joins. We have inner join, theta join, equi-join, natural join, semi-join, and anti-join. While in outer join, we have left, right, and full outer join. For theta join, Cartesian product with a condition. This is the symbol, and theta describes the condition. For example, R1 join R2, where condition is C greater than D. So you have to do the Cartesian product and then apply the condition. This is similar as Cartesian product with a condition. See here, R1 Cartesian product R2 with a condition C greater than D. 4, 5, 6 will be matched with 4, 5, 8, and then 7, 8, 9 will be matched with all 3. You will get this. Here you can see that C is greater than D in all the cases. So theta join is nothing but Cartesian product with a condition. Equi-join is the special case of theta join where condition can be equality only. You apply like this, R1 cross R2, where equality condition is only present. C equal to D. So 4, 5, 6, 6, 7, 2, C equal to D, which means this tuple will be present only. C equals to D. Equi-join is the special condition of theta join where only equality condition exists. We will talk about degree and cardinality now. For degree, it will behave same as the Cartesian product. R1 plus R2 equals to R1 theta join R2, similar R1 equi-join R2. For cardinality, if no tuple satisfy the condition, then 0. If no tuple satisfy the equality condition, then 0. And for maximum, it will behave like Cartesian product. For natural join, common attributes, if they present, if there are any common attribute, then they will be equated and they will come just once in the table. For example, is there any common attribute? Yes, C is the common attribute. So we will not write like this, R1.C, R2.C. We will just mention C once. Okay, and only that tuple will be included in which the C is equal, 6, 6. So that tuple will be included. What if there is no common attribute? Then it will simply act as the Cartesian product. What if I have all the common attributes A, B, C, A, B, C? Then it will act as the intersection. For example, A, B, C, A, B, C. And here we have 4, 5, and 6. So only this tuple will be included. If all the attributes are common, it will act as intersection. If there is no common attribute, it will act as Cartesian product. If we have multiple common attribute, then for example BC is common. So for all that common attribute, we will see the corresponding values 2, 3, 2, 3. This will be included. 8, 9, 8, 9. This will be included. So two tuples will be present in the output. And those tuples which are not present in the output, or those tuples or those rows which fail to find a matching partner or fail to participate in a natural join, they are known as dangling tuples. If all the attributes are same, it will act as intersection. If there is no common attribute, it will act as Cartesian product. R1 degree plus R2 degree is greater than R1 natural join R2 degree. Why? Because common attribute will come only once. Minus M for number of common attributes. For example, A, B, C, C, D, E. So C will present only once. So A, B, C, D, E, 5, and here 3 plus 3. That's why greater than. And if all the attributes are distinct, for example, A, B, C, and then E, F, G. In that case, here A, B, C, E, F, G. So 6 will come. So say 6 equals to 6. Are you getting the point? Why it is different from the relation of theta join and equi-join, where we have equated this. We will not equate. Why? Because number of common attribute, if present, they will come only once. For cardinality, the minimum can be 0. When attribute was common but tuples were not matching. See this example. Here, if I have written 11, then the attribute was common. C is common attribute, but there is no matching tuples. 3, 6, 9, and then I have written here 11. So 11, 4, 7. There is no matching tuple. In that case, the output will have empty relation. So 0 will come when attribute was common, but tuples were not matching. And when natural join act as Cartesian product, in that case, we will receive the maximum cardinality. Now, the question is, can natural join act as Cartesian product even if we have a common attribute and instance? We have discussed that natural join will act as a Cartesian product when there is no common attribute. But will it act as a Cartesian product even if we have a common attribute and instance? Yes, it can act. See here, A, B, C, C, D, E, attribute is common, but all the values are same. All the values are same. So 3 will be matched with all these 3. This 3 will be matched with all these 3. And this 3 will be matched with all these 3. So it will act similar to Cartesian product. Okay. So natural join can be written like this: A, B, C, C, D, E, where equal or common attribute will be equated. R1 dot C equal to R2 dot C with Cartesian product. Common attribute will come only once. A, B, R1 dot C, let's say R1 dot C, and then D. Equi-join can be expressed with the help of selection and Cartesian product. Same can be said with theta join, where condition is equality. And for natural join, we will also include the projection along with the Cartesian and selection. Now, before solving the queries, let's revise the inner join part again. Inner join, we have discussed all these 3 portions: theta join, equi-join, and natural join. In theta join, it's similar to Cartesian product with a condition. In equi-join, when the condition becomes equality, it acts as an equi-join. And in natural join, if we have a common attribute, then only include those tuples in which common attribute has the same value, and the common attribute will come only once in the table. Now, let's discuss the queries. The same schema. Find title of all the books supplied by Sarukian, Arman Sarukian. So we can do like this: books, natural join, supplier, where name is Sarukian, and then project the title. It's simple. Now, books and supplier have book ID common. So natural join will automatically tackle that. What is natural join? Common attribute are equated. So we have a common attribute of book ID. So books dot book ID equals to supplier dot book ID. This is implicit here. And then you have to just apply the condition that the name should be Sarukian and then project the title. Find book ID of all those books issued to Angad. Again, card number will be automatically matched between user and borrow. So you have to find the book ID of all those books issued to Angad. So user, natural join, borrow. the condition that user.card number should be equals to borrow.card number will be automatically matched. And then you have to apply the condition that name should be Angad and then project the book ID. Easy. Find title of all the books issued to Ziri. Now, title, user, and borrow. So we would have just wanted book and user, but there is no common attribute between them. So we have to include an intermediate relation. So we will include borrow. Now you have to write just this, and natural join will automatically tackle that between user and borrow, card number should be matched, and then with the final output, match the book ID. One more point, that natural join is commutative and associative. When you do like that, you have to just apply the condition and then project whatever you want. We want title, so we have projected the title. Condition was that name should be Ziri, so we have written the name Ziri. Let me repeat. In natural join, common attribute will be automatically equated. Doing when we have not learned about the natural join, we were doing the Cartesian product and then equating the common attribute so that we will find the valid tuples. Now the equating part will be automatically tackled. You have to just mention this: books and supplier, user and borrow, book, user, borrow. Natural join will automatically tackle the equating part. So natural join will automatically give you the meaningful tuples only. Then you have to just apply the condition and then project the title. Find name of all those suppliers who have issued book to Easy. So user, borrow, supplier, apply the condition, project the name. See, so simple now. With the help of natural join, we can see that query looks so simple now. We have user, borrow, and supplier. Just include the relation which you want. Natural join will automatically tackle, and then write the condition and then project whatever you want. We want the name of supplier, we will project the as name. But again, Cartesian product is inevitable, and if you are using these directly, then it will be inefficient. So firstly, I would recommend you to minimize the number of tuples before hopping onto the Cartesian product. So we will first apply the condition that the name should be Easy on user, and then we go ahead like user and then borrow, and then over here we have applied the projection, and then we have done the natural join with supplier, and then we have projected the as name. Find the name of all those suppliers who have supplied book of the same title as issued to Wonderboy Thompson. Find the name of all those suppliers, name of the suppliers, which means we want to extract the S name in the end, who have supplied books of the same title, which means we have to equate the title issued to Wonderboy Thompson's. Here is the name from user table. If we have not used join, then we have to first find the book ID of all those books issued to Wonderboy Thompson, and then from the book ID we have to find the title. Are you getting the point? Using borrow and user, we have find the book ID of all those books issued to Wonderboy Thompson, and with the help of book IDs we will find the title of all those books. Now I have a list of the title of the books issued to Wonderboy Thompson. I have the title of the books issued to Wonderboy Thompson, and I have to find another table in which I have title and the supplier name, title of all the books supplied by all the suppliers. Among these two tables we will perform the Cartesian product, and then we will equate the title, and then we will extract the S name. If you are not getting what I am saying, then pause the video and try to solve this first. When you will think, you will realize that we have to follow these steps. That firstly we have to find the book ID. After book ID we have to find the title of all those books issued to Wonderboy Thompson, and then we have to get the list of all the books supplied by all the suppliers. We have a title, all the books issued to the Wonderboy Thompson, title, and the supplier name of all the books supplied. We will do the cross product, equate the title, extract the as name. But if we are using natural join, the query will become so much simple. Book, natural join, borrow, natural join user, Just apply the condition that name should be Wonderboy Thompson and extract the title. This will directly give you the title of all those books issued to Wonderboy Thompson. No need to find the book ID first and then find the corresponding titles. You can directly find the title. So we have find the list of all the books issued to Wonderboy, and then we will find the supplier and the title using supplier, natural join book, S name and title. Now we will apply natural join again among these two. Title will be equated, S name will be extracted in the end. Okay. Next question. Find name of all those users who live in the same city as that of Rifleman Sanjay Kumar, Paramveer Chakra winner. Find name of all those users, name from users who live in the same city as that of Rifleman Sanjay Kumar. Okay. So what we will do first? We will include only those tuples in the table user which have a name of RSK. And then we will extract the city. From here we have got the city in which RSK lives. And now what we will do? We will remove the tuple in which the name is RSK. We will apply natural join and then we'll extract the name. This will give me the name of all those users who live in the same city as that of RSK. Let me repeat again what we are doing here. We are finding the city. Let's say RSK live in Bikaner. And then we will doing cross product with the table in which all those tuples are included except the name RSK, because we don't want the same name again in the output. We don't want another tuple with a name that Rifleman Sanjay Kumar is among those users who live in the same city as that of Rifleman Sanjay Kumar. That's why we have done the name should not be equal to RSK. And then we have applied natural join. We will extract the name. Okay. These type of query we have already done before. Find the name of all those borrowers who have issued book on the same date as issued by Major Shaitan Singh. Let me repeat. Name of all those borrowers. Name from user. Borrowers who have issued books on the same date. Date from DOI. Date of issue. As issued by again user name. So what we will do? Again simple. We will find the date of issue list of the books issued by Major Shaitan Singh. So from user and borrow, we will find the date of issue of all the books from the name Major Shaitan Singh. Now I have a list of the dates on which Major Shaitan Singh issued the books. Now what we will do? We will apply the natural join with which table? We do not want the same case from here, that I do not want the name of Major Shaitan Singh among the list of those borrowers who have issued books on the same date as issued by Major Shaitan Singh. That's why we have applied name should not be equals to Major Shaitan Singh. Natural join borrow, extract date of issue and name. So among this date of issue and name and date of issue again, date of issue name, date of issue, we will apply natural join, equate the date of issue and then extract the name. This is what we have doing before. See the pattern. Title, S name dot title, equate the title, extract S name. Here, date of issue name, date of issue, equate the date of issue, extract name. So I think this will be enough for understanding natural join. Now we will move to semi-join. Semi-join. Perform natural join but keep the attributes of left-hand side relation only. This is the symbol where only left-hand side relation attributes will be kept. For example, in natural join, what we do? We equate the common attribute values. So 3 will be equated, 6 will be equated. So we will include the tuple 1, 2, 3, 6, 9, 4, 5, 6, 7, 3. But we have to keep the attributes of left-hand side relation only. Right-hand side relation attribute will be deleted. So this will be our answer. If we reverse the case, it will become anti-join, in which we have to keep the attributes of right-hand side relation only. So there, the C, D, E attributes, which means 3, 6, 9 and 6, 7, 3 will be kept, and this A, B will be deleted. Let's see an example. Information of all the books which are issued. All the books which are issued. With the help of book table only, I cannot get that information. I have to include the borrow table, but I do not want the attributes of borrow table. I do not want card number and date of issue. If that is the case, it's a perfect time to apply either semi-join or anti-join. Whichever attribute you want, those attribute you keep and rest will be discarded. So if you apply like semi-join, you will write like this. And if you apply anti-join, you will write like this. While applying semi-join or anti-join, the common attribute will be matched. Now, what is the meaning of common attribute being matched? What is the meaning of BID being matched? It means that book has been issued. If BID is present at both these tables, at both these attributes, which means that book has been issued. So only those tuples should come in the output. So to apply this kind of scenario, semi-join or anti-join is the best case. Okay. Now we have discussed all those joins of inner join. The equi-join, theta join, natural join, semi-join and anti-join. Now we will move to the outer join, which include left, right and full. So before hopping on to outer join, let's again discuss the inner join so that no confusion remains. In theta join, it's nothing but the Cartesian product with a condition. Equi-join, the conditions become the equality condition. In natural join, the common attribute, if present, will be equated and only those tuples will come in the final output, and common attribute will appear once. In semi and anti-join, either left hand side or right hand side attribute will be kept after performing the natural join. So this was all about inner join. Now we will move to the outer join. Let's discuss outer join. We'll start with left outer join. In semi-join and anti-join, we have discussed about the attributes, that in semi-join keep the left hand side attributes after performing natural join. In anti-join, we discussed the same for right relation attributes. But in outer join, we are talking the same about tuples, not attributes. R1, R2. The symbol for left outer join is this. Perform natural join, but all the tuples from left relation must be included. What is natural join? Common attribute value should be matched. 3, 3, 6, 6. So I will include, and then include the tuples from left relation. 7, 8, 9 will directly come here, but there is no matching value, so I will keep null here. Okay. For right outer join, same case. 1, 2, 3, 6, 9, and then 4, 5, 6, 7, 3. These two tuples will come. Now all the tuples from right side relation must come. 3, 6, 9, 6, 7, 3 has already come. 4, 5, 2 was remaining, so I will include 4, 5, 2 here. And there is no matching value for left hand side relation, so I will keep null here. For here you must have guessed that both the relation tuples will be present. Write the common tuples first. 1, 2, 3, 6, 9 and 4, 5, 6, 7, 3. The tuples which have matched. Now keep the dangling tuples from the left here as it is, and write null for the right hand side column attributes, and the dangling tuple from here 4, 5, 2 will be present here, and for left hand side column attributes write null. So along with matching tuples, dangling tuples from both the relation will also be present. 7, 8, 9 null, null, and for 4, 5, 2 from right hand side will be here and null will be written here. Let's discuss about the cardinality of left, right and full outer join. For left outer join, R1 cardinality will be the minimum one, because all the tuples from left hand side relation are must. For right outer join, all the tuples from right hand side relation are must. So these are bound to come. And for maximum, you know that it will be maximum when the natural join act as a Cartesian product. If common attribute have same instances of 3, like 3, 3, 3 and 3, 3, 3. So this 3 will be matched with all these. So the maximum will be of Cartesian product, that is R1 into R2. And the minimum will be if left outer join then R1, if right outer join then R2. What about full outer join? In full outer join, R1 and R2, both the tuples from relation should come. So what is the problem with R1 plus R2? Why I have made a cross here? R1 plus R2 is not correct for the minimum cardinality. Why? Because if all the attributes are common, natural join will act as an intersection and dangling tuples will come then as it is. Like this, ABC, ABC, 1, 2, 4, 4, 5, 5, 7, 8, 9, 1, 2, 4, 7, 8, 9. In that case, 1, 2, 4 will come just once. So 1, 2, 4, and then 4, 5, 5, 7, 8, 9, and 7, 10, 12 will come. So in this case, 3 plus 2, and here it is just 4. So 3 plus 2 is 5, which is not equal to 4. That's why this is not right. Instead of writing addition, I should have written the union. And union automatically remove the duplicacy. That's why R1 union R2 will be the perfect choice. The minimum will be R1 union R2. In that case, do the R1 union R2 of this. This is 3 and this is 2, but I have a common. So that common part will be counted just once. So 3 plus 1 will be counted only. This is already counted. That's why R1 union R2 is the perfect. And for maximum, the Cartesian product. Let's discuss our final problem on joins. Employee ID and employee name, salary, employee ID and salary, list employee ID, name, salary of all the employees. So what I want, employee ID, name and salary. There may be employees which are present in employee table and not in salary table or vice versa. Is the question asking us to do natural join? No. We want employee ID, name and salary. In natural join, what is the problem? See here. For example, this is our table for employee ID, employee name. This is our table for employee ID and salary. Employee 101 has name A and employee 101 has a salary of 2000. Employee 103, I do not know the name of employee 103. And similarly, I do not know the salary of employee 102. In natural join, I will only get this tuple as the output. E101, A 2000. Is this the answer? Is this that they have asked? No. They are not asking us to do the natural join. They want something like this. Full outer join. Employee 101, employee name A and salary 2000. Employee 102, although I do not know the salary, but I know the name B. Employee 103, I do not know the name, but I know the salary. So this is what they have asked. So this was all about joins. Let's begin with division operator. First of all, we will understand when this operator is possible to apply. So I should first explain in the easier terms. R1 division operator R2. It is only possible when R1 is bigger than R2, which means all the attributes of R2 should be present in R1. But there should be some extra attributes in R1 that are not present in R2. Let me give an example. Suppose A, B, C, D. If I write like this, think, is this possible? Is division possible here? No. Because R2 should not have some extra attribute. Here E is extra attribute. All the attributes of R2 should be present in R1, plus R1 should also have some extra attribute. If I write like this, A, B, C, D, and then B, C, D is in R1. Is this possible then? Yes, because B, C, D is present in R1 and R1 also has some extra attribute. Now let's understand, if division happens, then what will be the output? If I write like this, A, B, C and division operator B, C, then remove the attributes of R2 from R1 and the remaining will be shown in the output. That's why I can say that degree of R1 division operator R2 will be degree of R1 minus degree of R2, because the attributes of R2 were removed from R1. Okay. Now, if R1 division operator R2 is possible, then R2 division operator R1 will not happen. Let me explain. If I say A is the subset of B, then think, can I say vice versa, that B is subset of A? Yes, I can say. this is possible. Let's say 1, 2, 3, and here also 1, 2, 3. In that case, A is the subset of B and B is also subset of A. I can say this when sets are equal. But there is an explicit condition mentioned here that it should be proper subset. In the case of proper subset, I cannot say like this, that if A is the proper subset of B, then B cannot be the proper subset of A. Why? Because in proper subset, one set will be bigger and another will be smaller. And if I say R1 is bigger than R2, then I cannot say the opposite, that R2 is now bigger than R1. That's why if R1 division operator R2 is possible, then R2 division operator R1 will not happen. If I write like this, R1 division operator R2, then first step is find the attribute of R1 which will come in the output. Suppose here A will come in the output and here B will come in the output. So whichever attribute which will come in the output, see the value of that attribute which will be associated with each and every instance of B or R2. If I am dividing like this, R1 division operator R2, then find the value of A which is associated with each and every instance of B. So P is associated with A and B, so P will come in the output. Q is associated with A and B, Q will come in the output. M is associated with A but not B. R with B but not A, so they will not come. P and Q will be in the output. Okay. If I divide like this, R1 division operator R3, then firstly find the attribute which will come in the output. B will come in the output. Now find the value of B which will be associated with each and every instance of R3, which means find that value of B which is associated with both P and Q. A is associated with P and Q, so A will come in the output. B is associated with P and Q, B will come in the output. C is associated with P and Q, so C will come in the output. Are you getting the point? If I am writing like this, R1 division operator R2, A will come in the output. So all those values of A which is associated with each and every instance of R2. B will come in the output. So all those values of B which will be associated with each and every instance of R3. Let's see some more examples. R1, ABC, R2A, R3, CD. So firstly check, is R1 division operator R2 possible? Yes, BC will come in the output. Check for this, R1 division operator R3. Is it possible? No. Because there is something extra in R3. R3 is not the proper subset of R1. So this is not possible. Check here. R1 division operator R2. Firstly find which attribute will come in the output. C will come in the output. Now check those values of C which is associated with each and every instance of R2. What are the instances of R2? 1, 2 and 4, 5. Now check the value of C which is associated with both 1, 2 and 4, 5. So 3 is associated, that's why 3 will come in the output. Check with 6, 4, 5, 1, 2. Both are satisfied, so 6 will come in the output. Check for 4, 1, 2 but not 4, 5. I want instance of C which are matching to both 1, 2 and 4, 5. So 4 will not come. This will be the output. Now for R1 division operator R3, A will come in the output. BC will be gone, A will come in the output. Now check the values of A which will be associated with each and every instance of R3, which means both 2, 3 and 5, 6. 1 is associated with 2, 3 but not 5, 6. 4 with 5, 6 but not 2, 3. So I can say no value is matching, so 5 will be answer. We have learned that division operator is a derived operator. Let's see. Suppose R1 division operator R2, same previous tables. R1 division operator R2. Check for the values of A which are associated with both A and B. Now you cannot think like stepwise to reach a suitable outcome, but we will start with the answer and then we will reach back to the value that we have previously received. We'll first project the value of A from R1. So we have PQMR. PQMR. The distinct values will come in the output. Now, this value will be cross product with this table. Cross product A and B. So you'll receive P will be associated with A and B, Q will be associated with A and B, M will be associated AB, R, AB. So this will be the cross product result. Now subtract the value of R1 from the cross product. So R1 will be subtracted from cross product. You will receive MB and RA. MB and RA. Now project the value of A from this. You will receive MR. So this is what those values of A which are not associated with each and every instance of B. If I subtract total A minus those A which are not associated with each and every instance of B, I will get those A's which are associated. So P and Q will be the answer. So what we have done? Project A, cross product with R2, and then let's rename this table as X, and then X minus R1. This is what we have done here. Project A, and then rename this table as Y. After that, total A minus this Y. This will give me the result. So division operator can be expressed with the help of projection, Cartesian product and set difference. Projection, Cartesian product and set difference. Let's see the general formula. R1 divides R2. Let's say the degree of R1 is R and degree of R2 is S. Then I will say pi R minus S R1 minus, this was the total which we were talking about. Now this will give me this R minus S, R1 cross product with R2 and then subtraction of R1. This is like that. And then R minus S will be projected. Okay. So this is the general formula. You do not have to remember. I have explained to you only to prove the point that division operator is the derived operator. With the help of fundamental operators, we can reach to the result of division operator. Now, whenever you see the word all in the queries, then division operator may come into picture. Let's see the example. Book, user, borrower and supplier or old schema. Find the name of that supplier who has supplied all the books issued to Adesanya. Whichever books issued to Adesanya, I want the name of that supplier which has issued all those books. If Adesanya has 4 books, then 3 issued by one supplier and remaining book by another supplier, then there will be no result. I want the name of that supplier who has supplied all the books issued to Adesanya. If he has 4 books and 3 are supplied by one supplier and 1 by another, then no result will come. Supplier should supply all the books which Adesanya have in order to come in the result. Are you getting the point? If you see all in the picture, all, then think of division operator. Then what we will do? S name, BID, divide with the BID. Now, these are the book ID of all those books issued to Adesanya. And these and this S name and book ID. Name of all those suppliers who have supplied the books. Okay. Now, if I divide like this, to which supplier name all these books, all these book IDs are associated with? I think I have to explain with the help of an example. See here. Book ID, supplier name. Let's say A, B, C. Book ID is 101, 102 and 103. Now here is the book ID of all those books issued to Adesanya. Let's say 101, 102. Now, will anything come in the output? No, because output will only come if there exists some supplier who has supplied all the books issued to Adesanya. Now, let's change the value. That supplier name here is A. Supplier name A and B. Now check. To which supplier name all these books ID are associated with. So 101 and 102 are associated with supplier A. So supplier A is that supplier who has supplied all the books issued to Adesanya. Which books are issued to Adesanya? 101 and 102. So supplier A will come in the output. Find the name of those suppliers who have issued book of the same title as issued to Pereira. Find the name of those suppliers who have supplied book of the same title as issued to Pereira. Again, what I want in the output, I want S name. First, find the title of all those books issued to Pereira. So we will use user, borrow and book, natural join, apply the condition, the name is Pereira, and the title. So we have find the title of all those books issued to Pereira. Now we want the list of supplier and title of the book supplied. So supplier, join book, project S name and title. So now we have S name and title. Here we have the title of all those books issued to Pereira. Similar case like previous one. These titles should be matched with the same supplier name. Now we apply the division operator. Supplier. So this is what the name and the title of the book which the supplier has supplied. Supplier name and book. Let's take an example. Again, A, B, C, D. The name of book supplied is X, Y, Z. And D has also supplied, let's say, X. The title of the books which Pereira have is X, Y, and Z. Will any supplier name come in the output? No, because I want that these all books should be supplied by the same supplier. Now nothing will come in the output. Let's check again. A, Z, let's say, or B. The title of all the books issued to Pereira are supplied by the same supplier name. A will come in the output now. So we have find this from this supplier join book, S name and title. This is S name and this is title. And from here we have find the title of all the books supplied to Pereira. Division operator will ensure that to which supplier name all these titles are associated with. So A is the answer. That's why A will come in the output. Now the question is, can you guess the English queries from the following algebra? We have the book ID and card number from borrow and selection operator with the name Bhamasha on user, and we have projected the card number. So this will give me card number of Bhamasha, just one instance, let's say C101. So I have here like this card number C101, and here I have the book ID and card number. So let's create a table, book ID, card number. Whenever it is asked to find English query from algebra, what I've told you, take example, build a sample table, fill the values, apply that query on those tables, and then see what the result is saying to you. Book ID B101 issued to card number 101. Book ID 102 issued to card number, let's say 107. Book ID 104 or let's say 3 issued to card number 101. Book ID 104 issued to card number 103. Book ID 105 issued to card number, book ID 101. Now here, book ID, card number, division operator, card number. So card number will be cancelled, book ID will be the remaining attribute. Now check the remaining attribute values which is associated with each and every instance of the table card number. But fortunately, card number has just one instance, C101. So I can directly say check those values of BID which is associated with card number 101. So this is a simple thing, which means list the book ID of all those books which are issued to Bhamasha. See what we have done in the division operator. If I say R1 division operator R2, then here we have book ID and card number. Here we have just the card number. Remove the card number. Book ID will be the final attribute which will have in the output. Now check. Let me write again. Now check all those book ID which is associated with each and every instance of R2. But R2 fortunately have just one instance, C101. So I will say list all those ID which is associated with card number 101, or specifically saying issued to Bhamasha. And this can simply be done without using the division operator. User join borrow, name Bhamasha, just project the book ID. Let's see another question, but by the way, you should learn about this man, Bhamasha. Do a Google search and learn about him. Book ID, title from book, and title equals to Dune from book. So this will directly give me this result, title equals to Dune. And if I have to apply division operator here, title will be cancelled, book ID will be the remaining attribute. Now check all those book ID which will be associated with each and every instance of the table title. Unfortunately, we just have a single instance, so I want the book ID of all those books which are associated with the title Dune, which means return book ID of all those books, all the books of Dune series. Return book ID of all the books of Dune series. Wherever the title is Dune, that book ID I want. Simple case. Now, do not try to remember things, try to understand. Let's see this example. What does this query say? Supplier name, price from the table supplier, and price equals to 200, project the price, division operator. The options are find the name of all those suppliers who have supplied all the books at price 200. Option B, find the name of all those suppliers who have supplied at least one book at the price 200. Whenever someone asks, this is the algebra, find the query, what you do? You take the example. So supplier, price. Ziri has supplied book of price 200, 250. Alex has supplied book of price 210 and 200. And Sean has supplied a book of price 200. What will this query will return? Price equal to 200, and I have projected the price. So this will be the output. Now I applied the division operator. Remaining attribute supplier. Now find the value of those suppliers who are associated with each and every instance of this table price, which is 200, which means I want those suppliers who have supplied at least one book at a price 200. So Ziri has supplied at 200, Alex has supplies at 200, Sean has supplied at 200. So Ziri, Alex and Sean will be the answer. Are you getting the point? Division operator applied, price cancelled, supplier. Now find the values of those suppliers who have supplied at least one book at a price 200. How I can say that? Because division operators say, firstly find the attribute which will come in the output, supplier will come in the output. Now find the value of those suppliers which are associated with each and every instance of the price table. So I want those suppliers which are associated with the price 200, which means I want those suppliers who have supplied a book, at least one book with a price of 200. I think now the point is clear. Do not try to remember things like that. Whenever you see all, think of division operator. So this must be the answer. No. You properly solve them by taking the example, applying the query here, and then see what the result is saying. Result is saying that those supplier name which has supplied at least one book of price 200. Then what will be the query for option A? Find the name of those suppliers who have supplied all the books at price 200. In that case, list of all suppliers minus suppliers who have supplied at least one book not of rupees 200. Are you getting the point? List of suppliers minus those suppliers who have supplied at least one book not of rupees 200, which means it will give me suppliers who have supplied all the books of rupees 200. Total minus those suppliers who have supplied at least one book not of rupees 200 will give me all those suppliers who have supplied all the books as rupees 200. If you are still not getting this, again I will say the same thing. Take the example, apply this on that example, and you will understand better. List of all suppliers, S name supplier. Supplier who have supplied at least one book not of rupees 200, S name, price not equal to 200, applied on the this condition applied on the relation supplier, and you will get this option A. Okay. Now the question, what will happen if R2 is empty in R1 division operator R2? Cancel B, A will be the remaining attribute. Now check all those values of A which will be associated with each and every entry of B. But B doesn't have any entry. What will happen then? In that case, duplicacy will be removed and this attribute will come as a whole. What was the steps that we followed? Consider the attribute which will be associated with each and every instance of B. But B doesn't have an instance, then this whole attribute will come. But you should remember that to express this division operator, we have used projection, Cartesian product, and set difference. And you should remember that projection removes the duplicacy. That's why just P and Q will come. Okay. If you are still not getting this, we can follow another approach. Let's apply the formula. What was the formula? This was the formula. So we'll begin with here. Project A, we have projected A. Cartesian product with B. B doesn't have any instance, so it will return an empty relation. Then subtract R1 from this empty relation. You will get empty relation again. And then project A from that empty relation. You will get this A and this. And now project A from R1. You will get PQ. And then subtract the empty relation from this PQ. You will get this. Okay. See, you will not fully understand by just watching this video. I have told you the formula. Apply the formula on these two tables and you will get the answer. Okay. Let's understand null in relational algebra. Null means non-existing, non-applicable or unknown values. Null is unknown, hence it is neither greater nor less nor equal to itself or any other value. If I write like this, null is greater than 5, then the result will be null. If I write like this, 3 is greater than 1, then the result will be true. If I write like this, 1 is greater than 3, then the result will be false. But if I write like this, that null is greater than 5, then the result will be null. Null is less than 5000, result is null. Null equal to 2000, result is null. Null equal to null, result is null. Null greater than null, result is null. Null not equal to null, result is null. But you do not have to blindly say null whenever null is involved. Understand. True and operator null. The result is null because null means unknown. If it is true, then the result will be true. If it is false, then the result will be false. But now we do not know the result. It's unknown to us. That's why null. If I write like this, false and operator null, then whether null is true or false, I know that the result will be false. Then I will directly say the result is not unknown, it's false. Okay, null plus 5, null, null minus 100, null, null divided by 50, null, null and null, null, null or null, null, not null is also null. True or null, this is true because I do not care whether null is true or false. Or operator is here. If one of the two is true, then the result will be true. So the result is not unknown, it's true. I know the result, that's why true. False or null, here the result is unknown because if it is true, then the result will be true. If it is false, then the result will be false. Okay. Let's see some more important points. Null values are ignored in selection operator because in selection operator, only those values are involved which satisfy the condition, which return true. But if I include like this, that null is greater than 2, in that case, the result is null. It's not true. That's why those values or those tuples are not included. Are you getting the point? Suppose if the condition is that C should be greater than 2, and here in this tuple, C is null, then I will not include this tuple because if I do like this, null greater than 2, then the result is null. It's not true. That's why this tuple will not be included. If I say like this, the condition is B greater than 2, then I can say that 3 is greater than 2. This is true. Then this tuple is included. Then I will not care that C is null or not. Okay. If the condition is true, then that tuple will be included whether that tuple involves null or not. But if the condition returns null value or false value, in that case, whether the tuple has null or not, I will not care. I am not going to include that tuple. I hope the point is clear. Let me repeat one last time. If the condition returns true, then you are going to include that tuple, otherwise not. What about join? If common attribute has null value, then those tuple will not be reflected in the output. Why? Same reason, because join also includes selection. What was join? Cartesian product and then followed by a condition. If the common attribute has null, in that case also the condition will not return true. That's why those tuples will not be reflected in the output. Projection. What about projection? Null is returned here. Suppose I have like this, project B. In that case, 3, null and 6 will come in the output. Null is not ignored in the projection. What about union, set difference, and intersection? They do not ignore null, just like projection. Suppose I have like this, 1, 2, null, 3, 4, 5, 6, null and 7. Intersection 1, 2, null, 3, 4, 5, 3, 6, 2. In that case, the answer will be 3, 4, 5 is common. So 3, 4, 5 will come. And 1, 2, null is also there. So this is also common between the relation 1 and relation 2. That's why this tuple will also come in the output. Are you getting the point? Selection operator returns only those tuples which return the condition true. That's it. If the answer is null or false, that tuple will not be included. Similar can be said for join, because join also includes selection. But when we talk about projection or union, set difference, intersection, they do not ignore null. Till now, we have learned just to retrieve the data. In the next lecture, we will learn about database modification, tuple by tuple, that is insertion, deletion, and updation of the database. Okay. Now let's learn modification of the database. When we will discuss about modification, we will modify the database tuple by tuple. We will not talk about updating a single cell value. We will talk about updation, deletion, or insertion of a whole tuple. Here we will talk about tuple by tuple modification, like inserting a whole tuple or deleting a whole tuple. We will not talk about modification of a single cell. Okay, like this. We will not talk about modification of this value. We will talk about the whole value. Even if we have to change the value of a single cell, we will delete the whole tuple and insert another tuple with the changed cell value of that cell, and remaining cell values will remain same. Okay. If I have to change this value, then I have to delete this whole tuple, insert another tuple with the updated value, and these remaining value will remain same. Okay. Now let's talk about deletion. In deletion, the representation of deletion is like this: R minus E, where R is that relation, E is the relational algebra expression whose output is union compatible with R. E will include those tuples which are there to be removed from this original relation. This is assignment operator. So I am assigning the old relation a new updated relation which has some tuples removed from the original relation. We will not talk about attributes here. We will not talk about a single cell modification. We are talking about the removal of tuples. So this E will include those tuples which are set to be removed. R is the original relation. After subtracting those tuples, the new relation will be assigned to the old relation. This is the assignment operator. Okay. And you know that for set difference, union compatibility is must. So this E will be a relational algebra expression whose output is union compatible with original relation R. Suppose I have say delete all entries from borrow relation corresponding to card number 101. So this relation will return me all those entries where card number equals to 101. All those tuples where card number equals to 101 will be represented by this. And if I subtract this from the original relation, then I will delete all those entries from borrow relation where the card number was 101. Suppose if I say that Ziri has returned all the books. So in that case, book ID, card number, and date of issue where the name is Ziri will be returned. Why this? Why this whole? Because from user join borrow, it is Cartesian product. the degree will increase automatically. But here the borrow just have book ID, card number and date of issue. That's why from user join borrow, I will output those tuples where the name is Ziri, and then I have to do the projection of book ID, card number and date of issue for union compatibility, and then I will subtract those tuples from the borrow relation. So Ziri has written all the books, this will be affected. Connor has written all wrestling books. Now here I have also included the title. So I will say selection book join user join borrow, where name is Connor and title equals to wrestling. Again, for union compatibility, I have to extract or project book ID, card number and date of issue, because I have to apply set difference with this relation borrow, and degree should be same. So book ID, card number and date of issue. This will also match the domain constraint. Okay, so degree and domain are same now. So union compatibility is satisfied. Delete all the entries of the book having price more than 1000 from the table book. So book join supplier, where price is greater than 1000, and then book has the attributes book ID, title and year. That's why for union compatibility, from this relation I will project book ID, title and year and subtract those tuples from the relation book. I hope the point is clear. Let me repeat. In modification of database, what we do, we modify tuple by tuple. So whichever tuple we want to delete, we will delete using the set difference operator, and the new relation will be assigned to the old relation. So this is the syntax of deletion. Relational algebra expression whose tuple is union compatible with R due to the use of set operator, which is set difference. Okay, and R was the original relation. And with the help of set difference, I will delete those tuples which I want from the original relation, and then this new relation will be assigned to old relation. Okay. Plus, you have to also follow that whenever you use like join, then make sure that union compatibility is followed. And how are you going to make sure? With the help of this projection. And which attributes you have to project? Based on whichever relation you are subtracting. Here we were subtracting from borrow, so we have projected book ID, card number and date of issue. Here we were subtracting from book, that's why we have projected book ID, title and year. Now let's understand insertion. For deletion we have used set difference, and for insertion we will use union. And again, for if we are using a set operator, then union compatibility is must. So these are all tuples which I want to insert in the original relation R, and then when these tuples are inserted, we will get the new relation, and then the new relation will be assigned to the old relation. So now the old relation is removed or deleted, and now we have this new relation. Okay. Example, insert an entry into book having book ID B101, year of publication is 2025 and title is A. So if I have to insert, I will directly insert like this: book ID 101, title is A, and the year of publication is 2025. Similarly, if I have to remove that, then I will simply use the set difference. Alex has issued a book on 15th April 2025 having book ID B101. So what I will do? Borrow union, which means I want to add another entry or tuple where book ID is 101. R1 is the relation and the date of issue is 15th April 2025. Now, what is R1? R1 is from the relation user, name is Alex, and I have to project the card number because I do not know the card number of Alex. With the help of this relation R1, I have found the card number of Alex, because in borrow we have attributes of book ID, card number and date of issue. This is followed by this 15th April 2025 book ID is here presented B101. I do not know the card number of Alex. That's why with the help of this relation R1, I have applied a selection operator with a condition that name should be Alex, and after that I have projected the card number. Okay, now we will learn about updation. If I say give 5% discount on all books, then here I have to project from the supplier table with the updated price. So I will project book ID, S name, the updated price, and I have renamed it to price, and then date of supply. You may have guessed that this is not the normal projection that we were doing before. Let's rename it as generalized projection, a new name. Okay, so if I say give 5% discount on all books supplied by Easy having price greater than 1000, then we will first delete those tuples where name is Easy and price is greater than 1000 from supplier, and then I will apply 5% discount on those tuples where name is Easy and price is greater than 1000 from the table supplier, book ID, S name, 5% discount applied, and then date of supply. These are all the attributes of the table supplier. And then see what we are doing here. We are first removing all those tuples where name is Easy and price is 1000, and then we are adding those tuples again with the updated price of 5% discount with the help of Unary. Okay, so this was about modification of database. Now let's learn what will be the minimum and maximum number of tuples when we talk about join. We have two relations, R1 and R2. R1 has attribute AB, where B here will act as a foreign key and here it will act as a primary key. R1 has 200 tuples, R2 has 100 tuples. We have previously learned that for join, maximum will be m cross n and minimum will be 0 if R1 has m tuples and R2 has n tuples. This was the case when attributes were distinct. If we have like a common attribute where we have a parent and a child relation, then make sure that foreign key is the factor. Foreign key will act as a determining factor of number of tuples in the final relation. B will act as a foreign key, and foreign key can be null. Say all values of B are null. In that case, here, if each and every B is null, then there will be no match. If there is no match, then the number of tuples in the output will be 0. Let's see another condition where we have this foreign key has 2, 2, 3, 3 and R2 has 2, 5, 3, 6. Here 2 will match with 2, this 2 will match with 2, 3 will match with 3, and this 3 will match with 3. So what will be the maximum number of tuples? 4, which is equal to the number of tuples in R1. B will act as a primary key in R2, which cannot be repeated. If B cannot be repeated, then what will be the deciding factor? I've told you earlier also. Foreign key will be the deciding factor. So here, if every tuple matches, then maximum number of tuples, maximum will be based on the number of tuples in the relation of foreign key, which is 1, 2, 3, 4. That's why 4. And here we have maximum 200 tuples where B will act as a foreign key here. So 200 will be the maximum. Okay. If I apply constraint on foreign key, that foreign key cannot be null. If foreign key cannot be null, then minimum number of tuples are 200 because matching is must, and maximum number of tuples we have seen here also will be 200. So see another example. Here we have applied that foreign key cannot be null. Let's say we have made this combination as the primary key, which means B, which is acting as a foreign key also, is acting as a primary key, which means that B cannot be null. If B cannot be null, which means foreign key cannot be null, then matching is must. If matching is must, then the minimum number will also be 8 and maximum number will also be 8. So if you have seen such kind of question in which we have a relation in which one relation will act as a parent table and another will act as a child table, then firstly see, is there any special kind of constraint applied on foreign key? If there is no such constraint, then foreign key will be the deciding factor. The maximum will be 200 and minimum will be 0 because foreign key can be null. If it is null, then nothing will match. But if I have applied not null constraint on foreign key, in that case, foreign key cannot be null, which means matching is must. If matching is must, then minimum number of tuples will also be 200. Maximum will also be 200 and minimum will also be 200. In the next lecture, we will learn about tuple and domain relational calculus. We will start with our relational calculus unit. In the last lecture, we have covered relational algebra. In this lecture, we will start with calculus. divided into two parts, tuple calculus and domain calculus. This relational calculus is a non-procedural language, which means it will not specify you how are you going to retrieve a data. Just what data to retrieve will be specified. Only specifies what to do, not how to do. It's a theoretical language, but you have to follow some representation or methodology that majority of the people understand. So there is no kind of strict syntax, as there is no compiler involved, but the general symbols or general representation will be same. Relational algebra has same power as that of safe relational calculus. And when I say safe, which means there will be some queries will yield unsafe results. And what are unsafe results? Those results which will also include those tuples which are not actually present in the table. Unsafe queries means including all those tuples which are physically not present in the table. For example, let's say I have a table named book. I have a book ID and title. If I say you to include all those tuples which are not present in this book, let's say when we will learn about tuple calculus, we will get the representation better, but for now let's see this. There is a tuple which should not belong to book. If I tell you to include all those tuples, then there are infinite tuples which are not present in this table book. So this is a kind of unsafe query. Understand this. Those queries which are not actually present in the table, these are unsafe queries. And relational calculus have more expressive power. It can also express the unsafe queries. So if we talk about just the safe calculus, then relational algebra and calculus have the same power. But if we talk about the whole, then tuple calculus or domain relational calculus has more power than relational algebra or SQL in terms of expressive power. So every query of relational algebra or SQL can be represented using calculus, but there exist some queries in calculus which cannot be expressed using algebra. Okay, I hope the point is clear. Now we will begin with what is relational calculus. Is a non-procedural query language that tells the system what data to be retrieved but doesn't tell how to retrieve. We will begin with tuple relational calculus. So this is the representation. S will consist of all those tuple which will satisfy a specific condition P, let's say. So this is a tuple variable, and P is the condition that should be satisfied by this tuple variable, and whichever tuple satisfy that condition, that tuple will be included. So what is a variable that varies? So this tuple variable will point to each and every tuple, and we will check that which tuple satisfy the condition. If that tuple satisfy, that will be included. So S will consist of all those tuple T such that condition P on T is satisfied. Okay. Same thing written here. T is the tuple variable. Condition should be satisfied on this tuple variable T. If that condition is true, then that tuple will be included. Now what about the attributes of the tuple? We will show the attribute with the help of T dot A, where A is the attribute of tuple T, or with the help of this T bracket A. Okay, T is the tuple variable. Ta denote the value of tuple on attribute A. T belongs to relation R. T belongs to relation R. This is the way to represent that this tuple is in relation R. You can write like this also. Let's say employee T, which means this tuple variable is in this table employee. So whichever tuple we are considering belong to the table employee. Condition is a formula similar to that of predicate calculus. Even this is also a condition that this tuple should belong to this relation. Now let's see some examples in the queries written in relational algebra and then the same query in calculus. Project the table employee. So in calculus we write T is a tuple variable where this tuple variable should belong to the table employee. You can also write like this, T employee T. If I want to project a specific attribute, then T dot ename where tuple belong to the table employee, or with the help of brackets T ename where T belong to the employee. What about condition? Let's say I want to imply that employee number should be 101. Then you can impose that condition with the help of AND operator. You can also write like AND here, and then specify T dot E number equals to 101, or you can also write T E number equals to 101. So these two are the condition that is followed by whichever tuple T, that tuple will be included. That tuple should belong to the table employee, and the employee number attribute of that tuple T should be 101. Employee name and salary I want to be projected, where salary should be greater than 1000 and department number of that employee should be 101. Easy. T dot ename, T dot salary to be projected, where T is the tuple of table employee. The salary attribute of that tuple T should be greater than 1000, and the department number of that attribute or that tuple T should be 101. Okay. More examples: employee, first name, last name, date of birth, salary, address, and department number. Find the details of all employee whose salary is more than 5000. Again, the same case, salary should be greater than 5000, or you can write like this: employee T, where salary is greater than 5000. Okay. So these are the way T using this symbol employee, or with the help of dot operator, or you can also write like this: employee bracket T, and using bracket operator. It produced the tuple of T. It produced tuple T of employee where condition is satisfied. So whichever tuple which has the salary attribute more than 5000, that tuple of table employee will be included. Now if we want to find only specific attribute of a table, then let's take an example. We have talked about this with the help of, you can write like this or like this. Find the name of employees whose salary is more than 5000. Then expression is like T dot F name, T dot last name, employee T, where T dot salary is greater than 5000. Now these two ideas we have discussed. There is one more special idea, that let's say there is a tuple variable S which do not belong to the table employee. There is a tuple variable S and there is a tuple variable T. Okay, so this is another special idea to represent the same thing here. Let's say S is a tuple which do not belong to the table employee, but there is a tuple T which belong to the table employee, and the salary attribute of that tuple is 5000. Now there is an attribute first name of that tuple variable S, so the value of first name of the tuple variable S should be equal to the value of first name of tuple variable T which belong to the table employee, whose salary attribute is greater than 5000, and there is also an attribute last name of the tuple variable S whose value should be equal to the last name of tuple variable T which belong to the table employee and whose salary is greater than 5000. So I know it's a kind of messy thing, but this is also a representation of these two. Here S is not the tuple of employee but T is. Then we say that T dot salary should be greater than 5000. After that we specify that S has an attribute named first name which is equal to the attribute first name of T, and similar for last name. So you can represent in whichever manner you want, but you should know in what way we represent all these things. So whenever you read these type of queries, then you should understand that we are talking about these two. Now what is the output of the following query? T dot department name, where employee belong to the table, where tuple T belong to the table employee, and department number of that tuple should be equal to 10. Now here was the schema. There is the department number only and there is no department name attribute. So I'm saying there is a tuple which belong to the table employee and the attribute department name of the tuple T, but we know that the tuple of employee doesn't have an attribute department name. It has department number. So the output of this query will be null because department name is not an employee table. So department name is not in the employee table. So none of the tuple will be able to satisfy this query, which means empty relation. Find date of birth and address of employees whose name is Rohit Sharma. Again, T.dob, T.address, where the tuple should belong to the table employee and the first name should be Rohit and last name should be Sharma. Easy. Student, roll number, name, degree, year, sex, department number, department ID, name, phone number and HOD. Find the roll number and name of all the female student of department number 2. So we have to project the attribute roll number and name. So we will say there is a tuple variable S which has the attribute roll number and the name, where S belong to the table student, and the attribute sex of the tuple S is female, and department number attribute of the tuple S is 2. Simple. Or you can also write like this: T, where S belong to the student, S dot sex equals to female, S dot department number equal to 2, where, and what attribute you have to project? Roll number and name. So this is what the projection is. T roll number should be equal to S roll number, T S name should be equal to S name. Similar thing which we were doing here. This is a kind of projection. So what we wanted name. That's why this is projection. We have projected first name and last name. So similarly here, even you can project like this, that S dot roll number or S dot name, or you can project like this. An advanced example: find the name of female student of maths department. Now we are talking about taking help from another table, which means referencing another table, doing join in tuple relational calculus. Because in a student table I have at max department number, but to find department name I have to take help from another table which is department. Find the name of female student of math department. This math is name attribute of another table. So to solve these type of query, we have to understand that there are two type of operators: there exist and for all. There exist means whatever be the condition, there exists some x which will satisfy that condition, and for all means whatever will be condition, it will be true for every x. For all x, the condition will be satisfied. So S will be the tuple variable where S belongs to the student, and I want to project the name. So S dot name will be projected, S dot sex should be female, and there exists a tuple variable D which belongs to the table department. Now we are matching the common attribute, that is department number and department ID should be matched, and department name should be matched. See, this is for the first time, so if you are getting confused a little bit, we will see more examples and you will get more clarity. Let me repeat: S is the tuple variable of the table student whose name attribute I want to project, and the sex attribute of tuple S should be female, and there exists another tuple variable D which belong to the table department, and department ID of tuple variable D of department should be equal to department number attribute of tuple variable S which belong to the table student should be same, and department name of this tuple variable D which belong to the table department should be maths. This is what the full query sounds like. Now there is a special point. This S is the free tuple variable, which means it can be present at both right hand side and left hand side. But this D, this is the extensionally bounded variable which is only present at the right hand side, which means I cannot project the attributes of department here. Okay, it is only used for referencing, for join. Okay, find the name of department that doesn't have any girl student. So I will say department name should be projected, and D belong to the table department. D is a tuple variable whose department name attribute is projected which belong to the table department, and there exists a tuple variable S which belong to the table student, and S dot sex should be female, and S dot department number should be equal to department ID. These are the female student of a certain department. Now I want that department which doesn't have any female student, which means I have to apply negation. So there exists no student. If this is, there exists some tuple S, and this is, there exists no tuple S who is female and whose department number matches with the department ID. So this query will give me the name of all those department that doesn't have any girl student. Let's see some more examples. What about taking three tables into factor? For example, we have course, enroll, and student, course ID, course name, course ID, roll number, grades, and roll number, name, address. Find the name of courses enrolled by Diamond Pori. So we want the course name from the course table and we have to match the course ID from course and roll number from enroll and student. To do that, firstly we have to identify the free variable and the bounded variable. We want to project the attribute of course table. So course will be the free variable. So we will say cname. So c.cname, where c is the tuple variable which belong to the table course. Now define the bound variable, which is student and enroll, where s is the tuple variable for student and e is for enroll. Now we want to match the roll number and the course ID. So s.roll number should be equal to e.roll number, course.course ID should be equal to e.course ID, and roll.course ID, and name should be Dustin Poirier. So this is how you apply join in tuple relational calculus, by first defining the tuple variables, the bounded variables, and then setting it to the relations, and then equating the common attribute. You can use the attribute of a table after declaring it either at the beginning or by using the existential quantifier. So you cannot directly use the attribute without even declaring it. So here we have declared that C should belong to the course, and here we have declared that S belong to the student and E belong to the enroll. That's why we are using the roll number, the course ID, and the name attribute. This case is different. Here we are projecting, but in the right hand side you have to first declare and then use. We can also write the query this way, that c.cname, where C belong to the course, and you first declare the student, so S belong to the student and the name is Diamond, and then declare the enroll, so E belong to the enroll, and S.roll number should be equal to E.roll number. You cannot now use directly roll number here. If you apply the same condition before this declaration, that S.roll number should be equal to E.roll number, error will be thrown that what is this E. So we have to first declare that E is a tuple variable which belong to the table enroll, and S.roll number should be equal to enroll.roll number, and C.course ID should be enroll.course ID. Okay, let's discuss on our old schema. We have book, user, borrower, and supplier. Find book ID and year of all DBMS book. So you can do like this: b.book ID and then b.year, where book b, either you can write like this or like this, b belong to book, and then set the condition that b.title should be DBMS, or we have already discussed this way, set a tuple variable t, and then there exists b which belong to the book whose title is DBMS, and then match the attribute we want to project. We want to project book ID, so match the book ID of both tuple variable t and b, match the year of both tuple variable b and t. Similarly, find the name of all those users who live in city Bikaner. So we will write like this: t, there exists u belong to user, and then city should be Bikaner, and then which attribute we want to project, name. So name should be matched from u and t. Or you can also write like this: s equals to u.name, where u belong to user and u.city equals to Bikaner. You can also write like this. How to perform join in calculus? Find book ID of all those books issued to Makhashev. So we want to project the book ID, name condition mentioned, and then user, join, borrow. In tuple relational calculus, we will write like this: t, there exists a user whose name is Makhashev, and there exists another tuple variable b which belong to the table borrow, and card number should be matched. So we have matched the card number, and book ID matched. So we have matched the book ID. This is the common attribute matching for join, and this is for the projection. We are matching for t and b. So this was for the projection, and this was for identifying valid tuples, the attribute matching that we used to do in a join or Cartesian product. Let me repeat: we want to find the book ID of all those books issued to Makhashev. In algebra, we will first mention the condition and then project the book ID. In calculus, we will first mention that there exists some user whose name is Makhashev, and then there exists a tuple b, and then here we have matched the common attribute that the card number from borrow and user should be same, and then the projection part that we did here, here, that book ID attribute which we want to project should be matched. Okay, find the title of all books issued to Tristan. There exists a tuple variable t which doesn't belong to any of the table above, and then there exists a tuple variable b which belongs to the book. So we want to project the title, so b dot title equals to t dot title. Here we have done the projection, and then the tuple variable bo for borrow, and then borrow book id should be equals to book dot book id. This is what we were doing for join. And then there exists a user where user dot card number equals to book dot card number, and then, or the book didn't have card number, I think here should be borrow dot card number, and then user name should be Tristan. Let's properly understand the difference between there exists and for all quantifier with the help of an excellent example. Suppose we have our table book and we want to project the book ID from this table. So what we will do, take variable t, there exists b which belong to the book, and then b dot book ID equals to t dot book ID. This is what we have done before. Now we will understand the backend. How does it work? There exists b, which means there should be at least one book where book ID should match with t dot book ID, which means this tuple variable has an attribute book ID which should be matched with the book ID of book relation. So how we will check? This is our output table, and we will make a blind entry here, B105. Now the condition is there exists, so we will check with every tuple. Does it match book ID of b dot book ID? Is it equals to t dot book ID? So t dot book ID is 105, and b dot book ID here is 101 for this tuple, so this doesn't match. 102 for this tuple, it doesn't match. 103 doesn't match. 4 doesn't match. 5 matches. So this blind entry will be accepted. So B105, does this satisfy this condition that there exists at least one tuple in this whole table book whose book ID matches with this book ID? Yes, so this B105 will be a valid entry. Now if I change this to for all b, which means that when I make a blind entry here, that B105, so in each tuple of book, if b dot book ID is B105, then only B105 in t will be a valid entry. For each tuple, this condition should be satisfied. T dot book ID here is 105, and b dot book ID, this should be satisfied for each tuple. Is it possible here to let B105 live in this output table? No, it is not possible, because for this to exist, B105 should be at each and every place. So this using for all with AND operator is meaningless. Let's take another example. There exists b which belong to the table book, and b dot book ID should be equals to t dot book ID, and b dot year should be equals to t dot year. We are using AND here. This means that we will make a blind entry, and projection is for book ID and year. So for book ID and year, we will make a blind entry, and then we will see that there exists at least one tuple for which this blind entry value matches. So we will first start with B105 and year 2002. So does it matches B105? No, it doesn't matches. So it will match here. B105 match here. And then year 202. Does it matches? No. So this tuple is also discarded, because we are using AND operator here. Both the conditions should be satisfied for this tuple to get entry. Now we will start with B105 and year is 2001. B105 matched here, and year is also matched. So true from this side and true from this side. So this whole condition will be true, and this tuple will be included. Okay. What will happen if we use OR operator with there exist? If we use OR operator with there exist, then if one of these conditions satisfied, whether t dot book ID matches with b dot book ID or t dot year matches with b dot year, then that tuple will be included. Let's take an example. We start with B105 and then year is 2002. So B105 matches here. I will not check further. I will allow this. B105 year 2001, B105 matches. I will not check further. I will allow this. B199. This condition is false here because there is no B199 here. Now I have to check for the second condition, that the year is 2000. Does year matches anywhere? Yes, year matches here. So I will say this is written true, this is written false. False or true is true. So this tuple will also be considered valid. So these are actually not the entries present in the original table. B199 and then year is 2000, B10001 and year is 2001, B107 and year is 2199. These are not the valid entries or actual entries present in the table. If you remember, at the start of the lecture we have given a name for such entries. These are unsafe entries that are not actually present in the table. So I can say there exist with OR operator produces unsafe queries. This is the another example of unsafe query. Include all those tuples which are not present in the table book. So this will include infinite such tuples which are not present, because book table have limited tuples. And we are saying include all those tuples which are not present here, which means infinite such tuples, unsafe. So using this combination is not advisable. There exist with OR operator and for all with AND operator. Let's explore more. What if I use implication? B.title equals to T.title. So we are projecting title and year. We are projecting title and year. So these are two conditions. Let's say this is P and this is Q. If I apply implication here, then this will be the truth table. P implies Q will only be false when P is true and Q is false. So the English version of this truth table I have written here, if P is not true, if P is false, which means title is not matched. Which means if P is not true, which means title is not matched. In that case, I will say this condition is satisfied. If title is matched, which means P is true, then check if year is matched. If year is matched, then true. If year is doesn't match, then false. Let me repeat. This was condition P and this was condition Q. Previously we were using OR operator or AND operator. Now we are applying implication. Implication is false only when P is true and Q is false. So that's what we are writing here. This is the condition P, which means if P is not true, title is not matched, then it is always true. If P is matched, then I have to check whether year is also matched. If yes, then it is true. If not, then it is false. So we have used for all. It should be true for all the tuples of the book. See here, we have used the for all operator. So we are using for all, so it should be true for all the tuples of the book. Now let's check. Let's dry run. This was our blind entry. What we are doing? We are checking whether title is matching. We have seen here title is matching, but year is not matching. Title matched, year not matched. True, false. This true, false combo will lead us to false. So this will be discarded. Let's update. From 2001, we are making the blind entry of 2000. So now check here. DBMS title is matching, year is also matching. So true, true, true. But where? Here we have using for all, which means for each and every tuple, if the condition is true, then only I can say this will be included. So here, true, true, for this tuple it's true. False, false, true. False, false, true. True, false, this was the red flag. True, false, this will only lead me to the false values. So this is not valid, that title is DBMS and the year is 2002. Title is matched, but year is not matched, then false. So for even one tuple, if the condition is not valid, if the condition is not satisfied, then discard, because we are using for all here. For all will impose the condition on all of the tuples, and at all of the tuples it should be true. Now let's check for the third case. We are making another blind entry here. Operating system, the year should be 2001. We will check for each and every tuple. Title is not operating system, that's why false. Year is not 2001, that's why false. False, false is true. Title is operating system, that's why true. Year is 2001, that's why true. True, true is again true. We will do this for each and every tuple. True, true, false, false, then again true, true, false, true, false, false. I'm not finding the combination of true, false, which means this is satisfied for each and every tuple of the table book, which means P implies Q condition is being satisfied by this tuple for each and every record of the table book. That's why this tuple will be allowed entry in the final output table. Okay, so now we have checked the condition P implies Q for each and every tuple, but what does this actually mean? This is condition P and this is condition Q. This is P and this is Q. And P implies Q should be true for each and every tuple of the table book. And P implies Q is false only when P is true and Q is false. Which means title should be matched but year should not be matched. In that case only the result will be false. So what I'm expecting, wherever title is matched, the year should be matching. The year should be matching. So if I write like this DBMS and then 2001, so I'm expecting that if this is my blind entry in the table, then wherever DBMS is present, the year should be 2001. See this case. Let's change the entry to be year 2000. Okay, so you will get a better understanding. I made this blind entry, so wherever DBMS is there, the year should be 2000 only. Here satisfied. Again check DBMS, but year is not 2000. That's why I found the true false combo here. Let's move down. Operating system to 2001. Wherever I see operating system, the year should be 2001. Operating system 2001, operating system 2001, operating system 2001. Are you getting the idea? What English query can we generate from this P implies Q? I want the title and year of publication of all those books which are published once. Operating system was published in just year 2001, year 2001, year 2001. While DBMS was published in 2 years, 2000 and 2002. TOC was published in 2 years, 2001 and 2002. The only operating system case we have just 1 year of 2001. So what we were meant to find, the title and year of publication of all those books which are published once. Okay, what will happen if I change this year here and title here? Will it remain same? No. First of all, you have to understand that this is not equal. They are different. Why? Because when I write P implies Q, then this is false only when this is true and this is false. And when I write Q implies P, then this is false only when this is true and this is false. So in the first case, P was true. In the second case, P was false. So these two are not equal when I write here year and here title. Now pause the video and think what will happen if I change the condition. Let's see. If I change the order like here DBMS 2000, if this tuple is there now, then wherever 2000 is present, the title should be DBMS. In the previous case, what was that? Wherever DBMS is present, the title should be 2000. Now wherever 2000 is present, the title should be DBMS, which means give me that unlucky year or unfortunate year in which just one title was published. Are you getting the point? So I will not waste much time on this. What you have to understand is make a blind entry and check for whatever condition that is given. If you are given with for all, then check for all the tuples that condition should be true. If that is true, then allow that blind entry into the final table. And if I write here there exists, then even you can find just one tuple for which that condition is satisfied, then you can include that condition in the final output. Okay, so this was our tuple relational calculus. Now we will move to domain relational calculus. In tuple calculus, we had tuple variable, that is variable representing an entire row of a table or entire record. But here we have domain variable. as we have domain relational calculus, which means the variable which will represent the entire column attribute. In tuple relation, we have a variable which will represent the entire row. In domain relational calculus, we will have a variable which will represent an entire column. So this is the representation. Output table equals to A1, A2, A3. These are the column attributes which satisfy the condition P. There we had a tuple variable T which will satisfy the condition P. Here we will have the column attributes which will satisfy the condition P. If I write find book ID and title of all the books. So what I want to project? The book ID and title, where what will be the condition? That book ID and title should belong to the table book. This is what projection looks like in domain relational calculus. Find book ID of all DBMS book. Then what I want to project? Book ID. So book ID should be the attribute which will follow these two conditions. That the book ID should belong to the table book and the attribute title of the table book should be DBMS. Find title of all books supplied by Habib. Then what I want to project? Title, and there exist the pair of column attributes book ID and title which belong to the table book, and there exist book ID and S name which belong to the table supplier, and supplier name should be Habib. Let me repeat what we want: title of which books which are supplied by Habib, which means S name should be Habib, which means we want another table. So this is what join looks like: title, and first of all there exist book ID and title which belong to the table book. These are the two attributes of the table book, and book ID and S name are the attributes of table supplier, where S name equals to Habib. So from this, book ID will be automatically matched. In relational algebra, if I write like this, roll number is 101 from the table student, so I want the tuples where roll number is 101. So basically what I want, the name and date of birth of roll number 101. So in tuple relational calculus, I will write t dot name comma t dot dob, where t belong to the table student and t dot roll number equals to 101. In domain relational calculus, I will apply the same with the help of this name and date of birth. These are the attributes which we want to project, and which condition should be satisfied? These two conditions, that roll number, name and date of birth should belong to the table student and roll number should be 101. And there is another smart way to do this. If we want to project name and date of birth, but a pair of attribute, this pair of attributes should belong to the table student. So we are just fixing the value of roll number. Now this is not a variable now. We have fixed the domain variable which is 101, and then name and date of birth can be different. So this belongs to the table student. So wherever you find a pair of attributes which are satisfying this condition, then from that pair of attribute you project name and date of birth. Okay, so this was all about domain relational calculus and tuple relational calculus. In the next lecture, the most awaited, we will start with SQL. Welcome to the new section of SQL. In this section, we will begin by a quick history, and then we will learn different type of SQLs, or different sections of SQL, I should say. And then we will directly begin by mapping similarities between relational algebra and SQL. That's why you should first learn algebra and tuple relational calculus first, so that you can understand, or you can have the foundational knowledge first before directly jumping to SQL. And I've used the same schema, the same examples, so that you can establish a pattern also. So without wasting further time, let's begin. Commercial database languages: SQL, QBE and QUEL. SQL, Structured Query Language, this is the full form. It is based on relational algebra and calculus. Query by example based on domain relational calculus, and query language is based on tuple relational calculus. And all these languages are relationally complete. What is the meaning of relational complete? The meaning is, if query can be in relational algebra, if query can be expressed using relational algebra, then that query can also be written in SQL, QBE or QBEL. SQL is fourth generation language, which is more closer to natural language. You will get this idea when we will learn the syntax. C, C++ are third generation language. The more the generation, the more closer it will look to natural language. SQL is a non-procedural language. It will only tell me what data I want. That's it. Now, being an RDBMS, I have to manage how I'm going to retrieve the data. Are you getting the point? So SQL works on top of RDBMS. SQL will tell me the RDBMS, what data I want. RDBMS will manage how to retrieve that data. SQL work on the top of RDBMS. EF Cord invented relational model, but due to inertia, people are feeling safe, or they were strict to network and hierarchical model. They don't want to jump to relational model. But then Raymond and Donald invented SQL for a relational model. SQL was first implemented on System R and then Oracle, MS SQL Server, MS Access, MySQL, etc. Then it became very famous. If user doesn't like MySQL, then user can directly shift to Oracle without any specific training. SQL clashed with the name of aircraft company, so all the vowels were dropped and hence the name SQL. SQL is divided into various parts: DDL, DML, DCL, and TCL. DDL will include the defining, the creation, and the data feeding part. DML will include the manipulation part. DCL will include the data control part, and TCL the transaction control. Okay, so let's begin. This is the basic syntax. This is the first thing that we have to learn. We will first begin with the retrieval SQL. Writing all those queries from the pre-designed database, from the pre-designed tables, we are going to retrieve some data. Okay, so select, from, where. These are the three keywords that you have to initially learn. And whatever the keywords are, I'm going to represent those with the help of the capital letters. And one more point, SQL is case insensitive. Even if you write like this in the small letters, then also it's valid, but it's kind of practice so that it may be easily distinguishable that these are the keywords. Select, from, where. Okay, so select, these are the attributes which you want. So select is like a projection, but it is not really the projection. Projection will remove the duplicacy, but this select keyword will include duplicacy. So I can say select is a projection with duplicacy. So select whatever attributes you want to select. From, these are the tables which you want. So writing like this, R1, R2, R3, this is showing the cross product or the Cartesian product. So R1, R2 is R1 cross R2. If I am writing just R1, then I have to project the attributes from table R1. That's it. And then the next keyword, where, and then P. So where is going to specify the condition. This is like the selection operator. So let me repeat. Select the attributes from these tables where the condition is P. Okay, these are the attributes, these are the tables, and this is the condition. And select from where is the keyword. Select is the projection with duplicacy, from is Cartesian product, and where is the selection operator. So to represent this in a relational algebra, I will write R1 cross R2 cross Rn, selection operator with condition P, and I have to project A1, A2 till AN. Projection A1, A2 till AN. This select and from are mandatory. If you want to retrieve any data, then this select and from is mandatory. Otherwise, how I'm going to know that you want to retrieve some attribute, or from which table you want to retrieve those attributes? Condition is not mandatory. Condition is optional. If you just write this, select the attribute name from the tables, then all the attributes, all the tuples will be given in the output. This will only help in filtering out the tuples. If I'm not writing this, then all the tuples will be presented in the output. If I'm writing this, then based on the condition P, the tuples will be filtered out. So I can say where is optional, but this select and from are mandatory. These are the keywords, and these are case insensitive. Select retains duplicacy. To get distinct values, we have to include another keyword which is distinct. which will eliminate the duplicate values. Let me repeat. I have told you that select is projection with duplicacy. If I don't want duplicacy, then I have to include this another keyword which is distinct. So this distinct will include, or distinct will eliminate duplicate values, or will include only those values which are unique. Okay. So select distinct title. This is the attribute from the table book. So this will give me the list of the unique titles from the table book. It is possible you change the by default setting to distinct. See, in SQL, the by default settings is retain duplicacy. But if you change the by default setting to distinct, then select will automatically behave like projection exactly. Select would also remove the duplicacy. What if I have changed the settings and then I want that duplicate value should also be present? Then I have to use all. Okay, so let me read. It is possible that you change the by default setting to distinct. Then there will be no need to specifically mention distinct. You will automatically receive the distinct value. What if I want duplicacy then? Use all. So I'm going to write select all titles from book. Now let's see some of the problems. Find book ID of all DBMS book. This is the attribute I want to project. This is the condition and this is the table. Select book ID from books where title equals to DBMS. This was the condition. This was the table and this was the attribute. Okay. Find book ID of all books issued to Diego. Select book ID from user, borrow. This was the Cartesian product where now I have to write the condition for valid tuples. The common attribute should be equated. User.card number equal to borrow.card number and the condition is Diego. Name equals to Diego. So I'm not going to waste much of the time explaining all these things because we have already learned these kind of queries in relational algebra. Find title of all the books supplied by Strickland. So select the attribute which is title from now which two tables I want to include, the book and the supplier, where now the condition for valid tuples. The common attribute should be equated. Book ID equals to supplier ID and then the condition that the supplier name should be Strickland. Find title of all books issued to Dan Hooker. Select then title from now I have to include the all three user, borrow and book. With the help of comma I can do the Cartesian product and then the valid tuple identification condition which is the common attribute should be equated. User.card number equals to borrow.card number and book.bid equals to borrow.bid. And then the condition we have, with the help of this, we have done the join and then the condition is Dan Hooker should be the name. Find the name of all those users who live in the same city as that of Rao Bika. Rao Bika was the ruler who have founded Bikaner. Select, and this is the same query which we have already discussed before in the relational algebra. So if you are remembering that, that would be good. Otherwise, this will be kind of difficult to understand. So what we are doing here, self-Cartesian product. User is the table. I'm going to first rename it as U1 and then copy again, rename it as U2. So I have two tables, U1 and U2. I'm going to take the Cartesian product and then I will say U1.city should be equals to U2.city and U1.name equals to Rao Bika. Now I don't want Rao Bika to come again in the output table, that Rao Bika is also included in the users who live in the same city as that of Rao Bika. That's why I have included this condition also, that U2.name should not be equal to Rao Bika. I'm not going to explain this query again. We have already discussed all of this in detail in relational algebra. For us, renaming can also be done like this. Instead of writing like this, user U1, user U2, I can also write user as U1 or user as U2. Okay, so there's one point important regarding this as operator, the renaming operator, that if I'm renaming a table, here I was renaming a table. In that case, as operator is optional. You can write as, or you can also not write. Both are valid. Writing is also valid, not writing is also valid, but If we are renaming an attribute or a column, then using as is mandatory. This is the point I need to mention. Operators in SQL. Union, intersection, and set difference. We have discussed about this in relational algebra also. So we will just see the syntax and move on. Find student ID of all those books, all those students, not books, who have issued book and are also enrolled in some course. So what I want, the common part, the common student IDs. So select student ID from book, select student ID from course, and then give me the common part which I have done the both, that are enrolled in some course and have issued the book also. If I just want those students who have issued the book but not enrolled in any of the course, then we will use the minus. Student ID from book, then student ID from course, and use the minus. Suppose I'm using like this 1, 2, 3, and 3, 4, 5. These are the student ID who have issued the book. These are the student ID who are enrolled in some course. Using the minus will give me those students who have just issued the book, not enrolled in any of the course. Find student ID of all those students who have issued book or are enrolled in any of the course. Then I will use the union. Okay. Let's see another example. Select book ID from book where title equals to DBMS. Union, select book ID from borrow. So this will give me the book ID of the DBMS book as well as those book which are issued, or list the book ID of DBMS book and those books which are issued. See, the difference is here I am sounding like I'm going to use the intersection and as well as this. These give me the hint of intersection, but don't just mug up the things. You have to understand. Union is the better operator here. Here we are using and as well as, but we are still not using intersection because we have to understand what would intersection mean here. If I write like this, select book ID from book where title equals to DBMS intersection, select book ID from borrow, then this will give me all those IDs of the DBMS book which are issued. Union will give me the list of DBMS book and the list of those books which are issued. Intersection will give me the list of DBMS book which are issued. I hope you are getting the difference. So this query is equivalent to this query. Select book.book ID from book cross borrow where common attribute matched and title equals to DBMS. You can either write like this or use the join and then title equals to DBMS. You can do like both. Let's use minus or except now. Select book ID from book where title equals to DBMS except select book ID from borrow. This will give me the IDs of all those DBMS books which are not issued. This will give me all DBMS books. This will give me the issued books. This will give me the issued books. If I use the except, then this will give me the DBMS books which are not issued. Okay. Let's see some more concepts. Select S name from supplier where price equals to 1000. So this will name all those suppliers who have supplied at least one book of the price 1000. See the case. Suppose we have supplied name like A, B, C, D, E, and they have supplied the book of 1000. B have supplied a book of 9000, or C have supplied the book, and so on. A again supplied the book of 1100. Then what will be the output of this query? Just this tuple, or I should say just A. Even though A has also supplied a book of 1100, then also A will come. Why? Because we want the name of those suppliers who have supplied at least one book, and A has supplied a book of price 1000. Okay, so what we will do, check all the tuples, check if price is 1000, and from that tuple extract the S name, and you have to do all this on the table supplier, the attribute, the table, the condition. I hope the point is clear. Select S name from supplier minus select name from supplier where price is not equals to 1000. So this will give me the name of those suppliers who have supplied all the books of price 1000. Are you getting the point? Total, this is the total. minus price not equals to 1000. This will give me price equal to 1000. Total, which means all the possible supplier names minus those suppliers who have supplied book not equal to the price of 1000, which will give me the suppliers who have supplied all the books of price 1000. Okay. And then we will move to in, sum, and all set operators. Find the name of those suppliers who have supplied any book at a price equal to any price book supplied by Mirab. Let me repeat the question. Find the name of all those suppliers who have supplied any book at a price equal to any price book supplied by Mirab. For example, Mirab has supplied the books of the value 100, 200, 300, and 400. Now what I want? The supplier name who have supplied a book of price either 100 or 200 or 300 or 400. They have supplied at least one book of the price either 100 or 200 or 300 or 400. Are you getting the point? So I will write like this. Select what I want, the name. So S name from which table? The supplier table, where price in. Are you getting the point? Where price should be in this range, in this category. Select price from supplier where supplier name is Mirab. So this should be matched. If I am writing like this, price in, and then I have to extract price attribute only from this subquery. Let me repeat. What I want the name of all those suppliers who have supplied at least one book of any price book supplied by Mirab. So if Mirab is supplied 100, 200, 300, and 400, and there is a supplier name, let's say X, who has supplied different books of let's say 100, 150, and 350, then also this X will come in the output because X has supplied at least one book, which is in the range of this, which is included in this. So what is this? This query. This query will return me this. Find price from supplier where S name is Mirab. This will be returned from by this, and select S name, the S name from table supplier. This is the table supplier where price is in this. So what I'm going to do, check each and every tuple. Check this tuple, S name is X and price is 100. Is price included in this? Yes. Include this S name X in the final output. Check again. Is price included in this? No. Ignore. Check again. Is price included in this? Yes. Include X again. Because in will retain the duplicate values. Union, minus, intersection, they will remove the duplicacy, but in will inherently doesn't remove the duplicate values. In will retain the duplicate values. So check again. 300 included in this? Yes. So X will be included. Check here. 400 included in this? Yes. So Y will be included also. I hope the point is clear. Let me read the final query. Select S name from supplier where price is in this, which is select price from supplier where S name equals to Mirab. And if you are using in operator, make sure that these two values are matching. That whichever attribute you are writing with the help of in, that same attribute should be extracted in the subquery. Okay. Let's see some more interesting queries. Select S name from supplier where price is greater than sum of the prices of this subquery. What will this subquery return? The price of the books supplied by Destin. Select price from table supplier where the condition is S name is Destin. So let's say Diamond has supplied 100, 200, 300, and 400. These are the values of the books the Diamond has supplied. So I would look for the supplier name who have supplied a book with a price greater than sum of the prices from this table. So I can safely say, even if you have supplied a book of 101, you are welcome in my output table. But if you have supplied like 99, you are not welcome. So I'm using 100 at my advantage. I'm saying for price greater than sum of the prices in this table, I can say if you are greater than 100, you are welcome. So I will say this is the least price book supplied by Destin. So I will say find the name of those suppliers who have supplied book with a price higher than the least price book supplied by Destin. So if we have a table which has tuples y101, z99, a201, this will be included. This will be included because of 100. Let's see some more queries. Select S name from supplier where price is lesser than. If I have to include 399, is this price lesser than some of the prices from this table? Yes. So here I'm using 400 at my advantage. So I will say if you are a supplier who have supplied a book lesser than 400 or the highest price book supplied by Destin, which is 400, you are welcome in my output table. So this will give me the name of all those suppliers who have supplied a book lesser than the highest price book supplied by. Here the name is Max, so Max. So if we have a tuple X who have supplied a book of 399, this will be included because of 400. Here 101 was included because of 100. If you are still not getting this, I strongly recommend to take example and apply this query on that example. You will get the idea. Select S name from supplier where price is greater than all of the prices from this subquery. Let's say easy have supplied book 100, 200, 300 and 400. What I want, a price, a supplier who have supplied all the books who select S name from supplier where price is greater than all and then the subquery. So let's say we will take the same table that easy have supplied 100, 200, 300 and 400 value books. What I want, the S name from supplier where price is greater than all. So what I want, that the price should be greater than 400. If the price is greater than 400, then it will be greater than 100, 200, 300 also. So this all condition will be satisfied. So I should say the name of all those suppliers who have supplied at least one book at a price greater than the highest price book supplied by Easy. If that's the case, the all will be respected. If I'm allowing 500, which is greater than 100, 200, 300 and 400, which means all the books supplied by Easy are lesser than this. Okay. Select S name from supplier where price is lesser than all and then the subquery. Again, the same thing, just reversed. Find name of all those suppliers who have supplied at least one book at a price lesser than the least price book supplied by Easy. So I want the price, I want the supplier name who have supplied book lesser than 100. Okay, so if you want to mug up this, you can, but I would not recommend. Try taking some example, apply that query on that example and then solve and then think. Find price of the highest price book supplied by Atal. This is an interesting case focus. What we are doing, we are extracting the list of the price of the books supplied by Atal. And then what we are doing, among this, you have to select that price which is greater than all of the listed prices. Or I should say greater than equal to all of the listed prices, which means is 100 greater than all of them? 100, 200, 300, 400? No. 200 is not, 300 is not, 400 is. So I can say 400 is greater than equal to all of them. So select price from supplier where S name is Atal. In the same query here, select price from supplier where S name is Atal. This will give me this list. And I want that price which is greater than equal to all of them. Among this, I want that price which is greater than equal to all of them, which is 400. This is the answer. Let me repeat. Select price from supplier where S name equal to Atal and price is greater than all of the listed prices. So 400 will be returned in the output. If subquery has just one tuple in the result, then we can skip the in part and can directly use the relational operator. See the example. Select book ID from book where title equals to. I have not included in operator here. Directly equal to. Why? because select title from book where title equals to compiler design will give me just one tuple which is compiler design. So I will directly say select book ID from book where title equals to compiler design. See, this will not make much of the meaning here, but I want to just prove the point that you can do like this. If the subquery has just one tuple in the output, no need to use in operator. Let's see more queries on in operator. Select name from user where card number is in the range or in the table. Select card number from borrow. Have you realized this is a simple join operation on the attribute card number? This is totally similar to this. Select name from user, borrow. This is the Cartesian product, and this is equating the common attribute for the valid tuple identification. So select name from user where card is equal to this. Select name from user, which means user.card number should be equal to the card number from borrow. Find name of all those users who live in the same city as that of Arjun. Select name from user where city in, and then identify the city where Arjun lives, and you get the answer. So this will return me the city where Arjun lives, and select name from user, and this will return me all those users who live in the same city that Arjun lives in. But this will also give me Arjun in the output, which means if I obtain the list of all those users who live in the same city as that of Arjun, Arjun will also be in the list. I don't want that. So I will mention a condition also that name should not be equal to Arjun. Select name from user where name is not equal to Arjun and city is in the city where Arjun lives. I have already mentioned that these two should be matched. Find the name of those borrowers who have issued at least one book supplied by Kern. Find the name of all those borrowers. So I have to project the name from the Cartesian product is needed because of this supply and issued thing. So user and borrowed both are needed. User is needed because of name and borrowed is needed because of issued. So user Cartesian product borrow where user.card number equals to borrow.card number, and book ID should be in this. Book ID of all those books supplied by Kern. Let me repeat. What I want, name of all those borrowers. So this will give me the name of all those borrowers, but I have to match the book ID part. Where I will get the book ID? Select book ID from supplier where S name equals to Kern, which means this will give me the book ID of all the books supplied by Kern, and this book ID should be in this range. Are you getting the point? So I will get the name of all those users who have issued book in this with the book ID in this range, which is the book ID of book supplied by Kern, which means they have issued book supplied by Kern. Let's understand more. Write query to find the name of all those suppliers who have supplied book of the same title as issued to Connor. To solve this question, you have to think step by step, procedure by procedure. What we are doing here? Projecting the name of the supplier. So S name will be projected. We want supplier table. Title is also involved. We are equating the title. So book should be cross product with the supplier. And then title is equated with the title of books issued to Connor. So title should be in the list of the title of the books issued to Connor. So I have to first find the title of books issued to Connor. So I will use cross product between book, user and borrow, where this is the join, equating the common attribute and applying the condition that name should be Connor. This is username that should be Connor, and this will give me the title from the cross product of book, user, borrow, where name is Connor. So this will give me title of all the books issued to Connor, and this will give me the name of supplier who have supplied book of the same title issued to Connor McGregor. I hope this is clear. So we have covered union, intersection, set difference, in, sum, all. Let's learn some more. Contains, exist, not exist, and unique. Contains. When I say A contains B, which means B is in A or B is the subset of A. Let's understand with the help of example. This contain will return me true or false. If I say A contains B, then this contain will return me true or false based on the condition whether B is the subset of A or not. Okay, so select S name from supplier S where A contains B or not. So firstly understand what A is, what B is. Select title from book B, cross product supplier S1. So we have renamed the book as B and supplier as S1, where book.bid equals to S1.bid. This is the join condition. And one special condition that S1.name should be equals to S.name. This S1.name should be equal to S.name. Now let's understand. Suppose we have a tuple name S name John, or I should choose another name. Okay, John is okay. S name John. This is the tuple, and I have projected John. So S name is John. Okay. Now what I'm doing here, select title from book B, supplier S1, where book.bid equals to S1.bid, and S1.name should be equal to now John. So what I'm doing here, I am projecting the title of those books which are supplied by John. Select title from borrow user book. This is the join condition, and user.name should be equals to Yuyutsu. This will give me title of all the books issued to Yuyutsu. This will give me title of all the books supplied by John. Are you getting the point? So does A contains B or not? Contains B or not? So I will first start with the tuple 1, which is John. So does Yuyutsu has issued the books which are supplied by John? If that is the case, then this John will be projected. If not, then move to another, let's say easy. Check if A contains B, which means the books supplied by Easy contains the title of books which are issued to Yuyutsu. I hope the point is clear now. If that is true, which means Yuyutsu is reading the books which are supplied by Easy only, in that case, Easy will be in the output. Okay? By the way, do you know who was Yuyutsu? Yuyutsu was the only one Kaurav who has fought with the Pandavas in the epic Mahabharata war in Hindu history. Let's come back to the point. So what I was explaining, that we will start with the tuple 1. Select the S name. Equate with the S1.sname equals to S.sname, which means this will give me the list of title of the books supplied by John. And this should contain all the books which are issued to Yuyutsu. If that is the case, include John in the output. Nesting, we pick the first tuple of the original supplier table S and let S.sname equals to X. We have equated this to S1.sname of another copy of supplier table, and then what we did? We did the join here. Include only those tuple where S name is X, which means project title of the books supplied by X. This should contain title of all the books issued to Yuyutsu, which means this query will return me the name of all the suppliers who have supplied all the titles issued to Yuyutsu. There is important point. Qualifier of attribute can be removed if the attribute is present in one table, and not using the qualifier will not cause any ambiguity. Are you getting the point? Suppose book ID, it was present in the borrow table also and the book table also. If I am to project, if I am writing like this only, select book ID from the cross product of book and borrow, then whose book ID I want to project? The book ID of borrow or book ID of book? To resolve that ambiguity, we are using qualifiers, that book.book ID or borrow.book ID. But let's say if I'm using or I'm projecting the attribute name from the user, the name belongs to user only. The name is not present elsewhere. See, here was the schema. Here is the schema. The name belongs to user only. It's not present elsewhere. In that case, there is no need to write user.name. Okay, I think I have written here. There is no point in writing user.name here. It's already clear that name is the attribute of user only. So that was the point. Let's see another query. Select S name from supplier S, where select book ID from supplier S1, where S1.sname equals to S.name. This is again nesting. This should contain the book ID from book borrow user, where this is the join, and name is Jatayu. So what this is returning? Let's start again with the basics. Select S name from supplier S. Let's say this is the tuple from the original supplier table and X is the S name. And what I'm returning? Book ID from supplier, where the name is the supplier name is X. Book ID from table supplier S1, where supplier name is X. I have equated this. So this will give me the book ID of the supplied books by X. And this should contain select book ID from borrow user, where borrow.card number equals to, this is again the join condition, and name is Jatayu, which means the book ID of all the books supplied by X should contain book ID of all those books issued to Jatayu. Okay, so find name of all those suppliers who have supplied every book that has been issued to user named Jatayu. I think the point is clear. How are we going to use the nesting? We will take the tuple from the original table, start with the first tuple, X, assign the name X here, select book ID from supplier S1, where X is the S name, which means all the book IDs of the book supplied by X, and this should contain the book ID of those books issued to Jatayu. So name of those suppliers who have supplied every book that has been issued to user named Jatayu. Let's try one more. Find all those card number on which DBMS book is issued. We will again use the contains operator. Select card number from borrow B, where select title from borrow B1, book B2, where book, this is again the join between borrow and book, and this is nesting. B1.card number equals to B.card number. Let's say we start with the card number 101. The first tuple, in the first tuple we have the card number 101, C101. So this will give me title of all the books issued to C101. This query will give me title of all the books issued to C101. This is, understand this like a loop. We are on the first tuple. We are on the first tuple C101. If this condition is failed, we will move to the next tuple C102. Okay. Contains select title from book where title is DBMS. So list of all the titles issued on card 101 should contain the title DBMS. This will give me all those card number on which DBMS book is issued. Exist will return true if the result of subquery is non-empty. Let's understand from this query. Select name from user U where exist. Now this is the subquery. Select book ID from borrow B, supplier S, and user U1. Cross product, equating the common attribute. So here we have done the join part. This is join. And now here we are doing the nesting. Select name from user U. Let's say the user have this tuple, card number and name. Card number is C101 and name is Ilya. So C101 is U1.card number, and this value is set to U1.card number. So U1.card number is C101. And S name, which is supplier name, is Sangha. So this will return me the book ID of the books issued to card 101 supplied by Sangha. This will give me a full length cross product. Okay, and then card number should be equals to 101 and supplier name should be equals to Sangha. So I want book ID of those books which is issued to card number C101 and supplied by Sangha. And select name from user U. I want this name. So I can say if Ilya has issued at least one book supplied by Sangha, then include Ilya in the output table. Let's understand the full perspective. Where exist this query should not be empty. This should return at least one tuple. That's why I have said if Ilya has issued at least one book supplied by Sangha. So name all those users who have issued at least one book supplied by Sangha. Here we have started with the first tuple. If Ilya has issued at least one book, then Ilya will be included. If not, if the result of subquery is false, or if the result of subquery is empty, then exist will return false. If condition is false, then that tuple will not be included in the final table. In that case, I'll move to the next tuple. See, 102, name is Alex. And then I will check, has Alex issued at least one book supplied by name Sangha? In that case, include Alex in the final output, otherwise no. You can write whatever you want in the select clause, because the purpose of exist was to check whether subquery is not empty or not. So if you want to write title here, that's also good. You can write whatever you want. You can also even write like this. The main purpose of this is to check just that whether the subquery is returning something or not. If it's not returning something, the condition will fail and the name will not be included. If it is returning something, I don't care whatever, the condition will become true and that name will be included. This is the point I want to mention. The purpose of exist was to check whether subquery is non-empty or not. Exist will return true if subquery is not empty. Not exist will return true if subquery is empty. Okay. Let's understand the not exist part also. Select name from user u where exist. So that name will be included if this subquery returns something, and not exist, which means this condition should also be true, this condition should also be true. In that case only that name will be included in the final output table, because we are using AND. True is true in the AND operator case. So this subquery should return true, which means should return something, at least one tuple. And this query should not return something, zero tuples. In that case only that name will be included. So what these two queries are saying, let's understand that. Select star from borrow B, supplier S and user U1. We are doing the join here. U1.card number equals to U.card number and S name equals to Chetak. It's the same thing, that the user should have issued at least one book supplied by Chetak. By the way, Chetak was the name of legendary Rajasthani warrior Maharana Pratap, and Behlol Khan was the name of person who was cut by him with his horse armor helmet into two parts. Are you getting what I'm saying? Maharana Pratap cut this man in the battle of I think Haldigati into two parts, along with his horse, the armor and the helmet. That was the power of that legendary warrior. You should learn about him. He's really an inspiration. I'm also from Rajasthan, that's why he's like a god figure for us. Let's come back to the topic. Select name from user u where exist. This will return me the tuples of the book issued by, let's say, card number 101 and supplied by Chetak. Not exist, same thing, S name Behlol. So I want the name of all those users who have read or who have issued at least one book supplied by Chetak but not by Behlol Khan. Or if I have to say fully, then I want the name of all those users who have issued at least one book who supplied by Chetak and none supplied by Behlol Khan. Find the name of all those users who have issued at least one book supplied by Chetak but have not issued any book supplied by Behlol. Unique. It will return true when subquery will return no duplicate tuples. This unique will not going to delete the tuples or delete the duplicate tuples, that was the work of distinct operator. The unique will return either true or false. True if all the tuples are unique, false if we have duplicate tuples. So unique will return true when subquery will return no duplicate tuples. Select name from user U where unique. Now, see this. Select name, which means from table user, we are traversing the tuples. We will start with the first tuple with the name diamond and card number C110. This name will be included if this subquery returns all distinct tuples. Are you getting the point? Select name from user U where unique, and this is the condition. If this condition returns true, in that case, this tuple will be considered true, and I am extracting name, so diamond will be included only when this condition gives me unique tuples, or this subquery gives me unique tuples. Select u1.card number from borrow b, comma user u1. Borrow cross user, and we are projecting u1.card number or card number. And the condition is u1.card number equals to u.card number. And what is u.card number? The C110. U is the table. This was the tuple. Name was diamond, and C110 was the card number. So C110 will come here. And u1.card number is set to value C110. So from the cross product of borrow and user, if the card number is C110, that tuples will be included in the final selection. Let's say the final output is this. Of this subquery, the final output is this, which means there are 4 tuples. There are 4 tuples which include C110, which means the card number C110s have issued 4 books. So if Dustin has issued 4 books, which means duplicacy is present. If duplicacy is present, the diamond will not come in the final output. Are you getting the point? Let's say the next name is Ilya. Card number is C107, and it has issued just 1 book. So C107 will just come once, which means unique will return true. In that case, Ilya will be returned in the final table. Let's take another example. Let's say C108. From C108, I cannot find any tuple here, which means C108 has not issued any book, which means unique will still return true because duplicacy is not there. The C108 is not present. If not present, then also it will not be considered duplicacy. So I can safely use the word at most one. Can be present just once or not present at all. But if you are present twice, like this, unique will return false. So name Ilya C107 just once included. Max doesn't come. Also, it's also good. So name of the borrowers who have issued at most 1 book. At most 1 book. So with the help of unique, I can say at most 1. And what if I wanted exactly 1? With the help of unique, I will also mention the exist, because unique will ensure no duplicacy. Exist will ensure non-empty. So these type of tuples will be removed. So only those tuples will come, or only those names will come who have issued exactly 1 book. Okay. So from here I can see select name from user where unique and exists. So from this, non-duplicacy and non-emptiness are both imposed on this subquery. Select u1.card number from borrow b user u1 join condition and u1.card number equals to u.card number. Okay. Select name from supplier S where unique. Select s1.name from supplier S1. Cartesian product book where this is the join condition and this is the Cartesian, this is the nesting. So let's say the supplier name for the first tuple is Dan. S name Dan, s1.name Dan. So get those tuples wherever s1.name is Dan. So I'll get those tuples Dan, 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 which means Dan has supplied 3 books. Are you getting the point? Are you able to read these queries? Let me repeat. Select S name from supplier. What I want that the supplier name should come in the output from the table supplier S, where now I am specifying the condition. The condition is this subquery if returned the unique values. In that case, the name Dan can be included. Now let's understand what this subquery will return. I want those tuples where s1.name is Dan. So I have got those tuples, which means Dan has supplied 3 books, but I am using unique here, which means I again want name of those suppliers who have issued at most 1 book. So Dan will not be included in the final output. Okay. In the next lecture, we will learn the order by, group by, and having clause. Okay. Sorting tuples in output with the help of order by. What if you want to sort the tuples in the output like in ascending order or in descending order based on some attribute? For example, based on roll number, I want that all roll numbers should be in ascending order starting from 1 till 100. Based on, let's say, name, we want it to be in descending order starting with the name from Z and then going back to the A. If you want to do such thing in the output table, you can use order by. This is the syntax: select name from user, and before that attribute you can mention order by. This will give me name from user table, and the name will be in ascending order. See, the by default setting is ascending, so you don't have to mention anything, just order by before that attribute, and it will give you the ascending list. And for descending, you have to mention like this DESC. Here, select name from user, order by name, descending. For descending, you have to separately mention. And for ascending, let me tell you the keyword, it is ASC. And for descending, it is DESC. For ascending, you don't have to mention, it's by default, and for descending, you have to mention. Select S name, price from supplier, order by. For the S name, I want ascending sorting, and for price, I want descending sorting. Think about this. If you sort based on the columns, the table will not remain meaningful. Let's understand. Suppose I have this table, the name and price. Ilya has supplied a book of 100, Izzy of 200, Ilya again of 300, Izzy of 400. Ordering doesn't happen column wise. What if we have done column wise ordering? For example, firstly we have ascending sorting we have done for this name. So we have Ilya, and then Izzy. And then separately we have done the descending sorting. Then we have 400, 300, 200, and 100. Are you getting the point? We have done like this: Ilya, Izzy. For name separately we have done the sorting, and for price separately we are doing the sorting. So we have Ilya 400 and Izzy 100. Is this tuple present here? Has Ilya supplied a book of 400? No. Has Izzy supplied a book of 100? No. So the table has created the tuples which are not actually present. So sorting is always done tuple wise. Otherwise, if you are doing sorting column wise, then it will produce invalid tuples. Are you getting the point what I am trying to say? If you are applying this order by on 2 attributes, let's say one ascending and one descending, then you don't do sorting column wise. Sorting is always done tuple wise. Okay, otherwise the values will be mismatched. Here Ilya has supplied a book of 100 and 300. Here Ilya has supplied a book of 400 and 300. So these two tuples are not actually present. These are wrong tuples. So how we will do then? Focus here. It's not exactly what you think. Order by primary and secondary. So based on primary, we will first do the sorting. Primary is name, so we will do the sorting based on primary ordering. So Ilya first, and then Izzy. This is the sorting we have done based on name, the ascending sorting. Now descending sorting is a secondary. So what we will do, we will fix this. We will fix the name, and on this cluster we will apply the secondary sorting. Select S name price from supplier, order by,
S name ascending and price descending. So we want the ascending sorting on this attribute S name and descending sorting on this attribute of price. Now if you think carefully, if you think doing the sorting based on columns or attributes, things will go south. The table will generate those tuples which are not actually present. So ordering doesn't happen column wise. Let's understand with the help of example. Suppose we have two suppliers, Ilya and Easy. Ilya has supplied a book of 100 and 300, while Easy has supplied a book of 200 and 400. Now what we want, ascending sorting on name. So we have done ascending sorting on name first. So Ilya will come first and then Easy. Ilya and then Easy. And then we want descending sorting on price. So we have done the descending sorting on price. Now have you noticed? This has created invalid tuples. Ilya has not supplied a book of 400 ever. But here he is supplying. Easy has not supplied a book of 100, but here it is supplying. So if you do sorting column wise or attribute wise, the final output table will generate invalid tuples. That's why the safe play is sorting is always done tuple wise. The whole tuple is sorted. Okay, so ordering doesn't happen column wise, it happens tuple wise. Otherwise, the values will be mismatched. See here. So this is the primary one and this is the secondary one. Based on primary sorting, we will sort first. So we have Ilya who has supplied all these books and Easy who has supplied all these books. So firstly, you have to sort based on name. Ilya will come first and then Easy. We have sort based on the name. Now, we will not apply sorting on this whole. For price descending, we will not directly apply like this. What we will do then, we will fix the name and then we will apply this secondary sorting on this cluster 100, 200, 300 and 400 only. And then for Easy, we will apply sorting for this cluster only. Are you getting the point? So we will fix the primary sorting attribute and then for the remaining values, we will apply the secondary sorting. We have fixed the primary attribute and for secondary, we have made the cluster and then we will apply the secondary sorting. Are you getting the point? So it will look like this. Ilya is fixed and then sorting is applied here on this. So 400, 300, 200 and 100 and then Easy is fixed and then sorting is applied here. 800, 600 and 400. I hope you are getting the point. For order by, if there are more than one attribute on which different type of sorting is going to be applied, then you have to identify which one is primary and which one is secondary. So first one will be primary. Sort based on the primary attribute and then fix the primary attribute for the remaining tuples or for the remaining values, I should say, for the remaining attributes. After fixing the primary attribute, you have to search for remaining attribute. The remaining one is this, the price. So for the remaining attribute, you have to apply the secondary clustering, fixing the primary attribute. I hope the idea is clear. Let me repeat again. Firstly, this was primary, so sorting will be done based on name. After the name sorting is done, fix the name and then for the remaining attribute, you done the sorting. Okay. Secondary ordering doesn't happen on the whole table, only where the primary ordering is fixed. For Ilya, we will fix this. For Easy, we will fix this. And then we'll apply the secondary sorting, not on the whole. Okay. Now we'll move on aggregate function in SQL. We will again use the same schema: book, user, borrow and supplier. Book have book ID, title and year of publication. User have card number, name, city. Borrow have book ID, card number and date of issue. Supplier have book ID, S name, supplier name, price and date of supply. These are the aggregate functions: minimum, maximum, average, sum and count. So if I say find price of highest price book, then you will write like this: select, and then you apply this aggregate function on an attribute. So you write like maximum price from supplier. So this will return me the highest price book supplied. Okay. Find price of highest price book supplied by ABC. So we will write like this: select maximum price from supplier where S name is ABC. I hope you are learning how to use these aggregate function. Aggregate function are applied on some attribute. Like select maximum price, and then the remaining queries are same. How many books are supplied by supplier ABC? We will use this count. We will write like this: select count star from supplier where S name is ABC. So we have written like this, count star. This is going to count the number of tuples where the name is ABC from the table supplier. Okay, count star means you are not counting some specific attribute value, you are counting the whole tuple. So select count star will count the number of tuples where the supplier name is ABC. Count star, count the number of tuple or rows. How many copies of DBMS book are present? Select count star from book where title is DBMS. This is so easy. You have to just understand how are we going to use this aggregate function. To count the number of tuples, you can use count star. To finding maximum, you can use max, minimum, min, average, sum. All these are easy part. How many books are issued by ABC? Select count star, user borrow. This is the join and then name is ABC. Simple case. How many books are issued? Just this. Then select count star from borrow. That's it. From borrow, the total number of tuples will tell me the number of book issued. See here. Book ID, card number and date of issue. So for borrow, the total number of tuples will tell me the number of books issued. Okay. List maximum price, minimum price, average price of all books supplied by each supplier. All books supplied by each supplier. Select S name, then maximum price as max P, minimum price as min P, average price as average P. We have renamed these attributes. Okay, from table supplier. So this will not exactly give what we want. You should pause and think why this will not give what we want. We want the maximum price of a book, minimum price of a book, average price of the book supplied by each supplier. So for each supplier, I want different values, but here this maximum price, minimum price and average price is applied on whole table. So if I write like this, select S name, then maximum price, minimum price and average price from supplier. Let's say the maximum price of all the books supplied by each and every supplier, all on the whole, then the maximum price is 300. It's the highest price book supplied. Minimum is 50 and average is, let's say, 200. Then for each and every supplier, we will see the same value because we are talking not about a specific supplier. We are calculating this maximum, minimum and average value, incorporating all the suppliers present in the table. Okay, what we want the maximum price, minimum price and average price of a book supplied by each supplier. So for Easy, I want the maximum price of a book supplied by Easy, the minimum price of a book supplied by Easy, average price of the book supplied by Easy. For Ilya, I want maximum price of a book supplied by Ilya. Are you getting the point? So this will not give me what we want. This will produce this result. This is not what we want. Minimum, maximum and average is working on a whole table, not on an individual supplier. I want to pick a supplier, search that supplier in the whole table, create a logical group of those supplier of those tuples, and there I want to apply these aggregate functions. Are you getting the point? So for let's say if I want minimum price of a book supplied by Easy. So for Easy, I will search for Easy in the table. I have identified, let's say, 15 tuples with the S name Easy, which means Easy has supplied 15 books. Out of those 15 books, now I have to search for the minimum price book. So I have to create a logical table inside a table with just S name equals to Easy. Are you getting the point? Let's say this is the whole table and these are the tuples where S name is Easy because these are the books supplied by Easy. So I want to break this table, and on this smaller table I want to apply the maximum, minimum, average. We can do this with the help of group by. Group by is logically breaking the table based on a specific attribute. So what will be the attribute in our case? Think. Supplier name. We want to break the table based on supplier name. And when we do this, then we will get the individual maximum price book supplied by a supplier, minimum price book, average price book. Easy has supplied the maximum is 270, minimum 110, average 90, Ilya 290, 70, 107. Are you getting the point? So list the titles and number of copies of each title present in our library. Select title, count star as title count from book. This will give me, or this will work on the whole table. List the title and copies of each title. No, this will give me answer like this. For example, we have 1000 book in our library, so it will give answer like this: DBMS 1000, OS 1000, compiler design 1000, computer network 1000. Are you getting the point? This is not what we want. We want the number of copies present of DBMS, operating system, compiler design, computer networks, different specific copies. Let's say DBMS has 10 copies, OS has 70 copies, compiler design has 80 copies, computer network has 30 copies. We want answer like this. How are we going to achieve that? With the help of group by. We will group by titles. See, if you are getting confused which attribute we have to use with group by, think on which attribute you want to logically break the table. Here we wanted to break the table based on DBMS. What we will do, let's say we'll starting with DBMS, we will search for DBMS in the table, the number of tuples where DBMS is title. And then you have to pick those tuples, make a separate table based on those tuples, and then count the number of tuples. This is what we are doing. So for counting the tuples, we will use count star. So select titles, count star as title count from book, group by titles. So we are breaking the table based on title. So we have shorter tables in a bigger table like this: DBMS, OS, compiler design. And then we will apply count star on this. So count star will just count the number of tuples in this shorter table, just the number of tuples in this operating system table. Are you getting the point? List the name of borrower and number of books issued by him or her. Select name, count star as borrower count from user borrow. This is the join. And then what we have to do, group by name. List the name of borrower and number of books issued by him or her. What we want a table like this. Ilya has issued 10 books. Izzy has issued 15 books. Alex has issued 20 books. Again, what we are doing, we are searching for, let's say, Ilya. We will search the whole table wherever S name is Ilya. We'll pick those tuples, push them into a separate smaller table, and then apply count star on that smaller table. So on which attribute we are breaking the table? Name. Okay, I hope the usage of group by is clear. Let's understand some important point regarding group by. All attributes used in group by clause must appear in select clause. And the second point is, any attribute that is not present in group by clause and we want to display that attribute in the output, so that must appear only inside aggregate function in the select clause. Let's understand them. Find the number of books supplied by each supplier. So we have to group by based on supplier name, but we are not including supplier name in the select. This will give me a meaningless table. For example, book count 7, 10, 10, 2, 3. What does this represent? Book count what? Number of books issued, number of books present in library, number of books supplied. What does that mean? So this will give me a meaningless query. That's why they have made it as a syntax error. So you have to include the S name in here select. So whichever attributes you are using in group by, those attributes must come in the select clause. Okay? Like this. Select S name, count star as book count from supplier, group by S name. Now suppose I also want to include a price attribute in the output, then directly including price like this would be absurd. For example, I have included select S name, count star as book count, and then price. Do you think this price will give us some meaning? Let's say the name is Shabri, book count is 21, Shabri has supplied 21 books. Now price what? Price what? Which book price? Are you talking about the maximum price book or minimum price book, or are you talking about average price, the sum of all the price? What does that mean? That's why to give that meaning we have to use like maximum, minimum, average, aggregate operators. So what would this price include? That's why if you want to include some attribute which is not in the group by, I have to include that with aggregate function like maximum price or minimum price. Select S name, count star as book count, average price as average price from supplier group by S name. Now this will give this tuple a meaning that Shabri has supplied 21 books with an average of 300 value. List the number of books issued by user on the same date. For example, user has issued 4 books on date this. We want this table in the output. User A has issued 2 books on this date 13. User B has issued 3 books on 12. User B has issued 6 books on 13. We want this table in the output. How we will going to achieve that? Select name, count star as number of books, name, username, I should write here name, count star is number of books, and date of issue. From user Cartesian product borrow, this is the join we have done. Now the question is on which attribute we have to apply, which attribute we have to logically break the table. I should close the windows, making a noise. Okay. So the question was on which attribute we have to apply group by. We'll apply on name or date of issue. If we apply on name, then we will not receive 4 and 2 here because we want this type of table in the output. We want the number of books issued by user on the same date. A has issued 4 books on 12th May, has issued 2 books on 13th May. We want output like this. But if we apply group by on name, we will receive output like this, 6 and 6. We will not segregatedly receive 4 and 2. If we apply group by on date of issue, then A has issued 4 books on 12th May, B has issued 3 books on 12th May. If we are applying group by and then count star, then we will receive 7 and 7. We will not segregatedly receive 4 and 3. So if we apply group by based on name, we will receive like 6 and 6. If we apply group by based on date of issue, we will receive like 7 and 7. Both are not right. So we have to take both attribute into consideration. Select name, count star as number of books, date of issue from user borrow, where user.card number equals to borrow.card number. This is join group by name comma date of issue. Okay, and they should both be present in select clause also. Find title of the books which has more than 50 copies. Now this is an interesting case. We are also applying a condition after group by. Select title from book, group by title, where count star is greater than 50. Is this correct? No. The thing is, we do not use where after group by. Where is used after from before group by, but after group by, we will use a separate clause which is having. So having will specify the condition. We do not use where after group by, we'll use having like this. Select title from book, group by title, having count star is greater than 5. Okay. Find those card number on which more than 5 books are issued. Here should be 50. Find those card number on which more than 5 books are issued. Select card number from borrow, group by card number, and then specify the condition with the help of having count star is greater than 5. Easy. Find name of all those borrowers who have issued more than 5 books. Again, just apply the Cartesian product between user and borrow, equate the valid tuples, project the name, and the condition is also applied. Group by name having count star greater than 5. That's it. Now there is an important point. Direct attribute comparison in having clause is not allowed, but is allowed with aggregate function or set operator. Let's understand this point with the help of example. Suppose we have a table R. We have 2 attributes A and B. From table R, we will group by on A. We will group by on A. So group by on A, 1. It has 2 and 1 and 3. So if we group by on A, which B will come here? 2 will come here or 3 will come here. Which B will come here? This is the confusion. This is the confusion. So direct attribute comparison in having clause is not allowed. If you are projecting B, which is not present here in the group by, then which B will come? 2 will come or 3 will come? This is the point I was discussing here. Any attribute that is not present in group by clause and we want to display it in output, we want to display B in the output which is not actually present in group by, then we cannot directly do like this. We have to, it must appear only inside aggregate function in select clause. So we will use aggregate function in select clause, because we have to remove the confusion, we have to remove the ambiguity. If we are directly doing like this, group by on A, then which B will come? 2 will come or 3 will come? But with the help of aggregate, we will remove the confusion that sum is going to come. So output will be like this: 1, 5 and 2, 10. Okay, 5 and 10. So 1, 5, 2, 10. Same confusion while applying the condition of having A from R, group by A, having B greater than 3. Again, which B are you talking about? Which B should be greater than 3? So we have to solve this with the help of either some aggregate function or set operator. Confusion will be cleared. So the direct thing is, wherever confusion is there, they have made it as a syntax error. So this will be a syntax error. But again, I will say different versions of SQL have different syntaxes. For example, MySQL doesn't throw error when you use having without group by. If you do like this, then each tuple will be considered a separate group, just like the where. Here I have written direct attribute comparison is allowed with where but not with having clause, because where whole table was considered. Here we talk about groups. The whole point is not to get confused. Wherever confusion was present, they made it as a syntax error. So the general flow is like this: where, group by, and having. This is the flow which is generally used, but different versions have different syntaxes. For example, in MySQL, if you don't use group by before having, then it won't show error. Every tuple will be considered a separate group, which means it will act like where. The whole table will be considered. Where clause can't have aggregate function. For example, like this: where count star is greater than 5. This will throw error. Okay, so these are the points that need to be discussed. Okay, in the next lecture, we will learn how to handle nulls in SQL. In this lecture, we will learn to handle null in SQL. Find the book ID of those books which are not issued. So we might think we can do like this: select book ID from book where SID is equal to null. Will this work? No. This will give me an empty relation because null is unknown. And when we will compute the SID with unknown, what we will get? Will we get true? No. If you are not getting true, then where will not include that tuple into the final output. That's why we will receive the empty relation. So null is unknown. We cannot equate SID with the unknown. But we have to do something. We have to compare. So how we will compare? With the help of this: is null or is not null. Select book ID from book where SID is null. Well, this is correct. Instead of doing like this, equal to null. Okay. So people have wrong assumption about null, that null is blank, empty, zero, nothing, missing value, lowest value, ignorable value, optional value, invalid, void, garbage value. Null is not this. Null is a keyword to represent the unknown. Null is not blank, empty, zero, or all this. Null is what? Unknown. Select A from R1. Well, we have these two tables, R1 and R2. And the query says select A from R1 where B in select B from R2. So we have to select those tuples, and from that tuple we have to select A where this B is present in this. So 2 is present, so A1 will be in the output. 4 is not there. There's our null. Null is not comparable to null because unknown is not comparable to unknown. 8 is present, so 1 and 7 will be in the output. Select A from R1 where B is greater than sum of the, and B is from R2. Select A from R1. We have to project A from those tuples where B is greater than sum of these B's. So is 2 greater than sum of these? No. 4 is greater than? Yes, 4 is greater than 2. We are searching for at least 1 because for sum we will search for at least 1. If 4 is greater than this, then this 3 will be included. and then is 8, yes, so 3 and 7 will be the in the output, and in is equivalent to equal to sum. Okay, select A from R1 where B is greater than equal to all, and then the B should be from R2. We have to select, so we have to project the A's from those tuple where B is greater than all. Is 2 greater than all of them? No. 4? No. I think 8, but no. 8 is not greater than this because null is unknown, and 8 is not greater than unknown. So empty relation we will receive in the output. Even though 8 is the biggest looking number, no matter whatever the relation, all will always return empty relation if null is present in the subquery, because null is not comparable to any number. Are you getting the point? That's why no matter whatever be the relation, all will always return empty if null is present in the subquery. Here all is present, and in the subquery null is present, we will receive a, okay, not equals to all is similar to not in. So not in will also return false if there is even a single null in the subquery. Okay, so for null, if we have in and null is present in the subquery, we were getting some of the tuples in the output. And for all, if the subquery has null, we will receive an empty relation. But what about not all? Not all is equals to not in. So not in will also produce empty relation, just like not all. Not all and not in will produce empty relation if there is even a single null in the subquery. So the behavior of in and not in will be different. This point should be clear. In will return something, not in will not return something if there is even a single null in the subquery. I think the point is clear. What about for between? Select A from R1 where B is between 2 and 8. In that case, everything is okay, but what about if I set either the upper limit or the lower limit or any one of them null? In that case, we'll always receive false. Order by will treat null as the lowest value. So if we have this kind of relation and we apply order by, then null will be treated as the lowest value. We will receive 2, 6, 7, 8. Or here we will receive null and then 2, 4, 8. Okay, so order by will consider null as the lowest value. Select star from R1 order by B will receive like this. After select, the null will come multiple times. If I'll write distinct, then multiple nulls will be removed. If I apply like this, select B from R1, then I will just get this. And then when I apply select distinct B from R1, then 2, 4, 8 and 1 null will come. The nulls will be considered duplicate. Okay. So after select, the null will come multiple times. If we will write distinct, then multiple nulls will be removed. Group by clause will treat all null as equal values. They will be grouped. See example here. 2, 2 will be grouped like this. 4, 4 will be grouped. 5, 5 will be grouped. And these 3 nulls will be grouped. So null are considered equal values for group by clause. All aggregate function ignore null except count star. Focus on the star. Because if I write like this, count A, then 1, 2, 3. Just the value will be 3. But if I write like this, count star, where A and B both are considered, all the attributes are considered of the table. And then there we see a tuple in which all the values are null, like this. That tuple is counted. You have to understand this point carefully. All aggregate function ignore null, except count star. Even count will also count. For example, count A, then the answer will be 1, 2, 3. This will be ignored. Count star will ignore. But count, just count will ignore. Count star will count. 1, 2, 3, 4. Are you getting the point? Count star will count. Simple count will ignore. If I write like this, count B, then there are all nulls, will ignore all, the answer will be 0. And rest of the functions, aggregate function will automatically ignore null. What is the sum of A? 3, 2, 1 is 6. Average of A, 6 by 3, which is 2. Maximum of A, 3. Minimum of A, 1. That's it. And if I apply same on B, then sum of B will be null, average of B will be null, maximum of B will be null, minimum will be null. I hope the point is clear. Let me repeat again. For select, the null will be considered duplicate, and select retains duplicacy. So null will come the number of times the null is. But if I apply distinct, then only once the null will come. Multiple nulls will be removed. Group by clause will treat null as equal values, and all aggregate function will ignore null except count star. So when all the attributes of a table are considered while counting the tuples, in that case only these kind of tuples will be counted. Otherwise, if we count like this, how many counts? If I write like this, count A, then 1, 2, 3, that's it. But if I write count star, then all the attributes are considered, then these type of null values are also counted. I hope the point is now clear. Okay. Note, if null appear in aggregated attributes, then all these nulls are ignored. If null appear in grouping attributes, then all these null will be treated as equal value and from single group. We have discussed that. Note, if null appear in aggregated values, then all these nulls are ignored. If null appear in grouping attributes, then all these nulls will be treated as equal and form a single group. We have discussed this. I think we have to make a summary and then understand better. Wait a minute, let me write the summary. And relational operator, no comparison allowed. These type of comparison are not allowed. They are usually evaluated to unknown, neither true nor false, and where will not care. Only that tuple will be included in which where returns true. Otherwise, either false or unknown, the where will remove that tuple from the final output. Null and in does not make a match with a value which is null. We have discussed that null and sum similar as in equivalent to equal to sum. Okay. Null and all will always return false if the subquery contain at least one null. Null and not in false if subquery contain at least one null. Not in is equivalent to not all. Null and between, it will always return false if the lower or higher bound or both values are null. Null and order by, treat null as smallest values. We have discussed that. Null and group by, treat all null as equal values. We will group the null together. Okay. Now let's understand pattern matching in SQL. By pattern matching, we mean string matching, and percentage sign we represent match with any number of characters and underscore match with exactly one. For example, A and then percentage. All strings starting with A. A then any number of characters. All strings starting with A. All strings ending with B. Any number of characters and then A. Any number of characters AB and then any number of characters. AB as substring. Underscore house. Here just one character, either mouse, house, these type of words will be accepted. I hope the point is clear. Any number of characters, exactly the number of characters which is equal to the number of underscore. For example, this means 4 characters. Okay. SQL uses like keyword for string matching. Find name of all those users ending with A. Select name from user where name like this ending with A, any number of characters and then in the end A. Find name of those users who have exactly 3 character name. So these 3 underscores. This will represent any number of characters and then 3 characters and then any number of characters. In any number of characters, we also include 0 character. So here it could be 0 or more. Same here. And 3 underscores, which mean exactly 3 characters. So I can say at least 3 character will be there. Similar can be said for this and for this. 0 or more and then 3 underscore, 0 or more, which means minimum 3 character name is there. Okay. Similar for this underscore, any number of characters and then 2 underscores, same thing. To use percentage as actual meaning, what about like this? I mean 5%, which means 5 by 100. In that manner, if I am going to use like this, SQL may understand this as starting with 5 and then any number of characters. So we have to explain SQL that we are not talking about this as any number of characters. We actually mean by percent. So we will use escape character, which is backslash. We have learned that select clause is like a projection with duplicacy. Select clause retains duplicacy. we can change this setting, which is by default. Then it will return the distinct values only. Now we want to gain the duplicacy, or we want the duplicate values to come in the output. We can use select all. That part we have learned. We have also learned that union, intersection, set, difference, which is minus or except, removes duplicacy. So union by default eliminates duplicacy. But if you want to retain it, you can use union all, just like select all. So from here, select B from R1, union all, select B from R2. So from this part and this part will be just joined here. This part and this part, it's like just added. Same thing can be said for intersection, intersection all, except and except all. This part is clear. What is this? Union by default eliminates duplicacy. Similarly, intersection and except by default removes duplicacy. If you want to retain it, you can use union all, intersection all, or except all. In sum all automatically retain duplicate values. This we have also covered before. Aggregate functions retain duplicate values. Okay. Handling empty queries in SQL. In will always return false if subquery is empty. Sum will always return false if subquery is empty. All will always return true if subquery is empty. Think carefully. Here, in and sum are searching for the values which are going to satisfy the condition. All is going to search for the value, at least one, which is going to dissatisfy the condition. If all has found even one value which is going to dissatisfy the condition, the subquery with all will return false. Okay, and if subquery is empty, which means all is not able to find any of the tuple which is going to dissatisfy the condition, then this will return true. In and sum think this way: if we can find even one tuple that will make my condition true, we would include that tuple in the output. All things this way: can I find even one tuple that will make my condition false? So having an empty query is also okay for all. If the subquery is empty, then all will not be able to find that one tuple which is going to make the condition false. So in that case, all will always return true. Okay. Different representation of queries. From clause can contain select clause. See this. Select max P1 from, and this is the table. So from clause can also contain select clause. We call these type of queries as complex queries. So this is going to return a table. Let's say this is the table, and from that table we are going to select the maximum priced attribute, the P1 maximum value. So this is going to return this table, and from this price we are going to return the maximum price. So this is similar to select max price from supplier. This is just a way to represent that complex queries looks this way. It's easy. It's not kind of that complex. First you have to understand the subquery, and then consider this as table, and from on this table you have to apply this. That's it. First understand the subquery and then consider it as a table, then solve for outer query. That's it. Use of with clause. With maximum price, price 1 as select max price from supplier. So see, we are going to name a table. The table name is max price, and price is the attribute. This is the table name and this is the attribute, and this is same as select max price from supplier. So here it should not be max price, it should be price 1, and the table name is max price. Okay, let me explain again. With use of with clause, you can create a kind of new table. With max price, this is the table name, this is the attribute as select max price from supplier, and select s name from supplier max price, where price equals to price 1. Name of those suppliers who have supplied maximum price books. That's it. You, with the help of this, you have created a kind of new table, and the table name is max price and the attribute is price 1, and you can perform join with the supplier and max price. In supplier and max price you have performed join, and price equals to price 1. So you have created a new table to solve a new query. Are you getting the point? See, if you have created this table and now you are looking at this query will look very simple to you. What we are doing, select S name, we are projecting S name from supplier and a table named max price, where price equals to price 1. Now we will look here with max price. Oh, max price is the table name and price 1 is the attribute as, and this is the max price table. Select max price from supplier. Are you getting the point? The use of with clause. Now coming to the next topic, joins in SQL. Again, we have already read about this joins and other things in relational algebra. Here we are going to cover up the syntax part. Inner join and outer join. Inner join will only contain the matching tuples in the output. Outer join will have matching as well as non-matching tuples. And we have discussed about this. Left outer join, right outer join, full outer join. We have discussed that in left outer join, we will include the matching tuples and the non-matching tuples of left hand side table. In right outer join, we will include the matching tuples and non-matching tuples of right side table. And full join, we will include the matching tuples and non-matching tuples of left side table and right side table. Okay, we will see the syntax now. Let's begin. Select star from R1 inner join R2 on R1.c equals to R2.c. This is the on predicate part. On and then the condition. Here inner is optional. You may see directly like this. Select star from R1 join R2. And here's the condition. So this is similar to R1 join R2 where this is same. See, this is similar to the theta join. Are you getting the part? Theta join. Here it could be a different condition also where R1.c can be greater than R2.c. Okay, so this act as a theta join on predicate where predicate can be any condition. So when I write like this, select star from R1 join R2 on R1.c equals to R2.c, you have to remember that we will include both the attributes of both the table, that R1.c and R2.c both will be included in the final table like this 3399. In natural join, we have discussed that you will take or you will see you will take C just once in the output table. It will look like this: A, B, C, D, E. That's it. C will not be broken into two parts, R1.c, R2.c, which is done kind of here. Okay. Natural inner join. Again, inner is optional. You can even write or not write. This is similar to Equi-Join. You will just write C, not R1.c, R2.c. And one more point, it's a good practice if you write the matching tuple, or if you write the matching attribute in the first place. If it is like this, A, B, C, B, C, D. Then in the output table, you write like this: A, B, C, A, D. You write the matching attribute first. Here also, C was matching, so we write the matching attribute first. It's a good practice. Let's understand applying join with the help of using. Using is a kind of thing to restrict the effect of natural join. In natural join, we will use each and every matching attribute. For example, here BC was matching, so we will see for the whole tuple 2, 3, 2, 3. So 1, 2, 3, 4 will be the tuple, and we have told you that the matching tuple, the matching attribute will come first. So BC will come first. So 2, 3, 2, 3 will come first, and then 1 and 4, 1 and 4. Similarly here 8, 9, 8, 9. So 8, 9 will come first, and then 7 and 2. This was natural join. BC was common, so we will try to match BC. But if you want to restrict the condition on common attribute, we can use using. Select star from R1, join R2 using B. If we have specified using B, then which means now even C is common in both, but we will not try to match C. Okay, here this part will also be included even if C is common. Are you getting the point? So we will just try to match B. Wherever B is being matched, we will apply that. 1, 2, so 1, 2, 3, 4. That's it. And again, R1.c, R2.c, now they are different. Now they will be considered different because this is not included in the natural join part. So R1.c, R1.c will be considered. And then see where B is being matched. 5 is not present here. 8 is present here. So 7, 8, 9, 8, 9, 2. And the matching attribute will come first. So this will come first, and then 7, 9, 9, 2. Okay. A, R1.c, R2.c, and D. A, R1.c, R2.c, and D. So 7, 9, 9, 2. 7992, and the matching attribute will come first. Okay. Outer join, again this outer part is optional. Now how we will identify whether this is outer join or inner join? If inner and outer both are optional, see, if you do not write anything, it will be considered inner join. For outer join, you have to specify it's left outer join, right outer join, or full outer join. They will help to distinguish. Okay, so we'll write like this: select star from R1 natural left join R2. Okay, so in this case, the matching tuple will come from here, and then extra part will come from the left table because we are doing left join. Okay, so this is like this: 2 3 2 3 was matched, 1 2 3 2 3 4. So 2 3 will come first, and then 1 4, and then 8 9 8 9. So 8 9 will come first, and then 7 2. 8 9 will come first, and then 7 2. And now the remaining part from the left hand side table. The remaining part from the left hand side table, this 5 6 4 5 6 4, and there is no matching at this side, so null. And then 4 7 5 4 7 5, no matching at that side, so null. Okay, if we do like this: select star from R1 natural right join R2, then extra part will come from the right table, natural join, and from right table the extra part will come. Select star from R1 natural full join R2, extra part from both the tables, natural join from right table and from left table, full outer join. Outer join on predicate. On predicate, what we will do? We will specify on and then the condition. R1 dot B equals to R2 dot B. And then here we have written right join, so extra part will come from the right table. Restricted natural outer join, and to restrict the effect of natural join on attributes, we will use using. So when we will mention using B, so B will come just once, and then R1 dot C, R2 dot C. And then the extra part will come from the right table. Here null will come. Okay. In the next lecture, we will learn to modify the database. We will learn about insert, delete, and update. Till now, we have been retrieving the data. Let's understand to modify. We will understand insert, delete, and update. Insert and delete work tuple by tuple. They will work on the whole tuple, while update works cell by cell. If you want to update a specific cell, update can do that. Delete all tuples from borrow relation. You just mention delete from borrow. That's it. And all the tuples will be deleted. But you have to remember that schema or the table structure will still be there. Delete entries of all books corresponding to the borrower Rathod. So delete from borrow where card should be in this range, which is of the username Rathod. That's it. And the corresponding entries to the borrower Rathod will be deleted. Insert, you can insert in various ways. Insert into book values. If you remember the corresponding attributes, then you can directly mention the values. B101, DBMS, and 2000. If you are not sure whether, not sure of the order of the attributes, then you can mention them. Title, DBMS, book ID, B101, year of publication, 2000. Even if you do like this, book ID, title, and then you mention like here B101 and then DBMS, that's also okay. Insert into book, B101, DBMS. Well, this is not a good practice if you are not inserting all the fields. You should mention insert into book, BID, title, and then insert values. And the remaining field, which is of year of publication, will be by default set null. Update command. Update date of issue to 15th April 2020, where book ID is B101. Update borrow. Set, you use word set. Update and then set. Update borrow, set date of issue to this, where book ID is B101. Give 5% discount on all the books supplied by ABC having price greater than 1000. Again, same thing. Update supplier, set price equals to 0.95 into price. You can, by doing like this, you can generate the effect of 5% discount, whereas name is ABC and price is greater than 1000. Simple thing. Okay. Now, interesting part. View or virtual tables in SQL. View are important concept. View are generally used for security purposes. They are not actually stored inside the database. Rather, they are evaluated or temporarily created whenever we apply a query on it. Understand with the help of example. This is the syntax: create view, and then you mention the name of table as, and then the query. Like this: create view. This will be the table name as, and this will be the table. Select book ID, title from book, where year is 2014. So this table will be stored as book 2014 and this will be stored in data dictionary. But remember, this won't be created directly. First, select title from book 2014. This will be created, and then when the query will be run on this, then 2014, the view will be created temporarily inside the data dictionary. Okay. And with the help of view, you can actually simplify the queries. See here, the definition of view is stored in data dictionary and it is created every time we create a view. This will actually help some other user to understand query better. It will look simpler. See here, you just have to mention this and then select title from book 2014, and then user will automatically see the view that this is okay, this is 2014, and I have to project the title from this table. This will make the query look simpler. Along with this, view also provides security. Data hiding is possible with views. So the database administrator that we have discussed in our second lecture, I guess, will give you permission on views, not on the actual tables. So there are different type of views we will see in few minutes. The permission of reading, updation, inserting, or changing the view, or which part of table that you can view, that thing is included in the view itself or the virtual table. So the permission are given on those virtual table, not the actual tables. Create view supplier table as select as name title from supplier book where supplier. We have this is join, and after the join has happened, we have named that table as supplier table. Now we have supplier table. Now see this query. Select title from supplier table where S name is Thakur. So easy and simple looking, where just you know that supplier table is what? The join of supplier and book. That's it. Different type of views based on accessibility. Updatable views, you can update things, insert, update, delete on these views. And when updation happen on the views, the actual tables are updated. Otherwise, what's the meaning of updation? If you are updating the virtual table and virtual tables are temporary, what is the meaning of updation then? They will be just erased after a few minutes. Read only views. You can only read from these views. You cannot insert, update, delete data through them. Typically applies to complex views or those using joins, aggregates, or group by. And this updatable views are on the simple tables. And if we are using complex views like joins, aggregates, then we keep it as a read only. Based on structure, we have simple and complex views. Simple views based on single table, no group by, having or aggregate function, and these are updatable. Complex views may include multiple tables, aggregation, join, group by, and are generally read only. And different type of views based on storage, dynamic views that are not physically stored, computed every time the query is run, and less storage is required. Till now, this has been studied as per note. And then the concept of materialized views, that is stored actually in the database, physically stored in the database. And when multiple queries are on the same view to save the computation time. And if we are not using the materialized view, every time the query is run, every time a new view is created, which is not kind of good for the computation purposes. So we create a materialized view, which is actual or physical view, and that takes storage space but is more efficient for frequent query performance. Creating a view with check option. Create view user Bikaner as select star from user where city goes to Bikaner with check option. And with check option, what is the purpose of check option? We provide a security that those users which are from Bikaner are given special or the updation or insertion can be done only on those users which are from Bikaner. Okay. This create a view named user Bikaner, a separate virtual table. It select only those users whose city is Bikaner, and with check option will ensure you that you can insert or update rows that satisfy the condition that city should be Bikaner. Whenever with check option is applied, you cannot update the attribute that is the basis of the view definition. For example, you are updating where city is Jaipur. If you are updating the user Bikaner table as city goes to Jaipur, then that will not be updated. It will be considered as invalid update. DDL truncate command. Truncate borrow is somehow same as delete option. tuples will be deleted and schema will remain. Then what is the difference between truncate and borrow? And you must have heard of the drop command, the drop table, drop this, drop that table. See, truncate and borrow will just delete the tuples, the table structure, the attributes, and the, are you getting the imagination? The structure of the table will still remain. And drop will delete the structure also. Then why truncate and truncate and delete are different? Truncate select the whole tuples as a whole and delete in one go. And delete select tuple by tuple and then remove those tuple. So truncate is fast and delete is kind of slow because it moves tuple by tuple. Truncate will be faster than delete. We will learn the reason in the part 2 of this course. Why part 2? Because I am kind of busy in the upcoming few months. So I was thinking just to publish this part of the course. The remaining part of normalization, indexing, functional dependency will be considered as part 2. So in part 2, we will discuss the actual reason regarding transaction. It is related to locking in transaction. Truncate will apply lock on the whole table and delete all tuples in one go, while delete apply lock tuple by tuple and will delete tuple one by one. Okay, we can apply where with delete but not with truncate. What's the purpose of where? To apply condition. We can apply condition with delete, that delete this from this table where, and in regarding truncate we can just mention like this, truncate borrow, then all the tuples of borrow will be deleted. Delete is a command of DML, data manipulation language, while truncate is DDL, data definition language. Drop will delete all the tuples along with schema, so we have to be careful while using drop. Create command, create table, and then you mention the name and then the attributes, SID, SName, address, and then the data types, int, varchar, char, primary key, and all these things. Create table, and then ABC, and you have to mention that which key will be primary key. You can either mention like this, primary key is SID in the end, or you can mention like here also, like A int primary key, B int primary key. But the problem is there cannot be two primary key. If that is the case, then you have to again opt for this value. Primary key A, B as the combination will act as the primary key. You have to be careful. If you want to make more than one attribute as a primary key, then you should not mention like this. If it would have been just a single property, just a single, what do we say, attribute, then it was okay. You can mention like this, int primary key. But for more than one attribute, you should not mention, because this will represent that there are more than one primary key, but this is not the case. So we have to mention like this in the combination. Create table account number in primary key, balance name or whatever, the balance holder name, balance branch, varchar, check that the branch should be in Delhi and Mumbai also. We can apply constraint also. Which type of constraint? Domain constraint. The domain constraint that balance should be greater than 0. Not null constraint, int primary key, all those things. There's a difference between char and varchar. Length type, char is of fixed length, varchar is of variable length. It always uses n byte. If you have written char n, it uses n byte. And if you have applied varchar, then it uses actual length plus half bytes more. Padding, pads with spaces if input is shorter. For example, we have mentioned char 10, and then name is just this. So for this remaining 7 the remaining 7 things, it will be padded with spaces like Ram and then spaces, 7 spaces. And in varchar there is no padding. Performance, it's slightly faster for fixed length data, more space efficient for varying data. Use case, best when data length is predictable or known before. Here, when data length varies. And what about foreign key? How we will set up the foreign key? Create table student, sname, and you apply the data type, constraint, again the attribute name, data type, default value, the data type, the attribute name, data type, and then the constraint that for SID, this will be the data type, and then constraint primary key, this is the primary key. Now we can give names to the constraint also by constraint keyword, and it's optional. Advantage is that we can modify or delete constraint easily using the alter command. We will see the alter command in few minutes. So this is the way to create table and apply the foreign key or not the foreign key, the primary key constraint. Now what about the foreign key constraint? Let's say this was our parent table. We have created a parent table. Now the child table. Create table book, SID int, SID references a student. This SID will act as a foreign key which is going to reference this SID of the table student. SID here of the table book will act as a foreign key and it is going to reference the SID of student table which is primary key. Okay, so SID references student, and if we do not mention anything, so by default it will refer to the primary key. But it's not necessary that foreign key always refer to the primary key of the parent table. Foreign key of child table does not necessarily refer to the primary key of the parent table. It can also refer to the candidate key. Okay, which means if at whichever attribute not null and unique constraint is applied, foreign key can refer to that attribute of the parent table. Okay, so if we have to mention specifically that attribute, let's say x is that attribute of the parent table, so you can mention like this, x. Okay, like here, SID int, and then SID references student, and you mention that candidate key in the bracket. Okay, so this is how you set up the foreign key. First you mention the parent table, you write like this constraint, primary key constraint is applied, and you name the constraint also, PK. This is the constraint name. We can give names to the constraint by constraint keyword. And why we do so? To change, if let's say in future we want to change some constraint of some another table which is already named, then it will become easier for us to change the constraint with the help of alter command. Okay, so this was the parent table, this was the child table. SID int, SID references student. This will automatically refer to the primary key. If you want to refer to some candidate key, then you can mention that candidate key here. Now we'll learn about on delete cascade and on update cascade. Let's continue. On delete cascade and on update cascade. We have already learned about this in our previous lectures. So we have discussed about referential integrity constraint. We have discussed that blind insertion and updation at referencing relation may violate referential integrity constraint. Blind deletion is okay because we were deleting from the child table, and deletion from the child table is okay. The main thing that you have to focus is the child table values should be subset of parent table values. So if you are deleting from a smaller subset, it won't cause any problem. But if you are deleting from a larger subset, you may delete that value which child table was referencing. Blind deletion and updation are at referred relation may violate referential integrity constraint. Blind insertion is okay if you are updating some or deletion of some value at referenced relation, which is the parent table, that may cause referential integrity constraint. Increasing the set of parent table or blind insertion is okay. Okay, so this part we have already discussed before. So delete cascade, if I delete S101 tuple from a parent table, then all S101 tuple from the child table should also be deleted. This is a kind of revision. Delete cascade. If you have deleted some tuple from the parent table, then all the corresponding tuple at which the referencing is being done, that tuple from the child table should also be deleted. Update cascade, if I update S101 to, let's say, S105 from parent table, then all S101 table, S101 tuple should be updated to S105. Let's say if 101 is updated to S105 at parent table, then at child table also S101 should be converted to S105. Okay. Create table. And now how to represent these constraints? This is we have learned to represent the child table, and on child table you write on delete cascade or on update cascade. This will ensure this part. The cascading. Cascading means like stairs. If this is deleted, this is also deleted. Okay. So I am discussing this again due to the syntax. So what is the syntax? We just represent the child table, and in child table you write on delete cascade. That's it. Alter command. We have discussed that the schema of a table is rarely changed because changing the schema will going to affect numerous tuples. That's why alter command is infrequently used. With the help of alter command, we can insert or delete constraints we can insert or delete new column, we can change the data type of a field or rename it. All these things can be done with the help of alter command. There is a concept of restrict and cascade also, we will see in a minute. Alter table, this is the syntax: alter table student, and you can add a new column, add the attribute name and then the data type. You can modify the attribute, modify attribute name and then changing the data type. Now restrict and cascade. Suppose there is a table, child table is referring this attribute of the parent table. Now if I am applying alter table drop column, if I want to drop this column which is being referred by some another child table, then what should be done? Should we allow the database to delete this or not? So this is the thing. Restrict will see the safe deletion. Monkeys are there on the trees. That's why I'm getting distracted by them. So let's continue. Drop column, semester cascade. So this cascade is like forceful deletion. Even if the column is being referred by some another table, another child table, then deleting this column will also delete the relation, the parent and child relation. And restrict is like a safe deletion. If some child is referring this column, then we won't be able to delete this. With column, some referring constraint will also be deleted. Okay, so this was the point. Now grant and revoke, as the name suggests, we use this grant and revoke to grant and revoke permissions. And the syntax is grant privilege name on object name to username. Common privilege name examples like select, insert, update, delete, references, all privileges. So allow the user to read data from the object. Select means retrieving the data, inserting some data, updation, deletion. Referencing means creating the relation of parent table and child table, referring foreign key, referring the primary key of parent table, all these things. All privileges, grant all available privileges on the object. Grant, insert, update on student to Gora. Gora is the name, username, and we are giving the privileges of insertion and updation on the table student to Gora. The revoke command is used to remove specific privileges from user or role that were previously granted using the grant command. With the help of grant, we grant the privileges. With the help of revoke, we revoke the previously granted privileges. Purpose: to take away the access rights from users. Revoke privilege name on object name from username. Revoke delete. So we are removing the delete privileges that was previously given to Gora. In summary, grant give permission and revoke takes them away. These commands are essential for database security and controlling who can do what with your data. Okay, so this was the core concepts of SQL. Now in the next lecture, or I think it may be the next part, we will see, we are going to have a practice test on SQL. I will give you a database, and on that database we will see various questions and answers of those questions. We will use MySQL Workbench.